Are you aspiring a career in IT? Or maybe you are in IT, a developer, for example, but would like to get into cloud and other specialties within the IT, but you are unable to because you lack some fundamentals that are essential. Whether this or that, this course is for you. The course will help you navigate a plethora of different areas in IT at a high level, but will make you understand what are these for and how to work with them. This includes networking, IP addressing, TCP/IP, what is DevOps, what is site reliability engineering, what's platform engineering, network and network security, and other stuff as well. My name is Isa Abu Sharif, and I have been in the IT industry for close to 3 decades right now. I am a certified Cisco instructor and I'm a certified AWS instructor as well. And I have been developing career programs to help people like yourself start or upskill into the modern IT roles. While coaching and mentoring a lot of our students, I have noticed that there is always a weakness in the fundamentals. And the first advice anyone would give you for the fundamentals would be take A+, take Network+, take CCNA, and then take MCSA, the Microsoft Server Administration, and that would be an absolute must. And you spend 6 to 12 months doing that, and you spend a lot of money as well for the certifications, but that is all unnecessary in the modern IT. If you are starting your journey, in my opinion, there has to be 3 main things that need to be there in any content that you are going to use. Number 1, it's going to take you from point A to point B very quickly without fluff. Number 2, it should minimize the effort and should minimize the cost as well for you to get into that area or that specific topic. Number 3, it should not overwhelm you because that is your first step, and this should be easy to navigate. With a little bit of effort and sweat and with a fresh mind, you should be able to navigate and break through that and be ready to the next steps. The unique thing about this course is that it blends a lot of things together in one course. It starts from what is a computer, what is a hardware device, what is a memory, what's a CPU, what's a GPU, what is a network interface card, and then it explains to you what's a PC, what's a server. And then it takes you from there, okay, so why do we use the server? What's the difference between server and the PC? And then takes you into virtualization. Why do we need to use virtualization? Why do we need to have a physical server? And then we start splitting or splicing and dicing that in a virtual manner. Then it talks about data centers, and data centers, from there it takes you to the cloud computing. It explains to you the networking devices, routers and switches, cables, types of cables, and speeds. And then it shows you how you can build a network in your home, or what are the components of a network in an office, or maybe in a campus, university, or school. Takes you from there to explain to you what is IP addressing, why do we need it, and then how do we actually design a network if we are given a block of IP addresses, what are the differences between public and private IP addresses, and then takes you from there in a scaffolding approach and explains to you what can you do with that in a cloud era. How can you build a network in the cloud, virtual data center, VPC? How can you secure it using security groups and network ACLs? So it takes you through network security as well. And from there, we delve into practicing on the AWS cloud. So you're not going to build any Cisco routers or any emulation softwares. This is going to be logging into the cloud yourself, creating an account, getting $100 free credit that you can use to learn throughout the course without paying any penny. And then we'll teach you how to use the cloud. So you're not only learning fundamentals, you're actually learning and touching the cloud as well in the meantime. Then it will give you a feel of the networking in the cloud and also the network security in the cloud. And it doesn't leave you there, but it then explains to you what is DevOps, the development and operation practice that is used for automating software development. And how did that evolve into site reliability engineering, and from there on to platform engineering. So you will understand what a network engineer would do, what a cloud engineer would do, and what a DevOps engineer would do, what a site reliability engineer would do, what a DevSecOps specialist would do, what a cloud security specialist would do, all of that. You will understand it as you go. The beautiful thing is you don't have to commit to any career before taking the course. So you're not going to end up a technical support specialist or a network associate or network junior engineer. You're not going to do that. You will go through the course, you will understand and touch and feel a lot of things, and then you can decide if you would like to take it further or if you would like to do something else. If you are a developer struggling with IP addressing and network concepts and network security and cloud and stuff like that, this course is also for you. This course wouldn't be possible without people like you watching it. And if you would like to support more free content like this at the same quality or maybe better, the best way to do that is to consider buying the supplemental material for this course. And you can get that at www.dolphinet.com/courses/ITF-course, the IT fundamentals course. You will get free lifetime access to any updates of the course. So any modules that are added, AI, machine learning, ML ops, and so on are going to be included. You will get also quizzes for the course, and you will get assignments with recorded video answers. So you will pause the video, look at the assignment, understand the requirements, do it, and then come back to watch the video and verify whether you have done it right or not. Also, PDF student guide, the entire slides of the course. You will be getting also a support channel for question and answers when you get stuck. And you are going to have a career coaching session recorded as well that will guide you at the end of the course as to which career path you should take and what exactly you should learn as next steps. Also, you will get an IT primer for a lot of the tools that are used in modern IT, like Git, GitHub, Linux, Docker, Kubernetes, Terraform, Bash scripting, and more, which will help you understand what are these tools as you cruise through a roadmap in order to study these. And the roadmaps are going to be explained in the career coaching as well. So thank you very much for watching. And now it's time to get into the course. All right, let's go ahead and start with Module 1, which is the important IT concepts. In this module, we are going to introduce terms that you are going to face or you are going to come across frequently when you are working with IT. And these terms are hardware and software. What's the difference? What is hardware? What is software? And do we have different types of software or is it just one software? And for the hardware, does it apply to our phones or tablets or servers or iPads? What does it apply to? So in this module, we are going to look at multiple lectures, and they are going to cover the computing device hardware components, the common components in computing devices that we come across. Then we are going to look at what is software. If we have discussed hardware, let's go ahead and discuss software and what are the types of software that we'll come across. And that will take us to talking about operating systems and applications as well. So let's go ahead and start with our first lecture. So let's discuss now the computing devices hardware components. Before we jump into that, let's define what are computing devices. Computing devices are devices that we use in our daily life, including mobile phones, including laptops, whether they are Windows or Mac or Linux, including iPads, and it includes as well tablets, desktop PCs, digital cameras, IPTV set boxes, smart TVs, servers, and more. So what are the common components, hardware components to be more specific, for these computing devices? We are going to discuss 5 important components that relate to IT in general, and it's important to understand them at the beginning of IT. So let's start with what is a CPU, the central processing unit. Your phone, your tablet, my laptop, your smart TV, all of them, they have a CPU. Even the smart fridges and all that, they have a CPU. So the CPU is the central processing unit. Basically, this is the mediator between the applications and software and programs that run on that computing device and the hardware components of the computing device. Now we are going to discuss the CPU as the first one in the hardware components. And basically, it is involved in all the operations that happen on that computing device. All right, let's say you are holding your iPhone and now you are going to open Chrome, the browser, or Firefox, or Safari. Where would that program run? And that will be the random access memory. So the second component or hardware component is called the RAM. And the RAM is used to run all software that runs in your computing device. The third one we look at is, okay, fine. Once upon a time, I was filming some videos and I took some photos while we were on a trip in a cruise, and then my phone died. The battery ran out. And when I went home and I charged or recharged my phone, I found that I still have all the videos and all the pictures that I have taken. Was that because of RAM, the memory? And the answer is no. When you run the camera program in order to take the videos and the pictures, this program ran into the RAM. But when you take pictures and all that, they are saved on a persistent or a permanent storage location in your device. And that is called the disk drives or the storage drives available on your phone or on your tablet or on your laptop. And they could be of two types. The older ones are called HDD, hard disk drives, and these are older storage types, slower storage types as well. Or they could be solid state drives, SSDs, and these ones are more modern and they are faster, but they are more expensive as well. So this is used, the storage, to provide persistent storage. Basically a storage that is not related to whether your device is turned on or off and whether it has power or it doesn't have power. This is what persistent storage means. That means as long as the device is not defective, you will be able to retrieve the data that you store on these drives. Then we come into the fourth component, the hardware component. And why do we call it hardware? Because we can touch it, we can feel it. If we open the device, we can see it. If you open your laptop, you can identify where is the CPU, where is the memory, where is the storage, and so on. That's why it's called hardware. Hard, something you can touch or see or feel. Then we talk about network interface cards, and this is how your devices interact with the surrounding, basically, with the outside world. That's how your iPhone connects to the Wi-Fi and then to the internet. That's how my laptop connects to the Wi-Fi at home, and then I can print on my printer, or I can connect to the internet, or maybe log into the corporate network. So these are called network interface cards, and they could be wired interface cards or they could be wireless interface cards. Of course, this image is kind of old because it used to be like that, but now it has been integrated within the phone electronics and within the laptop electronics that you don't see it. But it does exist because you can turn on and off the Wi-Fi and you can connect to Wi-Fi networks. So that connects the computing device to the outside world, and it can be wireless, WLAN or Wi-Fi, and it can be wired as well. Then we talk about monitors. In your phone, when you look at the display, that's your monitor. On your laptop, when you look at the screen, that's your monitor. And so on and so forth. TV, when you run your TV, you look at the TV itself, which is the big display or the big monitor. So this is to read or view the desired data from the device. And monitors can be built into the device like phones, or they could be external to it. We still see desktops in offices and all that where they have the compute device itself, but then it's connected by cables into an external monitor. Last but not least is what accelerates graphics when you are playing games, whether it is FIFA or Call of Duty or whatever the game that you are playing. Then the graphics needs to be fast because the game is all about graphics, right? When you are playing movies or when you are rendering videos, you need to have acceleration for the graphics as well and for the video and so on. And this is where the GPUs or the graphic processing unit or the GCPUs come into play, and they could be built into the device or they could be cards that connect to the device. So there are other components, hardware components like the power supply, the USB ports and so on, the fans and so on, but these are not of relevance now to our career in IT. We can read about this later on if required, but for now and for our discussion and getting into the cloud and DevOps and programming and all that, you don't need to talk about power supplies and fans and USB ports and all that stuff. So these we are going to exclude from our discussion for now. Okay, great. Now, how can I measure the CPU? Is it by kilograms or pounds or centimeters or meters or yards? How can I identify the strength or the power in the CPU or in the memory or in the storage and so on? And these components, they have units. So for example, the CPU is measured by speed, and the speed is measured in gigahertz. So the more the number next to gigahertz, 2 gig, 3 gig, 4 gig, the faster and the more modern the CPU would be. So if you talk about 1.6 gigahertz, 2.3 gigahertz as examples. Then when it comes to the memory and the storage, they are measured in what we call gigabytes or gigabytes. And if it is large, 1000 gigabytes is terabytes or tebibytes. So for example, if you talk about an SSD drive, the size is 10 terabytes. This is a good size storage device. Network interface cards, it's all about the speed, how fast it can transfer data to the outside world and receive data from the outside world. And that's why it's measured by how many bits or bytes per second I can transfer. And the higher the number, the faster the network interface card is. So for example, 100 gigabits per second card or NIC card. All right, so now we understand the hardware. How can we use it? So if I get the phone, do I just need the hardware? When I get the iPad, do I just need the hardware? When I push the on or the power on button, then I start to see stuff, and like there could be graphics, there could be text, there could be paragraphs, there could be licensing information. It all starts to show up. Where is this coming from? And to use the hardware, we need software. And that will lead us into the next discussion, which is software types, and so on. Let's talk about software in general and about operating systems. So what is software? Anything that is not hardware. We said the hardware is something you can touch, you can feel, or you can see at least. So software is something the programmers or the developers are going to write in a specific computer language in order to provide instructions that will tell the computer, the CPU, and so on, what to do exactly. For example, I have a software that I installed. It's about Uber. And for Uber, I need to reserve or book a ride, right? There has to be software commands, programming that has been done in that Uber application in order, when I try to define where my location is and where I'm going to and what type of a ride I'm looking for. And it is the invisible part that you don't see and you can't feel, but you can use it. If we talk about applications, Uber or else, games, operating systems, websites, all are software. And these are all examples. So now it is the time to dive deeper and find what are the types of software that we are going to interface or act upon when we are in IT. And that will take us to the first type, the system software or the operating systems. So the operating system on a computing device is the system software. For example, you have a laptop that has Windows on it. So what is your operating system? It is Microsoft Windows. I have a laptop that is Mac OS. What is my operating system on my laptop, on my computing device? It is Mac OS. You have an iPhone. What's the operating system on the iPhone? It's iOS. I have an Android phone, a Samsung phone. Then what is the operating system? Android. So that is what the system software is. So the system software will manage the hardware resources or the hardware components of the computing device it is installed on. So the operating system is responsible for running the installed applications and coordinating that with the hardware. So whatever the application is supposed to do, it needs to run some instructions. It needs to output something through the Wi-Fi to go to the internet, to Uber, to book the ride. So it will facilitate that to happen. and it will handle the files and permissions. Let's say I have saved a video on my laptop, but I don't want you to see it. So I'm going to put access permissions on that file where only my username on the laptop will be able to use it. So even if my wife or one of my friends tries to use my laptop, they will not be able to get to that. The operating system is the part on your phone where you can add your face recognition. And then if someone else puts the camera in front of their face, it will say that there is no match, or the fingerprint, or the password. And the operating system will provide you a user interface, and that could be a graphical user interface. Like for example, as you can see on the screen, I have the launchpad where I can click on a lot of programs that I have on my MacBook, and then it can start. So for example, I can click on FaceTime, and then FaceTime will start. I have multiple screens, so it started on a different screen, but here you go. All right, so this is called a graphical user interface, something you can interact with using your mouse and maybe some clicks, or maybe if it is a touch screen, you can touch on the screen on your iPhone, and that's it. So that is a graphical user interface. So what about the CLI? Here's an example of a CLI. So this is a terminal program that we have in Mac OS, and you have something similar on your Windows device if you are using Windows, called CMD. So if you go to the search bar and you type CMD, then a black window is going to open, and then you will be faced also with a cursor like that is flickering or flashing, and you can type commands. So for example, here I can type make directory IT foundation. And if I do cd IT foundation, I have created a folder somewhere to store files into my operating system, and that is called ITF, and it exists under the path downloads on my user, which is DolphinNet. So this is dealing with computers using, or with your computing devices using CLI, command line interface. So here if I type date, it will tell me that we are on September on this date in this year, for example. So how did it understand this? The operating system understands this command, and that's how it understood that it needs to show me the date, day and time and hour and so on. Make directory or make dir, it understood, the operating system understood that I need to create a folder where I'm going to create some files, and this is called ITF. So reserved a place, a location where I can start to create files. So for example, I can do touch, and then I create file itf.txt. And if I do ls, you'll find that ls means list the files that exist in this folder. And you'll find that I have a file called itf.txt. So as you can see, we can deal with the operating systems using CLI, graphical user interface, like the screen in front of you, or using GUI, graphical user interface, which is more common when it comes to Windows and so on. So the operating system will keep everything working together. The hardware and the applications and everything, they work in harmony because of it. And examples, as we mentioned, Windows, Linux, and Mac OS, and these are common icons. You could be familiar with at least one of them, if not all of them. GUI or CLI, which one should I use, and which operating systems will give me this one or that one as an option? So the graphical user interface, you are using icons, windows, and mouse. And if you are doing CLI, then it's going to be commands, basically, as we have seen. So if we need to compare Windows versus Linux, a lot of people ask that at the beginning of their career, and you get the two advices. No, study Microsoft Server Administrator, and others will tell you, keep away from Windows, go for Linux. I am an advocate of the second one, because the modern IT, whether you're talking about cloud, whether you're talking about machine learning, AI, data analytics, and so on, the modern IT, even if you would like to learn a lot of tools that we're going to discuss later on, containerization, Docker, Kubernetes, and so on, it needs a high level of comprehension, understanding, and familiarity and experience with Linux, not Windows. One would jump and say, okay, but Windows also can run this and that. I'm saying what is common, what is more in demand in the industry, and that's why I would say go for Linux. But if we compare the two, if you compare Windows and Linux from a features perspective and usability perspective, Windows will be mostly graphical user interface. People like to use graphical user interface on Windows more than the command line. Linux, although you can run applications like browsers and so on, but it's mostly CLI, and that's the power of Linux, although people don't like to memorize commands and all that. It comes with experience. We're going to cover Linux later on in the course. The cost usually is paid on Windows, and it's free or open source primarily in Linux. We're going to come to what open source means. Popular use, desktops and laptops. Personal use more, even the corporates and all that, they prefer to use, on the user side, Windows mostly. But on Linux, a lot of people now are shifting into Linux because it doesn't have any licensing and they don't like to use Mac OS or Windows, or maybe because of affordability. But it's very common on servers where we run the applications. We're going to come to what servers are in details. Flexibility, you have limited control on Windows, but it's highly customizable when it comes to Linux. So what is open source software? That means I build a software and then I allow it for the public where they can download the source code, the code itself, the program that I have written, and they can update, they can change, and it is all for free. That's what an open source is. Linux is a perfect example of the operating system that is running as an open source. All right, so we have discussed the fact that one type of software is the system software, the operating system. Now, what about the applications that run on top of it? The Gmail, or maybe the Outlook, or could be Uber, or it could be Uber Eats, DoorDash, and so on. There's plenty of applications that we use on our phones, or maybe applications we can access through our browsers, banking, and so on. Amazon and others. So what is the other type of software? And we mentioned it already, which is the application. So the other type of software is applications. And an application built by a developer is built for a specific purpose, right? Maybe I'm doing an application, personal one, because I'm going to track my calories or the steps I'm going to walk or the meals I'm eating. Maybe an accountant is going to build an application to provide it to its customers so they can upload documents about their expenses, or so it's easier for them to do the bookkeeping. So an application is a software program that is built to do a specific task. The task could be online banking. The bank will build the application so customers can download them and they can manage their accounts, they can upload checks and so on from their phones. Examples for applications, we have Chrome, the browser. We have Excel, Microsoft Excel, spreadsheets, we have Zoom, and we have WhatsApp. These are examples of applications that we are all familiar with and use. So applications run on top of system software. So the applications will require the system software, and the system software gets the instructions from the application and coordinates that with the hardware. So that's how it works within a computing device. Are there different types of applications? Yes. So desktop applications, they run on your laptops, Mac OS, Linux, Windows. So they run on PC or Mac, and examples are PowerPoint, Word, and Excel. Mobile applications run on mobiles and tablets, and examples are Google Maps and Uber. One might say, okay, but I can run my Google Maps on my laptop. I would say yes. There are web applications that you can access them through their app or through the web, through Firefox or through Safari, for example. So they run in a browser, and examples are Gmail, Canva, your banking, online banking, all of that, your school or university account, all of that can be accessed through a web application, through a browser, basically. And these applications can be built to run in the cloud. So cloud applications, that means an application built to run in the cloud. So Google Docs, for example, and Zoom, they all run in the cloud. Okay, so let's do a quick recap. We have learned that computing devices have hardware components. Hardware components are things that we can see, we can feel, we can touch maybe. So this is hardware. Anything that I can hold on to or see or touch, that is a hardware. We agreed that there are plenty of components, but we only looked at 5 of them. We looked at monitors, we looked at CPU, RAM, storage devices, network interface cards, 6, not 5, and we looked also at GPUs. GPUs may or may not exist in devices, depending on how complicated and advanced the device is. Then we looked at software. We said that the hardware cannot be used by itself. We have to have programs that will use the hardware, and we take advantage of using these programs. And we looked at 2 types of software. Software that is built by developers as an operating system, so to make that device operate, to make the hardware usable. So the operating system in itself is not what you are going to use, but it is required and mandatory in order to be able to use the hardware. And the second level, or the second type of software that we have looked at, is the applications. That's the actual programs used to do a specific task. The developers, when they built the application, they did not think about controlling the hardware. They thought about, okay, this application will be for a medical clinic or for a hospital or for a sporting club or maybe for a ship in the sea or maybe for a port that will upload and unload and track what has been shipped, exported, and imported. So the applications can be used on desktops, on mobile applications, or through the browser, and they're called web applications. All right. So this is what we have learned so far. We didn't yet do a deep dive into any type of hardware or software. So let's go ahead and look into that in the subsequent sections. So let's now talk about module number 2. And module number 2 will be about servers and virtualization. So we learned about hardware and software and applications in the previous section. Now, let's talk about a computing device that is commonly used when we talk about IT in general to deploy applications and software. And this is the servers. And servers, as we will explain, they posed some limitations for scaling, for cost, and all that, which had led to the emergence of what we call virtualization, or dividing a server into virtual servers. So let's go ahead and look at these 2 topics in this section. We'll cover what a server is, physical servers, and then we'll talk about what were the limitations and how did we get into virtualization and what virtualization is. So let's talk about physical servers. You will come across the concept bare metal servers. Physical or bare metal, they refer to the same thing. So we knew about hardware components for a laptop as a computing device. Is a server a computing device? And the answer is absolutely. The physical server is nothing more than a muscle computing device. A computing device that has high specifications, basically. And this is an image of how a rack-mountable server that can be installed inside a cabinet, we call it a rack. So the physical server is basically a powerful computer, powerful computing device that has a good size of memory, the RAM, where you can run big applications or many applications, 1 or more CPUs. Sometimes they have 16 CPUs, 32, 64, and so on. And it has 1 or more disk drives for persistent storage, and that could be in the terabyte size. And 1 or more network interfaces to connect to the outside world, 1 or more GPUs. So the more expensive the server is, the higher the specs or the sizes and specifications of these hardware components would be. So a physical server is hardware. What do we need to use the hardware? We need to run an operating system. So an operating system, whether it is Linux, Windows, or any sort of an operating system that can be installed on server machines to be able to use the server. So we have to have one. Of course, the most common one in the cloud is Linux, but also Windows servers are common in the traditional IT more than in the modern IT or the cloud. We can install 1 or more applications on top of that operating system in order to fix them or install them or use them into that server. And this is how it would look like. So we have the physical server. It will have 1 or more CPUs, a good amount of disks size and memory, and it will have 1 or more network cards, 1 or more GPUs. Then we install the operating system of choice, and then we can run one or more applications on the server. And depending on the specs of the servers, the muscles and the size of the muscles and how hard it can process, how fast it can process, it can support on these applications. They can support tens of users, maybe hundreds of users, maybe thousands of users. All depends on the specification of the servers, how many CPUs, how fast, how much memory, and so on. So the high specifications in a server as a computing device allows it to serve a lot of users concurrently. All right, so here is an example of how we can benefit from using servers with the operating system installed and the application on top of that to build a Dolphin Ed Academy website on the internet. So this is an e-learning, an edtech company on the internet, and we are going to install the website software on the server, and the server will be connected to the internet, and then clients are going to be using mobile applications or maybe their desktops and laptops in order to get to it through the browser. In either case, any web application is an application like websites, e-commerce websites, or any application accessible over the public internet. So how would that interaction happen? The user is going to start the application, the mobile application or the browser, and they will send in a request to the server, and the request will be, for example, to open the page and then to log in. And then the server is going to, the application on the server, to be more specific, is going to send the response through the operating system, through the peripheral or the network interface card or cards available on the server, back to the internet to the client. So this is an example of how we can use the hardware and software in the form of operating system and application on a server connected to the internet to provide services through the web to clients, be that client a mobile app or a desktop client through a browser. So this is all good stuff. Now, is servers the magic solution to everything? And that is what we'll explain next. All right, so now it's time to talk about virtualization. And definitely, if we move from a physical server on top of which we install an operating system and an application to a different solution, a different way of hosting the operating system and applications, that means there should have been some limitations in using physical servers as is. So let's go ahead and find out about these limitations. So physical servers, as they are bare metal with an operating system and applications on top, posed or showed limitations when scaling and when installing multiple applications on a server. These include underutilization. If we have only one application on a physical server, a muscle computing device that costs a lot of money, then the average utilization, if it is in the form of 10, 20, 30%, that means underutilization. We have a lot of muscles, but we are only requesting that server to use maybe one muscle of this bunch of muscles. When we install multiple applications, we would need to see isolation between them. So the files will not intermix in the file system, such that when someone for application A is trying to troubleshoot, maybe they will remove some files, delete some files, or update them. Maybe they will impact another application. So we need isolation. And also, some applications are going to deal with critical data. Others will not deal with critical data. So we want isolation between them or among these applications on the same server for security reasons as well. So in order to do that, the only way with physical servers is to have multiple servers, separate servers, and that will be 100% isolation. Also, if we need to build environments for testing and development and production, then we have to multiply or duplicate the environments again and again, which is extra cost. And if we would like to maintain isolation and security and scale means that this application is becoming so popular, a lot of users are coming into Uber Eats, for example. So one server is not enough. We have to add more servers. Adding more servers means it's now going to go through the procurement cycle and lead times for delivery, installation, deployment, and it's going to be more expensive because now we are talking about multiple physical muscle computing devices. So that will raise the cost if we would like to scale an application that becomes popular. And of course, the lead times for delivery and shipping and procurement and all that is going to make that slow. So to scale an application, to scale an infrastructure, it will take a long time. And also backing up, so taking copies of the application software and the data on the servers in order to retain it in case if we have a hardware problem, then we can restore that application again to a workable situation or status. Then that is also hardware dependent, depending on what is the hardware configuration, what's the server configuration, how many CPUs, how many this, how many that, and it is then difficult to restore in case if we have a failure. All of these limitations, underutilization, isolation, security, scalability, and the rising costs led to the concept or the emergence of what we call virtualization. So what is virtualization? Virtualization is a means that would allow us to divide a physical server into virtual servers. So now we don't have to use the physical server as is, we can split it virtually. So we're not going to bring a saw and cut into the server. It's a software that will divide the resources virtually in software only across different virtual servers. That's exactly what it is. So when we have the physical server, the bare metal, where we have the hardware and then the operating system and the application or applications, depending on how many we have, here is how we are going to virtualize it. So we are going to add a layer called the hypervisor or the virtualization engine. Once you have the hypervisor, multiple virtual machines, virtual servers, will be possible to create, and they are going to share the physical hardware resources on the server. So this is as if we have this server split into 3 actual servers, but they are not physical, they are virtual. And the good thing about virtualization is it allows you to have a different operating system on each one of the virtual machines. Here we have to choose either it is Microsoft Windows or Mac or Linux. So you have an operating system of choice, and it's one operating system. On virtual machines, the same physical server will have different virtual servers. Each of them, you have the option to install a different operating system onto. So virtualization will enable us to run more than one virtual system, virtual machine, virtual server, and multiple operating systems on a single physical server. And that is magical if you think about it. And of course, when we come to the low utilization or underutilization, now we will have multiple servers with multiple applications isolated, which means we have better utilization of the physical server that we had before that was underutilized, where isolation was difficult to do as well and backups were a challenge. So each virtual machine is isolated. They are isolated from one another, and the hypervisor, this magical layer that we add here, will use virtual instances of the hardware components on the physical server. So the memory is going to be split virtually into multiple virtual memories. The CPU or CPUs are going to be split into multiple vCPUs. The disk is going to be distributed or split also into multiple virtual instances of the disk. And then we'll start to assign, the hypervisor will start to assign these into the different virtual machines. The backups, we can take a snapshot, a backup, a copy of the entire virtual machine, and then we can move it, upload it into somewhere else, and then we can fix it on another hypervisor, compatible one, and then it will run as if it existed on that hypervisor. So let's take a closer look at how it would look like when we have multiple virtual machines on a physical server. So this is our physical server. And these are the physical hardware components on the server. Now we install the hypervisor. So that is a software component that will be installed, will be fixed on the physical server. And that's an emulation layer. And then we can, through the hypervisor, start to create multiple virtual machines. How many virtual machines? If you are going to split the vCPUs and the memory and the disk among them, then the limitation would be how much CPU, how much memory, how much disk, and how much GCPU and interface cards you have. So if you have, let's say, 10 terabytes of disk space, and then you give each one 2 terabytes, that means you can do 5 virtual machines. Of course, there are ways called oversubscription to do more than 5, and then assuming that they are not going to use that allocation, all of them at the same time, but that is out of our scope for now. Let's keep in mind now that the physical resources on the physical server is the limitation on how many virtual machines you can create on a physical server. So you cannot do 1,000 machines, each of them with 2 terabytes if we are talking about a 10 terabytes disk space available on the physical server. So the hypervisor is going to allow you to create virtual machines. When you are creating the virtual machine through the hypervisor, you can decide how many virtual CPUs you are going to allocate, how many virtual memory you are going to allocate, how many virtual disks or how much disk space on a virtual disk you are going to allocate, and also on the network cards. Similarly for the second, third, and so on. Once the VM is created, then you will have access to it as if it is a physical server, and you have to have an operating system installed on it, and then you can decide, is it one application per VM or multiple applications per VM? So this is a virtual machine, and then the process is repeated for the second, third, and so on until n virtual machines on the same physical server. Okay, so a virtual machine must have a full operating system, a full one, and it gets an allocation of the CPU, memory, disk, and GPU and memory card in the form of virtual instances of these resources. Okay, so the hypervisor is how we can share the physical server across or among the VMs, and each one of them will get virtual network interface card, virtual disk, virtual memory, and virtual CPU. What are the common vendors or the popular vendors when it comes to virtualization? We have VMware vSphere as a solution or an engine for as a hypervisor. We have Zen, and then we have Microsoft Hyper-V, and we have Linux KVM, and then we have Oracle VM VirtualBox. So these are different hypervisors that we can use from different companies, as we can see here. And of course, we have the VMware workstation as well. So we have a VMware vSphere, which is industry scale basically, and VMware workstation is something you can do on your laptop or on your machine. The hypervisors are in two different types. Are you installing that hypervisor on a physical server, or are you installing that on your laptop? So that will define whether it is type 1 or type 2 hypervisor. So a bare metal hypervisor, this is type 1. It's installed directly on the bare metal hardware without needing a full host operating system. So basically, the hypervisor will have a mini OS within, so it can deal with the hardware of the physical server, and it doesn't need a full operating system. And this is how it would look like. So we have the hardware, the physical server, and we are going to install the hypervisor right on the hardware. And as we said, it has a mini OS with it. And then we can start through the hypervisor, create different VMs, and then have the operating system on each of them, and they can be up and running. Examples are Microsoft Hyper-V and VMware vSphere and Zen. Type 2, when we talk about a full operating system on the physical hardware, and this is common more on the laptop side. So if you want on your Mac OS or on your Windows laptop to install a virtual machine or a hypervisor, and then you start to create, for example, a VM to practice for a Linux lab or for networking or so on, then you can do multiple VMs, small specifications, and you can run with that if your laptop has enough resources. So in that case, your laptop will have an operating system. It could be Windows, it could be Mac, it could be Linux, and then you are going to mount the hypervisor on top. An example is VirtualBox from Oracle, for example, and then you start to create VMs and you start to install operating system on them, and then they will be functional. But of course, this is when we are talking about production grade. This is when we are talking about personal use. So Oracle VirtualBox and VMware Workstation are examples of what you can do with this. Now the question, we have talked about physical servers, bare metal, and we talked about virtualization and all that. But where is the physical location a company would put these physical servers? So where would that be placed? Would it be placed under a desk in an office, or maybe in a storage room in an office, or are there locations which are equipped and purposely built, and the fit out is to become a place where you can host those physical servers and the application on them? And that is data centers. So our next discussion is going to go around data centers. What are they and how do they look like, and so on. All right, now since we are going to do most of our hands-on lab and practice in AWS in the cloud, we are going to work extensively in the cloud in this course. And that will be a great opportunity for you to learn the cloud as well while you are learning the IT fundamentals. So what we'll do is we are going to create an AWS account, free, don't worry, you will not have to pay anything. And that will make it easier if you have an old laptop, if your laptop is busy or not performing, it's full, the disk is full, you don't have to upgrade to another laptop, just continue to use it in the cloud. That's it. So what do we need to do? We need to go to aws.amazon.com. aws.amazon.com, and you will get a page like this one where you click on create account. So we need to open an account. We have to have an account in order to use AWS services. So I'm going to click on create, and this is a free account. From here, get started for free, and this will tell you about the options you have. You have a free plan, you have a paid plan. What's the difference between the two? The free plan is an account. It doesn't give you access to all AWS services. So there will be some services that you will not be able to use. And scaling of services is going to be capped. So when you are working and you are trying to scale and do like advanced stuff, it will not scale accordingly because there are some thresholds based on the credits. So these are the disadvantages, and the account is going to be closed after 6 months from creation. You will receive $100 credits as soon as you open the account. So you can use AWS services worth $100. If you use them in 1 month, that's it. The account is unusable. You cannot add credits unless you change it, upgrade it into a paid plan. And there are some activities that if you do, exploring some AWS services, and if you do them within the 6 months, you will get another $100 credit. So you'll have $200 credit, and that's a lot of money for someone who's learning AWS. I mean, that could easily help you do a lot of AWS stuff that would take a year to work on. And you will have free usage of select services, and there's no charges whatsoever. So if you are worried about incurring any charges, that will be the account. But of course, you have limitations. You can always upgrade within the 6 months to the paid plan. And in the paid plan, the same thing. You get 100 credits and another 100 if you do the AWS services exploration, includes free usage. You can scale and all that, but you are going to be charged if you go beyond the thresholds. Workloads can scale beyond credit thresholds because it's paid, you will pay for it, and you have access to all AWS services. If you need to know more about the differences, there is an FAQ. So these are services that are available in both, and you can keep exploring which services, and you can always click on show more and it will tell you if this is available in both or not. And you will get this is the FAQs, and in the FAQs they will tell you about, so here the free plan accounts, paid plan accounts, earning additional credits, what you need to do exactly, and what are the activities that you need to do in order to explore that. How do I earn additional free credits? And you go through this console home walkthrough and dashboard, and you can find out what needs to be done. So you have everything you need, and you can find it by yourself without having to ask me for any questions regarding these accounts. All right, let's go back to creating the account. You need to write an email that is going to be the communication between AWS and you for bills and for updates and so on, and a nickname of your choice for the account. So once you have entered the email and the nickname, click on verify email. So what they will do is they will send you a verification email to ensure that this email is an active email and you have access to it. And once you verify, you will be taken to the next step. So once you enter the email and the name, you will get into this CAPTCHA where you have to do the security verification. So go ahead and do it and then click on submit. Once you do the CAPTCHA, enter a code that was sent to the email that you have specified. So you need to get that code from the email and enter it here and then click verify. And as you can see, the email has been verified now. Now you need to configure the root user password. Basically, the username will be the email that you entered, and this will be the password, and this is the most powerful user in your account. So you have to be very careful, and it's better to use a password phrase, not an easy to guess password. And the conditions are available here. It has to be at least eight letters long, at least and it includes 3 of the following: uppercase, lowercase numbers, and non-alphanumeric characters. So go ahead, create your password and confirm it, and click on continue. You have the 2 options that we talked about, the free and paid. It's up to you. If you don't want to be charged under no circumstances, but you're okay that you will bump across some services that you are not going to be able to use. And of course, for this course, the free plan is more than enough. I would go with the free plan for now. Now you need to select what will be the use of this account. So I'm going to click on personal, put all the details, your personal details. It has to be accurate. The phone number has to be accurate. The country and all that has to be accurate, because they are going to send you a code to your phone and you will need to verify it. So now they have verified the email, they will need to verify the phone number as well. So fill this, and after you do, then tick this box and click on agree and continue. Now you will need to enter credit card information. You might be wondering, why is AWS asking me for a credit card if this is a free plan? Simply, they need to verify your identity in 3 different ways. Email was one, phone was another, and now credit card information. That means they know you, they can verify, and there is no way you can have wrong information entered here, because they will check and probably they will hold like $1, €1, or a small amount. Only hold, they are not going to charge it, and it will be released in a few days. But this makes them sure that there is a payment method just in case in the account. And if you upgrade to a paid plan, then any extra charges are going to be charged to this credit card. If you are on the free plan, they will not charge you. So don't worry about that, but you have to enter this information. There is no way out of this. So fill this information and click on continue, and I will see you in the next page. Now is the sign up for AWS. You need to confirm your identity, and now they have given you an option. They can either call you and give you a code, or you can receive a text message. So both of them are used to verify that this phone is yours. So go ahead, fill in the information and click on send SMS, or you can have a voice call if they want to call you and give you the code. Either way, fill in the number, click on send, and then they will text you, or they are going to call you depending on your choice. Go ahead, do this step, and I'll see you in the next page. Now you are faced with another CAPTCHA, and then they will send you the verification, or the verification code, or the text message. So you have to fill this CAPTCHA, and then you will get the code. All right, so this is the page, and you will get the code. Enter it here and click on continue. Okay, so I got the code. It is 5320, 5320. Continue. Okay, in my case, because my credit card, my phone number, and all that exists already on AWS, they are refusing to give me a free plan, and they will upgrade me to a paid plan. So anyone who created an account before in the good free tier all times, where we could create 5, 10 accounts and use free tier in all of them for 12 months, this is not the case anymore. You need to use a new credit card, a different phone number if you would like to get around and have another free tier. In your case, this shouldn't be a problem, because if you are a newbie to AWS, this page will not appear to you. So in my case, I'm going to say, okay, I agree. I'm not eligible for the free plan anymore. Anyways, I'm going to click on confirm because I want to show you the rest. So that page will not appear in your case. Now we come to the support plan. Leave it to the basic and click on complete sign up. All right, so I'm going to click on that. And guess what? Congratulations, you have an AWS account right now. Click on go to AWS Management Console. All right, so once you log in, that means you're going to the Management Console. This is the portal. This is the orchestration and automation and management tool in AWS. So I'm entering my account right now, and I'm going to take you through a walkthrough quickly, but let's close this video and start a new one to do the walkthrough so we don't keep this one for long. All right, so let me take you through a walkthrough of the AWS Management Console to help you get familiarized about the AWS Management Console, how to use it and all that. Let's go ahead. Okay, so these are a few messages. If you'd like to go through them, that's okay. For me, I'm not going to go through them. Let me make this a little bigger. So this is the console home for a brand new account. So this is an account which doesn't have any recently visited services or anything. If you click on this side, you'll find the account ID. You can go to billing and cost management, where you can look at your bills and find out your consumption and so on. You can sign out. And here you can see that you have all the AWS regions. So by default, it has chosen for me this as the default, the one in Stockholm in Sweden. But you can switch to a one closer to you because that will help you with the internet latency. If you want to play with an AWS service, work with an AWS service, then you can click on here and you can see that you have here a list of AWS services. Or if you know the service that you are going to work with, for example, in this course, we are going to work a lot with EC2. This is the service that allows you to create virtual machines in AWS. Virtual servers in the cloud, basically. If you would like to launch your own presence in AWS, you have to create what we call a VPC, or Virtual Private Cloud. There are some services under VPC that are created for you by default. You don't have to do anything about them, and they are there for you. AWS assumes that this is like a common denominator that most of the people who are learning might need it, and they volunteer and they create it for you. We're going to learn more about this later on. If you go into one of these services, I'm just going to show you how it looks like. You don't have to know anything about it right now. So usually you have the dashboard. So this tells you where exactly are you right now. So I'm in the VPC dashboard, Virtual Private Cloud dashboard. And these are the settings that I can choose, or the stuff that are under the VPC. When you choose one of them, what you see on the right-hand side will be the details of what you have selected. So for example, if I click on this, these are the subnets under subnet. VPCs, these are the existing VPC. Root tables, these are the existing root tables. Now let's go to EC2, which is the virtual machines in the cloud. And as you can see, this is the service. Here is the EC2 dashboard, as it says. Instances means virtual machines, and instance types and launch templates. And there's a lot of configuration stuff that also fall under the EC2 dashboard. For example, if I wanted to create a virtual machine, and you will be amazed at how fast you can do that. So I'll click on instances. I don't have any, as you can see, but I can choose to launch one. So this is the page that at the end, when you fill in all the information, you can just click on launch instance and boom, you have a virtual machine in the cloud. So what do I need to do? I'm going to call it first VM, first virtual machine. And here you have the operating system. So you can do Amazon Linux, you can do Mac OS, Ubuntu Linux, Windows, Red Hat Linux, SUSE Linux, and so on. So there are plenty of operating systems you can run on the virtual machine. Remember that the virtual machine needs a full guest OS. And after that, I'll leave it to the default. So I'm assuming that I'm going to go with an Amazon Linux one. Any virtual machine has a VNIC virtual memory, virtual disk, virtual CPU, and so on. So if you look here, you'll find that this is T3.micro. That's the size of an instance or a virtual machine. And it comes pre-packaged. So the T3 micro will always have 2 vCPUs, 1 gigabyte of memory, and here it tells you the prices per hour if you use it. So in my case, I'm going to choose, let's see if I can get to a smaller one. No, that's fine. That's the least I can do. So T3.nano. Key pair. If you would like to access the instance remotely, then you have to create a key pair. Otherwise, I can do proceed without. We're going to explain that later on. Network settings, which VPC or where it's going to land. I'm going to leave everything to the default now because I'm just explaining that to you. Security. And once you are done with all of this, all you can do is launch instance. And congratulations, this is your first virtual machine in the cloud. Successfully initiated launch of this instance. And if you click on that ID, you get to here and you will see that it is running and we have created a virtual machine. Of course, as you learn the particulars or the specifics about each one of the attributes that we needed to configure, then probably it will take you another 10 seconds, 15 seconds, but you will have a virtual machine in no time. You don't have to virtualize your laptop. You don't have to learn about new tools like VirtualBox or VMware Workstation, and you don't have to do nothing. Your laptop is as is. You don't need to split or partition it to include a VM. You don't have to do nothing. In the cloud, in your case, if you are new to AWS, it's going to be free. You have $100 credits, and you can do some exercises and gain another $100 credits, and it's going to be there for you for 6 months. You don't need anything else to do. All right, and at the end of the 6 months, as you advance, you can upgrade to the paid plan, and then you start controlling your expenses based on your usage, basically. You are investing in the environment that would look like the actual environments you are going to work on as you specialize in your career. All right, hopefully that was clear. What I need to do now is I'm going to terminate the instance because my account is not a free account. And once I click on that, guess what is happening right now? You'll find that it is shutting down and it will be terminated in no time. Let's now start with module 3. In module 3, we're going to start the discussion about data center. We talked about servers and applications and software and virtualization, and we said all of that is hosted in data centers. So now it's time to talk about data centers. And after knowing at a high level what a data center is, we are going to take it one step further and we are going to get into what is cloud computing and why did we get from data centers to the cloud and why cloud is attractive. So this is what we are going to do in this module. We are going to cover what data centers are, cloud computing, and cloud services models. What are the different services that you can hire or rent or lease from the cloud? We'll talk about cloud deployments models, and also we are going to talk about if you are going to study or specialize in the cloud or DevOps or AI or MLOps, any one of the modern IT roles would require you to have sufficient knowledge of the cloud. So which cloud you should start with? Is it AWS? Is it Azure? Or is it GCP from Google? This is what we are going to cover in this module. So let's get started. So let's start with an overview of what a data center is. In traditional IT, in the pre-cloud era, and still ongoing, servers and applications are hosted in client-specific, purpose-designed or purpose-built IT data centers. And if we get into a data center, we will see aisles like these ones, and you will see cabinets, as you can see. And if you open one of the cabinets and look from the front and the back, you will see cables on the back side, and you will see the details of the servers that are mounted on the front side. In general, any data center is a considerable space size, real estate size, a building basically, or a floor in a building, or could be the entire building that is air conditioned, physically secured, and manned 24/7 to ensure continuous operation. And this is where the servers will be placed. Of course, there has to be power and redundant power and so on. and servers are going to be connected to a network, and this is how they function basically. We're going to touch on data centers again when we get to the networking component, because we need to talk about what is a data center network, or DCN, is, but that will come later on. Let's continue with our overview of what a data center is. The image that you see in front of you right now, this is the AWS data center in Mumbai in India. So this is how big that is. So if you look at the size of the trees, for example, compared to the size of the buildings that are available in data center, and the redundant power and the generators and all the different utilities that get into the data center, you'll understand what the size is. So for example, look at this car, this vehicle, compared to the size of the building, and then you will appreciate how big that would be. So we talked before about physical servers, and we showed the images of some rack mountable servers, the one that are flat basically. They are not high, they are flat. So the servers that are flat, they have angles or brackets on the side, and that's how they get mounted. So this is called a rack or a cabinet, and each one of these rows that you see here is a rack mounted server. And the rails on the side, the silver components here, the rails on the side, is where the server gets fixed or bolted to the rack. So we can have lots of racks in a data center, and they will be side by side, and usually they can be physically secured, so they can be locked, and only the responsible or the authorized personnel will be able to open that. If you turn around the rack, so the racks are fixed in aisles basically, or rows, and the rows will have aisles in between. So if you move to the back of a row of racks, you will see the cabling part, and this is how they connect into the network. So the yellow and green and white that you see here, these are cabling that goes from the servers to the network, and then from the network to the outside world or wherever they need to communicate with. The term on-premises or on-prem is something that you are going to encounter a lot when you deal with cloud or networking or infrastructure and all that. And this is or refers to a location that is owned and controlled by the customer. So if we're talking about cloud, AWS, Azure, or GCP, these are data centers controlled by these vendors. But if a company, Bank of America, for example, they have their own data center where they host their servers and applications, so that becomes on-prem for Bank of America. So when they refer to their own data center, they will talk and say on-prem, or they will mention on-prem, on-premises. That means it's our data center, it's our location, it's our space. So what is so special about on-premises data centers? This is 100% customer controlled, and 100% the customer is responsible for the design. So they will go out and they will find where is the space. Is it going to be in their building, or maybe they are going to lease it somewhere else? The cost of establishing the data center, if there are any real estate build or cabling or false ceiling or raised floors, all of that is the customer responsibility as well. Who's going to operate that? The customer. Who's going to optimize it? Who's going to upgrade it? Who's going to be responsible for the security, the power, the AC, the cooling, and all of that stuff? The customer. Of course, the customer may hire companies to do that on the customer's behalf, but still, it is the customer who's responsible to find the third parties and sign contracts with them and monitor their work to make sure that they are doing an immaculate job as far as the operations of the data center are concerned. So what is exactly the customer responsible for in a data center? They are responsible for everything: the real estate, the physical security, the cameras and all that, and then they're responsible for the network. They are responsible for storage solutions to store the data permanently, a persistent storage for the data. They're responsible for the hardware, whatever the hardware is, servers, monitors, storage solutions, so on. This is all the customer's responsibility. Virtualization, if they're going to use virtualization, and definitely in a huge data center, virtualization will be used. Then who is the vendor of the virtualization? or the hypervisor, and what's the licensing required, what's the cost, the maintenance, support, and all that. They are responsible for that. They are responsible for deciding on which operating systems are going to be used on the different servers hosting the different applications. Also, if there are any message brokers, components that have to do between the application components, basically for them to communicate with one another, they call it middleware, or they call it message brokers as well. They are responsible for deciding what that is going to be. If it is Python, for example, so what will be the programs that are required to run Python? And we call that the runtime. And what will be the data or the applications, and what will the application communicate and process and store? And also the actuality or the actual applications is also their responsibility. So they are responsible for the entire spectrum, from the physical all the way to the data and its storage and security and so on. It's all the customer's responsibility. Who's going to pay for that? It's the customer. And that's why they call it a CapEx model. This model, the on-premises data center owned by the customer or leased from another company, for them, this is called the CapEx model, capital expenditure model. That means, Mr. Customer, you want all of this? Yes, you have to pay. So you have to pay upfront to buy the equipment. You have to pay upfront to rent or own the place. You have to pay for the construction. You have to pay for the cooling. You have to pay for this. You have to pay for that. So each time you need something new, okay, fine. Please show us your credit card and we're going to charge you upfront. To establish and build a data center, it could cost up to $50–100 million to establish the data center, and then it will be costing a similar cost as well to operate it on an ongoing basis. CapEx model is very expensive to the customers. Think about a startup that needs to start, and they have an idea and they want 3, 4, 5 servers or something, and they don't want to spend a lot of money. If they use services, they want to pay for it as a utility bill, and if they don't, then they don't pay anything. As opposed to buying 3 or 4 servers and then hosting them in a room in their office, and they don't have office, they are working remote. So how can they facilitate the power and the cooling and the storage and all that? They have to buy. So in that case, this is an obstacle and this is a showstopper. They can't afford that. And this is where the cloud computing comes into play as a utility service, which provides you everything you need and you only pay when you use. And this will be our next discussion. So let's look at what cloud computing is compared to on-premises data centers. And does it really provide us with a financial model other than the CapEx or the capital expenditure, which the on-premises data center require? So what is the attractiveness of the cloud? And what is the cloud? Why do they call it the cloud? They call it the cloud because they are going to provide you all the services that you need. So in cloud computing, everything the customer needs is pre-built and ready for use. So we have everything ready for you. Just decide when you want to use it, enroll or sign up, and then go ahead and use it. So that includes the infrastructure, network, physical, storage, all the way to the application and database if you want, passing by storage and security and. So all of that is pre-built. Why do they call it the cloud? Because you don't know where it is. And you shouldn't know, and you are not concerned to know where it is. You need to connect to it, establish your services, not even knowing where that data center is. And someone would say, okay, hold on. Now you are talking about a data center. So how is a data center different from the cloud? In the cloud, the vendor of the cloud, let's say AWS or Microsoft or Google, they have already pre-built the infrastructure. They have already pre-wired the servers. They put them in the racks. They have the 24/7 operations, and they have everything, and it is waiting for customers to come and sign up. Do you have to go to AWS? No, online, on the internet. And the promise is what you use, we'll send you a bill for the usage. And if you don't use anything, even if you are signed up, we're not going to send you anything. You don't have to pay anything upfront. It's up to you. If you want in some services to pay a little bit upfront to reduce the monthly or the usage bills, that's up to you. But if you don't want to, that's perfectly fine. So who has spent money or followed the CapEx model to establish and build that data center? The vendor. AWS or Azure or GCP. For you, that becomes an operational expenditure model. So as you use, you pay. This is exactly like electricity. When you travel and you switch off everything in your home and you don't use water or electricity, the bill will be zero. If you come back and you start using the AC and the water and showers and all that stuff and the bathrooms, then you will be getting some money in the bill next month, right? So that's exactly the same, like your phone bill, like your utility bill, like your Netflix bill, like your Zoom bill, anything. When you use, we charge you. You don't use, we don't charge you. This is called OPEX model or operational expenditure model. And this is where the attractiveness comes from. Think about the startup we were talking about. They don't have a lot of fund and they would like to build a proof of concept and they don't want to buy anything and they would like to switch it off as soon as it is done and stop paying for anything from that point onwards. So in that case, OPEX model is perfect because they know what they are going to use. They will find out about the prices even before using that. And then they can estimate the budget that they'd like to spend. And they have the funds for that little budget. And they start using, finished, switch it off, life is good. Or build the proof of concept when you go to talk to an investor, turn it on so you can demo that to the investor and then switch it off. That's it. So OPEX model is the attractiveness of the cloud. And that's why when someone tells you that cloud is going to disappear or go away or people are leaving the cloud and companies are walking away from the cloud, tell them, I don't think so, because even when the economic or the global economic outlook is bad, companies would save money by not investing in building data centers or refreshing data centers or expanding data centers, and they will find cloud solutions to suit them. So it's easier and faster to build, and also it is cheaper to use in the most case if they are used properly. I'm not saying that cloud is cheaper all the way because it turned out in some use cases to be more expensive, not less expensive. So the message you can respond to those who claim that cloud will go away, that cloud is here to stay and it will stay because of the fact that it depends on an OPEX model and customer doesn't have to pay anything upfront. In a lot of the videos that I watch on YouTube and other sources, I'll find a lot of people, especially the ones who are coming from networking background or the ones who teach networking, Cisco and CCNA and all that stuff. They always claim that cloud is just a data center. That's it. So if you learn networking, you know the cloud. And that's absolutely, absolutely wrong. I come from a networking background. I know very well cloud computing as well. And it is absolutely an inaccurate statement to say that the cloud is a data center. The cloud is built in a data center, but it has hundreds of services that have nothing to do with networking. Yeah, it functions on a network. I cannot say that the data center is the street because people use the street to get to the data center, so the data center becomes the street, and that's wrong. 100% the same analogy. I cannot say the cloud is just a data center. Why? Because when we have a customer with the customer's own data center, then I have to go to the data center. I have to get in to start mounting our own servers, mounting our own racks, connecting them and all that. We are building the data center. We have to know where it is. We have to have access to it and all that. That's a data center. But the data center in the cloud computing is just the component, is just the place, is just the network. But that is not everything in the cloud. Okay, so it's a component of the cloud, but it's not a synonym of a cloud. So this is a wrong statement. Data center is not the cloud. It is a component that the cloud uses to provide services to the customers. So cloud is the data center housing or hosting the equipment and the servers and the applications and the softwares and the teams and all that for the cloud provider. But the automation of services in the cloud and the orchestration, basically, when you get to the AWS management console, you can start to use the different services, including the network, including the storage, including the security, including AI, including machine learning, including any service you may think of. You consume it through a portal or a management console or online basically. And then behind the scenes, whatever you click, it does an action in the background that has been pre-built to do the task that you have clicked. So you have the icon representing what you need to do, but then in the background, there's a lot of automation programs that have been written and scripts that will execute what you are planning to do by clicking that icon. So the automation and orchestration on top of the data center housing and hosting all the services and servers and applications, that provides me what is a cloud. So is it enough for me to learn networking and data center to be expert in the cloud? I would tell you that you are 10-15% of the cloud knowledge that you need to acquire. So don't fall for those who are telling you have to start with a networking career, otherwise you will not be a cloud engineer, and you can't do cloud without networking. That is all BS, and we are going to see that in this course. By the end of this course, you can jump into the cloud. Actually, we are going to start learning the cloud as we learn the fundamentals in this course. All right, so again, this building for AWS in Mumbai in India, that's the data center, but there is a lot of programs and scripts, the automation, the orchestration of services and how they integrate and how they work together, that is done, and it is provided to you through a web application, a web browser. You can log in and then you can consume all these services without having to call anyone. You can deploy servers, you can deploy virtual machines, you can choose the operating systems, the specifications of the virtual machines, and you can launch the virtual machines, and you can work on them without even having to know where that is, and all online and without having to call anyone from AWS. So that's the beauty of the cloud, that's the attractiveness of the cloud, and that's why the cloud will continue. Okay, let's now discuss cloud service models. When I buy a service from the cloud, what is that called? And there are three main ones, and there are plenty of as-a-service models in the cloud. Okay, so we'll talk about the as-a-service or the AAS model in the cloud. Before we start talking about the cloud, let's think about the on-premises. What is the customer responsible for, and what is the cloud provider responsible for? So this arrow, if the color is green, that is the span of the customer responsibility, and if it is orange, that will be the vendor responsibility. On premises, as we mentioned, the customer is responsible for everything from the network all the way to the application. And then there is something called IaaS, or infrastructure as a service. So basically you are using infrastructure only from the cloud provider. For example, you are hosting a virtual machine in AWS, and that virtual machine, it's up to you to decide its specs, it's up to you to decide the operating system and which data and what you will use it for and so on. So in that case, if it is infrastructure as a service that you are using from the cloud provider, then the cloud provider will be responsible for the network, for the storage, for the hardware, and the actual virtualization engine. But once you launch your virtual machine, then choosing the operating system, what middleware, what runtime, what data, what application is your responsibility. So this is infrastructure as a service. Now, what if I don't want to be responsible for the operating system and the middleware as well? I want to ship that and the runtime maybe. I want to have that ready from the cloud providers, and I'm going to take it as part of the service I'm getting from them. So in that case, the runtime, the middleware, and the operating system and everything below is going to be part of the platform as a service, or PaaS, P-A-A-S. In this case, the customer will be only responsible for the application and the data. Data in the databases and data in the application. We'll talk about databases later on. The third one, which most of us use right now, like Uber and Netflix and similar services, is called software as a service, or a SaaS offering, SaaS services. SaaS. So all of them, they have as a service, as a service, as a service. Basically like a utility that you are using and you're paying for. So services in the cloud, majorly, they will fall under one of these categories. And that's how we map services to what service models we are using from the cloud. So these are the three ones. And of course, when it comes to SaaS, Netflix, and so on, you are not responsible for anything except for signing up and using the service. Let's talk about cloud deployment models. Is there anything that prevents a company from building their own orchestration in their own data center and making that a private cloud? And the answer is there is nothing to prevent them. They can do that. And that's why there are different deployment models. So we have public clouds like AWS, Azure, and GCP. And we have private clouds that a bank or a corporate or a hospital may decide to build in-house and to manage it using their own teams. And that will be private for them only, for that corporate or that organization or that hospital only. So in public clouds, what is the criteria or the specs? In public clouds, the resources are publicly shared. So I could be using a virtual machine on a physical server in AWS, and maybe you are from a different country and you launch a VM and by coincidence, it lands next to my VM on the same physical server. Public clouds, by nature, they are shared multi-tenant infrastructures. And internet connectivity is the common way of getting to your virtual machines and applications in the cloud, in this case. And it's best suited for less confidential data. So banks, for example, or hospitals, they will think thrice, not twice, before they are going to move the credit card information for the customers or their bank account details or their confidential information into the cloud. And that's why companies, they don't live off the public cloud only, but for whatever data that they can't move to the cloud, they can establish their own private cloud. And as the name implies, the resources available here are going to be for private use. This is only to host the confidential data that they cannot move into the cloud. But they can have orchestration and automation in their own on-premises data center, so they have a private cloud. So this will be for a single customer, and the customer can be a group of companies and they are using their private cloud. It doesn't have to be like a one business unit in a company. It could be multiple business units in Bank of America that are using their private cloud to host different applications and relevant data. Connectivity in this case, how can they connect into their private cloud? They can have high-speed connectivity from service providers. They can have their own fiber optic cables that they can provide them hundreds of gigabits per second speeds into that private cloud. And this is best suited for confidential data client private systems. All right, what if Bank of America has lots of data that can be moved into the cloud, but also they have sensitive data that they cannot move into the cloud? So they want to use public cloud, but also they need to use the private cloud. What if we need communication between the two? For example, an application in the public cloud would like to highlight or reference some data from the private cloud or the other way around. Then this brings to us what is called a hybrid cloud. So a hybrid cloud is a mix of public and on-premises private cloud, and both are orchestrated to run a single task. And that's how it would look like. So the corporate data center with orchestration becomes a private cloud, and then let's say AWS, and they can have private connectivity between them or connectivity through the internet. Both would work. And of course, orchestrating this and that, and which users will log in here and which user will be able to access the cloud, or both of them, this is orchestration. It's going to be more complex because now we need to manage private and hybrid access and security and so on. And this is suitable for so many use cases, and it is proving that hybrid cloud is the direction that most of the companies using the cloud are using right now, or they will use. So that's why we need to be also knowledgeable about hybrid cloud. And in this case, it's up to the customer to decide what runs here and what runs there, and they can optimize application usage, access, cost optimization as well, more control, and they can run applications where they decide. They can use the cloud only for failover when they have a problem in the data center. This is called disaster recovery, for example, or they can just store their data as a backup, as a second copy in the cloud in case if the main data center fails, then we can launch it from the cloud. Then the trend that is evolving as well, and a lot of companies are deploying, it has proven that cloud providers are not one size that fits all. For example, AI and machine learning, Azure and Google are much better than AWS. So a company might host their AI in Azure or in Google, for example. Whereas the company will be hosting their e-commerce on AWS because AWS is e-commerce, Amazon is e-commerce. So now, once they start splitting workloads among the different cloud providers, this also will give them the advantage of avoiding vendor lock-in. So if I go to AWS and put everything in AWS, now AWS kind of controls me and controls the prices and discounts, because if I'm not happy, I'll have to move stuff and move it elsewhere, which is not an easy task. And that's why vendor lock-in can be avoided by using multi-cloud, and also gives the customer the choice of which one provides me the best features for the lowest cost, and that is what I'm going to follow. So multi-cloud is very important, and that's why we always advocate for learning at least 2 of the 3 major clouds, if not the 3 of them. And I'm not saying you have to become an expert in all of them. That will be great if you can do it. But what I'm saying is you need to have enough knowledge about them, not at the start, as you move on into your career. All right. So in that case, customers will put some stuff in AWS, for example, and some in Azure. And that will be a single heterogeneous architecture that includes all of that. So the organization will continue towards the multi-cloud because it is proving that cloud providers are not all good and at the same price point when we compare the same services in each one of them. So what about hybrid multi-cloud? To make it even harder, this is when we connect our private cloud or data center into the multi-cloud, because we need to consume services from the different cloud vendors that we are using. So that will become a hybrid multi-cloud solution. And of course, the challenge will always be, how will you be able to orchestrate, control security, and define users and access permissions across the different cloud environments that you are using? So we have learned at a high level what cloud is and what a data center is, and we have learned about public and private clouds and hybrid cloud and hybrid multi-cloud and what multi-cloud is. Which one should I start with? I love what you said, and I would like after this course to start working towards building my cloud skills. Should I go with AWS? Should I go with Azure? Or should I go with GCP or all of them? What do I do? And in order to find out, there is something called the Gartner Magic Quadrant. This is a report that is launched annually or sometimes multiple times a year by Gartner. And Gartner, what it does is, here is the public cloud providers comparison. And the Magic Quadrant is this part. So whoever is in this part is one of the top players. So in 2021, AWS was here, Azure was here, and Google was here. I'm not going to talk about the other players. In 2023, see the distances here and how the horizontal gap between them was. In 2023, the vertical distance narrowed and also the horizontal distance narrowed. This axis is called completeness of vision, and this was the ability to execute. So AWS was always at the top of the ability to execute. But here, the vision, which is the vertical gap, now Microsoft is even better than AWS in a vision perspective. But AWS is more able to execute for the customers and services and all that stuff. But Google is getting very close. In 2025, you can see that the gap between Azure and Google in both the vision and the ability to execute is very narrow. AWS is still behind Microsoft in terms of vision, but they are still able, or their ability to execute is better, but now even the vertical ability to execute access is narrowing. The gap is narrowing right now. So it is a catch up. They are catching up, but AWS is still the major player across the globe in terms of market share. By all means, if you are going into AI and machine learning, skip AWS and get into Azure or GCP. They are much better in AI and machine learning than AWS is. If we look at the market share percentage, we'll find that AWS has 30% of the public cloud market share, and Azure has 20%, and Google has 13%. So what's the message? The message is, if you don't know, ask and find the reputable job boards in your country and try to find how many Microsoft, how many AWS cloud, how many GCP jobs are there. And follow that for a 2 weeks, 1 month period to find out which one posts more jobs. That means it's in higher demand. Ask in the forums or on the social media in your country, which one should you start with, which one is providing higher salaries, more jobs, more demand, and so on. Start with that one. If you couldn't find a solution, some people told you AWS, some people told you Azure, some people told you Google, and there is no preference, then go with AWS for the infrastructure or for the start. But as soon as you want to shift into machine learning and AI, move to Azure or GCP. Generally speaking, you are never go wrong with one of these two. But again, if you know which country, which one is the preferred one in your country, then definitely by all means, you are doing the right thing. That's it. So now you know about the cloud providers, about private, public, and hybrid and multi-cloud, and also you know about the models and you know about the cloud provider to start with. All right, so let's start with the first module from the networking focused modules. These modules will constitute a deep dive into networking fundamentals, and that would be more than enough for you to proceed into the modern IT roles that we are going to cover at the end of the course without having to go through A+, Network Plus, and CCNA. All right, so what are we covering in the networking fundamentals module? We are going to cover what is a network. So let's get to introduce ourselves to what networks are. And we will look at the network types, LAN, WAN, wireless LAN or WLAN, CAN, and we'll talk about these in more details. Also, we'll look at the types of network traffic or network flow that could happen within a network. We'll look also at the wired network devices that we may encounter that basically build the network. We'll look also at the network cabling. How do they connect to each other and to the servers and to users and so on? We'll also look at the data center network or DCN. So we introduced what data centers are. Now we are going to dive into what a data center actually looks like. We'll look at the CAN, campus area networks, and we'll also look at what is the internet. I mean, we talked about LAN, WAN, CAN, wireless LAN. What is the internet then? We're going to summarize that, and then we'll look at the wireless network devices, which is something that you are used to at your home or maybe at your office or at the airports. You just take your phone and then connect to a Wi-Fi network, enter the password, and you're connected to the internet. All right, so let's start with the first one, which is what is a network. So a network is nothing but a group of 2 or more computers, and other devices also can connect to the network. It's not only limited to computers, that are connected to that network or to that medium in order to share data. They could be sharing files, they could be sharing images, they could be sharing videos, it could be a server or a website that I'm connected to. Whatever the means or the use case is, they have to connect somehow into the network to be able to communicate. And devices that may connect to the network are not limited only to servers and computers and virtual machines. They could be printers, they could be your laptops, they could be phones, they could be tablets, they could be security cameras. For example, the surveillance cameras could be your smart TV. If you have a network, then you can choose what devices will be connected into that network to communicate. And here's an example for a home network, but this is a wireless network. So we have a wireless device, and then I can have my desktops, I can have my phone, my tablet, my printers connect to it. So I can, from my laptop or from iPhone or my tablet, I can, for example, print images or print documents on the printer. That's one use. Or it could be that I would like to connect to the internet, so I'm going to connect wirelessly within my home, but then I need a device that will connect me to the internet. We'll look into that. Each device in a network must be uniquely addressable. So that means it must have a name or an address of some sort in order to be able to connect to the network and communicate with the other devices and with the internet if required. And that is called an IP address. We're going to cover that later on. So what are the network types that I may come across in my career for cloud or for networking or security or even development and so on? There is one called LAN or local area network. And as the name implies, it's a network in a local area. And then WLAN, wireless LAN, wireless local area network. And then WAN, wide area network. And CAN, campus area network. We're going to cover all of these one by one as we proceed. So let's start with the first one, which is local area network, abbreviated LAN. So a LAN is a network that connects computers and devices in a small area. Like what? It could be a home office, it could be an office business, it could be a school, it could be a building, it could be a company. Any of that is called a LAN. Why do we build a LAN? Because we need to connect the servers for the LAN, we need to connect the printers, the users, and use the internet, for example, or share files or print documents. So examples of a LAN is all the computers, servers, printers, and CCTV cameras in a school. So if I have a school, I would like to have the library connected to the internet. I would like to provide internet access to the students maybe, or the teachers. It could be wired or wireless. I want to connect the smart boards in the classrooms to the network as well, so they can share documents and files and stuff like that. And this is how it would look like. So I have the LAN, which will be composed of or consist of network devices. We're going to talk about what these devices are. And then we can connect servers, tablets, we can connect printers, smart boards, maybe phones that work on IP, on networks, printers, maybe security cameras and screens, laptops. All of these are possible connections in a LAN. And of course, I would connect that into the internet, so students or researchers or teachers or assistants, they will be able to send and receive emails and connect maybe to the Ministry of Education and other sites while performing the classes or while presenting the classes. The second type is WLAN or wireless LAN. So the wireless LAN, it's similar to what a LAN is. So it's a wireless network in a small area. It could be a shopping mall, it could be school, it could be an airport. I mean, relatively small, but I'm not talking about 2 meters. I mean, it can be multiple buildings even attached, or maybe a campus building, but that would be a big or a larger wireless LAN. So it is like a LAN, but it is wireless. So we don't use cables to connect all the devices into the network. Examples to that, when we use our phone, laptops, or tablets, when we connect to the Wi-Fi network at home or in the office, that is a wireless LAN. And here's how it would theoretically look like if this is what we're talking about. And of course, we need a device. We call it the wireless router. We'll talk about what a router is later on, in order to be able to connect to the internet and then provide the Wi-Fi service to the devices. So basically what happens is, through Wi-Fi, I can connect to the router, and this router is already connected to the internet, because you have to subscribe to the internet to connect your home to the internet, right? You have to call AT&T or maybe British Telecom, and then they will provide you with the Wi-Fi router and the connection. They will send in a technician maybe, or a do-it-yourself kit, and then you fix it, put the username, passwords, all the stuff that they will send you, and you are connected to the internet, and now your computers can connect to the internet as well. Then we have wide area network. So a wide area network is a network that connects computers and networks over long distances. So it could be that I have a branch in New York and another branch in California, or the corporate in California, and I would like to connect them to each other. It could be across cities, it could be across states, across countries, or even across the globe. The WAN can connect many LANs together so people can communicate and share files and so on. And here's an example. If we have a company LAN branch in Germany, but the headquarters of the company is in the US, how can we connect them? One way would be to do a WAN connection between them, a high-speed WAN connection. Of course, it's going to be costly because this is across continents. And then the LAN in Germany and the headquarter LAN in the US can now be connected through that WAN. We're going to look at the details of what a LAN or network devices that can build a LAN and what network devices can build a WAN. And since we are talking about WAN, then what is the largest WAN in the world? And that is the internet. So this is our largest one in the world. So I can have someone in a home office in Japan and maybe a branch office that is in Germany, or a company that is in Germany, and they are all connected to the internet, and they can exchange data or access data that is hosted in the US, for example, in the corporate office. So this is the gigantic WAN that we have, and we are all using it and we are used to it. Now let's look at types of traffic flow. When we are talking about a network and I have devices connected, do they connect one-to-one or one-to-many or one-to-everyone? How do they communicate? What are the different ways to send traffic in a network? And there are three major types: unicast, multicast, and broadcast. There is another one called anycast, but it's not the time to talk about it now. So when we talk about unicast, what do we mean? If I want to connect to my bank account or online banking, that is one-to-one. I am talking to the bank server and I'm not sharing that data with anyone else. So this is one-to-one, as if Sarah and John are communicating with each other and they are separately in a meeting room and there is no one else. So that's one-to-one traffic between them. So the data goes from one device in the network to a specific device, from a client to a server, from an iPhone to the HR server, for example, in the company. Then we have multicast. Multicast means one to a group. So it could be that I have an IPTV server in a hospital, for example, and then the patients in the rooms, they can turn on their TVs. It could be a hotel as well. They can turn on in their TVs and I could be watching the same movie that you are watching and someone else is watching. So that would be one to many. That will be multicast or streamed to the others. And Netflix is an example of that as well. A broadcast, on the other hand, is one to all. Like if there is a PA system, think a PA system connected to the network in an airport. So when the message is presented or the message is run, now we're talking about British Airways flight number such and such is boarding now, and that is in gate such and such. Everyone who is within the reach of that audio system or a PA system will be able to hear it, right? So in networking, if one is sending a broadcast, that means everyone on that network is going to receive that traffic. Now let's talk about wired network devices. If I'm talking about a LAN or a WAN, what are common devices that I may come across when I am building a LAN or building a WAN or even investigating, troubleshooting, configuring, or even just looking at a design? What are the common devices that build a WAN or build a LAN? That's what we need to know now. So networking devices are needed to create LANs and WANs. So what are they? What is inside this little bubble here and what is inside that little cloud over there called a WAN? So the very first one that you may rarely encounter, because that's an old technology, is called a hub. So what's a hub? It's a network device that connects multiple computing devices in a LAN. So can I connect a printer? Yes. Can I connect a laptop? Yes. Can I connect a server? Yes. Can I connect a CCTV monitoring or surveillance camera? Yes, you can do all of that. But it is not intelligent. And here's an example of how a local area network, an inexpensive one, may look like. The disadvantages of a hub: it sends data to all connected devices. So it's like a broadcast. If any device sends, let's say this laptop is trying to print something to the printer. So the traffic that will be received by the hub is going to be sent on all ports of the hub. And these are ports that I'm talking about. These are the hub ports that we connect the devices to. If this is going to the printer, this should not have been sent here and should not have been sent here. So it wastes the bandwidth, it wastes the media, or it occupies the media of the network for unnecessary reasons, for devices that don't need to receive that traffic. And there is no filtering and there is no intelligence. It's just forwards traffic. That's it. All devices will share the same bandwidth. So these are major disadvantages of hubs. and it is lower and less secure as well. Another networking device type that we may encounter when we are building LANs is a switch. And that is an intelligent version of the hub. It is much faster and it is more intelligent and can do isolation as well. And here's an example of how a switch from a company called D-Link, for example, looks like. So this one has 8 times 3, so that's 24 ports. I have here LED indicators, LED indicators. When one of the ports is connected and there is traffic on it, it will be flashing lights showing that this is connected, and the light can be green, can be red, can be orange to indicate whether green means normal operation, orange means there might be some errors, red that means a major problem, or maybe it's just switched off so there is no connection into it. And as you can see, each one of these is called a port or an interface. So this is a switch port where we have the cable connect to. So these are 24 ports. That means I can connect physically 24 devices to this switch. So that's an example of how a switch in a LAN would look like. Now, if I take that and I start to connect the devices to it, so each one is going to connect through a physical cable. We're going to look at the details of the cables later on. And that occupies one port, that occupies a second port, third port, fourth port. So now I have 20 ports left for extra devices or for future connectivity. So a switch can be physical or virtual. So this is a physical switch, we can see it. And if it is in front of me, I can touch it as well. I can power it on. I can connect a cable into it. But there are also software switches. These are the virtual switches, and we're going to cover that as we move on. Advantages of switches compared to hubs: it will send data only to the intended device. So if we have the same scenario where this laptop would like to send traffic into this printer, the traffic is going to be switched only between this port and this port. So this will not see it and this will not see it, which means I am segmenting the bandwidth. It's not like one common bandwidth. So at the same time, this is sending to the printer. It could be that someone sitting on this device is displaying the video from the camera on this monitor, for example, and they're completely separate and they don't see each other. And it is faster and more secure because now we can do the isolation. It is intelligent as well. We can have security features configured, and each connection can use its full speed. If this port is 100 megabits per second or maybe 1 gigabits per second, so it has 1 gig speed into the switch. Similarly, the second, third, and fourth. And it can handle many devices more efficiently compared to hubs. One important feature when we talk about switches is something called virtual local area network, or a VLAN. What is that? So a switch can be configured. So we can configure the switch or virtualize the switch to have multiple isolated segments, multiple or completely isolated from one another. They cannot talk to each other. So separate segments, they are called virtual LANs or VLANs that can be used to group devices logically. So as we have discussed the concept of virtualization on a physical server level, that we can have virtual machines into that server, we also can have virtual LANs into the switch. And how can we do this? We can create VLANs, the different segments, let's say VLAN 10, VLAN 20, VLAN 30, for example. That's the ID of the VLAN. And then we map the switch port to VLAN 10 that we needed to connect to VLAN 10. So the devices that need to connect to VLAN 10, they are going to be configured, or their physical ports on the switch, they are going to be mapped into VLAN 10. Similarly for VLAN 20 and 30 and so on. Why would I do this? It could be that I need the accountants or the accounting team to be on a separate VLAN, and they can communicate with one another and with their server, but this is sensitive information. I don't want guests that will connect to the network to be able to communicate or maybe sniff or copy that traffic between the accountants for some reason. Okay, and that's how it will look like. So now I decided the 4 leftmost ports are going to be in VLAN. I'm just referencing here the color, but it could be VLAN 10. And the next 4 ports are going to be configured or mapped into VLAN, representing it as red, but this could be VLAN 200, for example. So any devices that will connect into the red ports or the red map ports will not be able to communicate with the ports that are in the blue or VLAN 10. They will never be able to communicate this way without extra configuration or extra devices. Advantages: this is better security. You can have isolation and segmentation into your LAN. And isolation also, that data will only go to the right VLAN. So if I send traffic from this device, it will only be with the basic configuration of only segmentation, only VLANs. It will only be able to communicate with other ports in the same VLAN. And that's it. It will never be able to get into the blue port VLANs unless I do something extra. Okay, so we talked about the hub, and we talked about the switch, and we talked about the fact that the switch can be segmented or configured to have isolated segments, isolated VLANs. Now let's talk about the third device that we may encounter when we are dealing with LANs and WANs as well, and that is the router or the router, however you would like to pronounce it. So the router will connect different networks together. Networks that are not the same, they will be connected together using a router or a group of routers. And these are some examples of physical routers and how they would look like. In essence, it looks like switch in terms of ports, but the device is a router. That means it has more intelligence than just a switch. And it can have bundled a switching function, but we'll talk about that next. So the router will know how to send data from one network to another. So that's the connection between separate networks. And the router, as the switch, can be also physical or it can be software, virtual. And here's an example. So we have the branch that was in Germany and the head office that was in the US. If I need to connect them, what do I need to do? So they will have to connect because they are far away from each other. This is a LAN and this is a LAN. They need to connect through routers, through the WAN. And the essence of the WAN is routers. So I have to procure a router at the Germany branch and another at the US branch. I need to connect each one of the routers to the local LAN. It cannot represent the LAN if it is not connected to it. Because when traffic will leave one of the devices and needs to get to the US, it has to pass through the router. And the only way is to have a physical connection from the router to the same segment or VLAN where this device is connected to. Then I need to talk to the service providers, AT&T for example, or Verizon Wireless or Bell Canada or whatever the company is, and I will ask them, okay, here's the address and here's the address in the US, and I would like to connect this address in Berlin or Germany, whatever the city is, and I want to connect it to the US, and this is the speed I want. You will sign some contracts, they will take some time, provide the connection, provide the configuration, and everything works. So the router can also be used within a LAN to connect the different VLANs. Remember when we mentioned 2 slides earlier that a VLAN is a completely isolated segment in a LAN from the other VLANs, right? What if there is a need for me to have one device from here, or maybe the monitor, watch the video streams that are coming from the camera? How can we do this? This is a network and this is a completely separate network. This is a segment and this is a completely separate segment. So the only way to do that is to do routing between them, because the router is the device that connects multiple LANs together. And how can we do this? The router must be connected to the different VLANs in order to be able to forward traffic between them. And how do we do this? I need to have separate interfaces on the router, connect to the different VLANs, and then I will configure the router here to be part of this network and the router here to be part of this network, and then the router will be able to forward traffic between the two when there is traffic to be sent across the two networks. As I mentioned earlier, there could be some switches that are intelligent and they have routing function, or it could be a router that has switching function. No matter how it is, these are called intelligent switches, or they could be routers with switch functions. Sometimes they are referenced as multi-layer switches. We are going to talk about where did the multi-layer come from, but for now, intelligent switch or a switch router combo or a multi-layer switch, they are all synonyms for the same thing. So the switch router combo device can do both switching and routing functions. And we signified the fact that this can do routing as well by the little icon on the switch. So in that case, if I need communication between this network and this network, I don't have to have an external router. A combo router here, that means there is a software function on the switch that can do routing as well. So if I configure that properly, I will be able to allow traffic from the red VLAN into the blue VLAN and the other way around. So no need for external routers to connect the different VLANs in this case. All right, so we learned about hubs, switches, VLANs in a switch, segmenting a switch, router, and now we learn about switch router combo. And please remember that a router connects different VLANs, not devices in the same VLAN. The switch connects the devices in the same VLAN, or it could be multiple VLANs. But a router connects the different VLANs or connects a LAN to another LAN through a WAN. So we learned about types of networks and network devices that we may encounter. So network cabling, how can I wire the router into the switch? How can I wire my CCTV camera into the switch? How can I use connectivity in the WAN? What type of cabling, physical cabling that I could use? Is it any cable? Can I just bring any wires and connect them? Or does it have to be of specific type? And what will be the end connectors that will connect into the devices? That's what we need to see right now. So network cables are physical wires used to connect computers, routers, switches, and other devices. They can carry electrical signals if they are copper cables, or they could be light signals if they are fiber optic cables. So let's start with the first one, which is the Ethernet cable or the copper cables. Also, we call it twisted pair or TP cables. They could be UTP, they could be STP, different names for them. These cables have standards, and they have standard connectors. Maybe you have come across them when you are connecting your TV, for example, to the wall in order to reach the internet. So this is called an RJ45 connector, RJ45. So that's the standard name for this connector. It has 8 pins, 8 copper pins, and the cable has 8 wires. They are twisted pairs, and that's why it's called a twisted pair. Each 2 wires are twisted together in a pair. So we have 4 pairs, and then we have the little pin right here, which latches into the switch port. So if you look at the pin, and here you will find that there is a groove on the top of the port. So there is a wide rectangle, and then there is a small rectangle. This is where the pin will latch, and the wires on this side are going to touch on wires on this side in the switch, and that's how it connects into the switch. So this is used in most homes and offices, short distances, not long distances. And common cable types are Cat5e, enhanced Cat5 or Cat6, and Cat6a. Depending on which one, it can go for higher speeds, and the distance is usually limited. We're talking about 100 meters or 90 meters, depending on who you talk to. Okay, and it can carry speeds from 100 megabits per second to 10 gigabits per second. It could be, with the new technologies and all that, could be even higher speeds, but it's usually limited in distance. And the data on the cable, the actual traffic, is represented as electrical signals. So either there is a voltage or there is no voltage, 1, 0. That's it. We're going to come into that later on. So maximum length is around 100 meters. Some people will tell you 100, some people will tell you 90, but it's very limited distance as we speak. The second common cable type that we use in our LANs and WANs is the fiber optic cable. Fiber optic cables carry light signals, and they can go for long distance connections. Believe it or not, the internet has underwater, undersea, and under ocean cables to connect the continents together for the internet. These cables are sturdy, they are very rugged and very protected, so there's no water leakage, and it's not easy for a fish to cut them and all that. And when any incident happens that one of these cables is cut, you will find a lot of countries suffering if they are dependent on that cable. So when do we use them? We use them when we need long distances and higher speeds that cannot be achieved using the copper cables or the twisted pair cable. And they convey the data, they encode the data, they represent the traffic in light signals and not in electrical signals. And they are much faster than Ethernet and can travel longer distances, and often used by internet service providers and data centers, and also they are used commonly in WANs, wide area networks. Now let's talk about data center network, or DCN. So the data center network, abbreviated DCN, it's a type of a local area network that will connect the servers, storage systems, and networking equipment inside a data center. So they can communicate and they can serve traffic and they can connect to the internet at a very high speed. So it is very common to use fiber cables within a data center and not UTP cables. The UTP cables can be used at the end with the servers. That is possible. But fiber is much higher speed, and especially for the important servers and so on. And as you can see, the data center switch, it has similar ports like in the normal switches, but the capacity is much higher. The ability to process, so the CPU and the memory and all that, are much higher as well. It usually has multiple power supplies and usually has multiple processor engines as well. So it can have more availability, and one failure in a component will not bring the switch down. A data center may have lots of these switches. I'm here just representing one switch, but it can have 8, 10, 16, 20, depending on the scale of a data center. And the data centers usually will have one or more internet connections for diversity and high availability. So one or more routers are going to connect to the different switches into the data center, and that's how they can serve traffic to the internet. So if I have multiples, that means if one of them dies, the other one is available. And that's called high availability or redundancy. All right, so we learned about LANs and we learned about data centers. What if I need to connect a LAN into a data center? So for example, the corporate office exists in a building, and adjacent to it, we have another building that is the data center of that bank or that corporate. So in that case, if the LAN that I would like to connect is close in a closer vicinity, 10 meters, 20 meters, 1 kilometer, 500 meters, but not 500 miles away, it is a very close, then what we can do is we can use a fiber cable, we call it an uplink, from the switch into the data center switch. That is, of course, if this switch is capable of providing fiber optic cables. Here we are only representing a port, but if we use copper cables, these are UTP copper ports. So if I use a copper cable, that will be only 100 meters away or less. But if I want longer distance, 1 kilometer, 2 kilometers, 5 kilometers, then I can use fiber uplinks. And of course, I can use multiple ones for redundancy. So if one fails, the other one will still be available. And through this uplink, now this LAN can connect or share the internet connection that is available in the data center. So that's how we can consolidate one internet connection, high speed, in the data center, and then all the scattered buildings nearby, they can use to route or to use the internet, instead of having an internet connection out of each building. What if the LAN that I need to connect to the data center is far away? It is 200 miles away, 500 miles away, in a different country. Then in that case, I have to rely on the WAN, wide area network, not the uplinks. So in that case, I need to get a router connected to this switch and then talk to the service provider to have a wide area network connection served here and another wide area network connection served in the data center, and then proper configuration is done, and that is how they can communicate. And of course, the same. If I want to have a central internet connection, then through the router, through the other router, the LAN can be using the internet connection. A corporate or a bank has two big data centers and would like to have some backups between them. Copies of the data will be sent between them. So if you lose one, the other one will have the data available, or the applications available, or the websites available. So how can I interconnect two data centers? And in that case, it depends on whether they are in a close by vicinity or far away from each other. But the common one is that we connect them through routers. That is more common, although connecting them through switches is possible as well. But if we connect them through routers, then what we'll do is, again, we need a larger size router that can perform much better under load, and it can provide higher speeds, and then the WAN connection, and that's how they connect to the two sites. And each one of the data centers can have a separate internet connection. So if we lose one of the data centers or one of the connections, the LANs connected, they will be interconnected to this one and to that one. So the LAN or one of the branches, if I lose one data center connection or I lose the switch in the data center, then they can reach the other data center through this connection instead. All right, so routers can help me connect data centers, not only connect wide area network branches and local area networks only. The other type of networks that we need to talk about is called campus area network. And as the word implies, campus, so multiple buildings close to each other. It could be a university, it could be a hospital, it could be a ministry. Multiple buildings nearby, they can be connected through campus or a CAN, campus area network or a CAN. And here's an example. I have a data center, and nearby could be 500 meters away, I have building B, and maybe 1 kilometer away, I have building A. And I have a LAN inside each one of these. And I could have also wireless LAN and a LAN in one of the buildings. So in that case, and I have the switches connecting all the devices. So within a building, we are fine. We can connect and we can share and we can print and everything. Within the other building, yes, we can do that as well. But we need to connect to our servers or website or human resources department servers on the internet. Or maybe we need to connect to the internet, generally speaking. Then, in that case, if the decision was made to connect the data center to the internet, and have common internet connection for all of them, then we can connect them using uplinks. And this will be fiber optic because they can go higher speeds and longer distances, not copper cables in that case, or UTP cables. All right, so that's a CAN. So it's a private high-speed network that links several buildings on one campus or a limited area, like a university, hospital, or company campus. Of course, there is MAN as well, metropolitan area network, and so on, but it is enough. We learned about LAN, wireless LAN, WAN, and CAN, and that is more than enough for our purpose of this course. Since we talked about the wired parts, let's now talk about the wireless network devices. So what devices that are wireless that we may encounter as we build networks? So wireless network devices are needed to create wireless LANs. And as we looked at the example in the home office, I need a wireless device that will broadcast the wireless LAN and will also be able to authenticate or basically check the user name and the password when they log in to the wireless network. The first device that we need to talk about is called a WAP, or a wireless access point. A wireless access point is a device that provides Wi-Fi signals, broadcasts Wi-Fi or broadcasts wireless LANs into a certain coverage area. For example, at an airport or in a school. And if the area is large, then I may need more than one WAP. One will not be enough. And this is how they look like. Maybe when you are walking down your company or street or school or shopping mall, look at the ceiling, look at the walls, you'll find devices similar to these. These are the wireless access points. In the outside, in the outdoors, they have to be rugged and they have to be industrial grade, and that's how they look different on the outdoors. A WAP or a wireless access point is not a router, not necessarily a router. It doesn't have routing function. It only broadcasts the actual wireless signals and then it connects through a cable into the LAN. So here's a wireless access point. It will broadcast a signal, and that's how devices will connect into the wireless LAN. But is that it? How can I connect to the internet? How can I connect to the actual network? Let's find out. So a WAP extends your network. It doesn't create a new one. So when it creates a wireless LAN, the wireless access point itself has to connect into your network. At the end of the day, what you need in your device is not to connect to the WAP. You need to be hooked into the wireless access, and then from there you would like to get to the internet. So there has to be a LAN backing the wireless network, and it will have a wired connection into that switch. In larger offices, we will also need multiple wireless access points because the coverage area is larger and one WAP is not enough. All right, so now we have multiple devices, maybe wing A and wing B in the building. So wing A will have one or more access points to cover all the area and provide strong signal. And also for wing B will have one or more depending on the size of the building. So we have that connected to the LAN. And then how can we get to the internet? That means we have to have a routing function or a routing device connected to the internet and to the switch in the same VLAN as that connection in order to be able to provide wireless and then wired connection for the traffic to go out to the internet. One would jump now and say, okay, now, but I don't have that in my home, and I don't have that in my home. I only have one device and my network is connected to it and everything works fine. I would say yes, absolutely, because that's a special case and this is how it looks like. But then you need not a wireless access point only, but you need a device that can do wireless access point function and routing or routing function as well. So it would look something like this, or maybe something like this. And most of them, they would have a switch built in as well. So that would, the backside would look something like this. So go check your wireless router right now that you have at your home, and you will find that it may have antennas. The modern types, they don't have antennas, they have it built in. And you will have at least 2 or more ports of connection or physical connections that can hook to the network. So in that case, what happens? You will have one port that will be connected to the service provider. Usually it is a special port, and you will have either internet or WAN written on that. And then you will have this, because if I have a printer, the printer needs a wired connection, not a wireless connection. In this case, we can take advantage of the back ports for wired connections. So it will serve the wired connection requirements and the wireless through the antennas, and that connects to the internet. So this is a Wi-Fi access point that has a routing function as well, and it will have a built-in mini switch to connect the wired devices. So hopefully that's clear. Now we know about hubs, we know about switches, and we know about virtualizing a switch into multiple switches or mini switches called VLANs. And then we learned about routers, and routers connect different networks, and we learned about data center network, and now we learned also about network devices that are wireless, like wireless access point or wireless routers. All right, hopefully that was clear and easy to understand. Let's zoom into or have a closer look into the internet. The internet consists of millions of local area networks, data centers, home offices and homes, and wide area networks connected through routers and high-speed links, creating one global network. That's what the internet is. So I may have a corporate data center in India, and we have the data center switches, we have the router, and it's connected to the internet, and I have databases and applications and storage and so on. Maybe I have a branch in Germany that needs to connect to the data center. So the corporate data center is in India, but the company has a branch in Germany. So I have a LAN in Germany and maybe a wireless LAN as well. I need to connect it to the data center. How can I do it? Have a router connected to the internet. So there was a possibility to connect it through WAN that we talked about previously, but also we can connect it through the internet. How can we make it secure? We'll talk about that later on. And maybe also one of the employees works in the UK in a home office, and they need, or he needs, or she needs to connect through the internet also to the data center. So that's all possible, and that's what the internet does, the largest global network or global WAN in the world. So a closer look into that. What does the internet consists of? So as we mentioned, we have home-based users, we have separate users in a library, we have data centers in other places, and that is routers connected via very high-speed links, and that is what actually forms the internet. So high-speed connections interconnecting tens of millions maybe of routers across the globe, and that is what the internet is, that everyone connects to. And once you are connected to the internet, you can communicate with the rest of the internet. All right, it's time to start Module 5, and this will be about first steps into diving deep into networking fundamentals. So understanding more about the networks, and the first thing we need to understand is why do we need IP addresses and how do they look like and how can we deal with them. And by the end of this module, you will be able not only to spot IP addresses and recognize them and identify the different networks, but also you'll be able to be given a block of IP addresses and design according to requirements an IP scheme breaking down that block into multiple networks and subnetworks and assigning them to WANs and LANs and so on. So we are going to cover what are IP addresses and why do we need them, and how do they look like. Numbering systems, we'll get into a little bit of math. I will make it super easy. I promise you, I know a lot of you hate math, but I'm going to give you the analogies where it will make it a lot more easier, because you need to understand how computers can comprehend IP addresses and how can distinguish a local IP address from a remote IP address and then send the traffic to the router or not, depending on where it is. So we'll talk about decimal, which is the numbering system we all know, the 10, 20, 15, 32. This is what we are used to. But also we'll introduce how computers deal with numbers and text and data, which is binary. And we are going to show you how you can convert from decimal to binary, from binary to decimal. We'll look at the IP address types. There are two versions, IPv4 and IPv6. We'll look at what are the differences between them. We'll also look at hosts and networks. How can we assign to the servers on a specific network IP addresses, and how can I tell whether they belong to the same network or to different networks? We'll look at something called the subnet mask, and we'll do a lot of practice on that. We'll look at the IP address classes. We have class A, B, and C. We'll look at them, and you will be able to distinguish between the different classes when you see an IP address. I will show you how to break down a range or a block of IP addresses the easy way using online tools. And also, we are going to show you the detailed way of how you can do it if you would like to practice doing that. And of course, those of you who are going to dive deeper into networking, they should be able to understand how that is broken down and how it works and how to calculate them and all that stuff. So that will be the IP subnetting in details. And then I'm going to provide you with a table that has subnets ready for your use if you would like to train without going into all that hassle every time, calculating what the subnets are and all that. So these are going to be handy anytime you'd like to create networks in the cloud and practice on them. We'll look also at what are public IP addresses and how do they relate to the internet, and what are private IP addresses. So we have a very long module ahead of us, but very interesting, and I'll make it super easy, I promise. So please hang in there. Networking fundamentals are very key to any engineering role in the recent or the modern IT. And also, if you would like to build networks as a developer and you start launching your application and databases and different apps and put security in between, then you need to know also all these IP addresses thing. And this is where a lot of people get stuck in getting into cloud and getting into IT, because they would say, this is above my head, I can't understand it, it involves math. No, not for me. Stay with me, and I promise you that it will be super easy by the end. I will make it super easy, all right? The first thing we're going to look at will be the IP addressing and why do we need it. Let's look at analogies from our life and find out if that is relevant or it makes sense or it doesn't make sense. How can people communicate? It's very easy. Even if I don't know you and you don't know me, I can smile and say hi, and you're going to say hi back, and I'm going to ask you, what do you do here? How's your coffee? How's your day? This and that. And then we start and we get to know each other, maybe introduce our names and maybe phone numbers later on, and then probably a friendship starts or something. And we use names to distinguish each other. So if we have a group of people standing in a park, for example, then George and Ahmed and Sarah and Layla and Sneha, they can be in a classroom, they can be in a hospital, in a match. And if they know each other, they can call each other by name. Or if they have badges, I'm going to read the badge that you have, and then I'm going to call you by your name. Same thing for mobile phones. Each one has a unique number, and that number is not used by anyone else in the globe. If the number is the same, the country code will be different and the area code will be different. So numbers can repeat, but not the area code and the country code. So globally, there are no two people using the same phone number if you add the country code and the area code. Why do we have unique numbers? Because when I'm calling you, if you don't have a unique number, I'm going to call the wrong person, or maybe multiple people will pick up the phone. But I want to reach you and nobody else. If I would like to call Sarah Joan, for example, this is her number on my phone, and I'm going to push the screen or click on the screen on that one, and it will start calling Sarah. Same thing, Sarah has my number and my phone number and my name. So as soon as the phone rings, she will look and she will sign Ahmed Eid is calling. And depends on how important the call, if she's available, if she's free, and if she's in a meeting, she will just mute it and call Ahmed back later on. So each user of a mobile phone has a unique number as well. Individuals have mailing addresses, and that's how they receive Amazon deliveries and food deliveries and so on. So John Smith lives in 32 University Street in Boston, Massachusetts, and that's the zip code, and it is a house. Similarly, Sarah Halim, she lives in 122 Maidan Street, Dokki in Cairo in Egypt. She has a postal or a PO box, and she lives in a house as well. So street number is enough to deliver the package to the house. That's more than enough. So if John Smith from the US would like to send something to Sarah, then he will write to, so that's the recipient, the other party, and the details of the address of Sarah. And then from, who is the sender, so that is John Smith, and of course there will be a stamp, and that will be sent through United States Postal Service. It will get to Sarah eventually, and it will be delivered using the Egyptian post to her address. She will read the letter, and then maybe she will respond and send it back. The same thing applies to email addresses. I send you an email, you know who sent it to you, and then you reply to my email address. So if Sarah would like to respond to John through a letter in an envelope, then she will be the sender and he will be the receiver. And again, the postal services, if the address is correct, they will be able to deliver it back. So this is all human being stuff, and it's very common to all of us. Now the question is, if I have a desktop connected to the internet in Germany and another one in Brazil, and I have a mobile phone user in Egypt connected to the internet and a laptop user with a browser in India, how can they all get to Amazon.com? They want to buy stuff from Amazon.com. They would like to get into the e-commerce website of Amazon, and then each one of them is going to look at the products and then decide what to buy. How can we ensure that the internet will not be confused, that if this guy will communicate with Amazon and they are looking at watches, the response will not go by mistake into the user in India or maybe the user in Egypt? And if the user in Brazil is looking at soccer balls, how do we ensure that the response will be addressed properly to the right place? That means we need unique addresses for anything connected to the internet, and that is called an IP address, an Internet Protocol address. So if we take one of these users that would like to get into Dolphin Ed Academy, which is hosted on the internet on a server, then how can they approach or address the request sent to the website to sign in? And how would the server know who is the sender so they can respond to the correct user and provide the sign-in page? So we need an address. We need a client address, and we need a Dolphin Ed Academy server address. Who is going to do the connection between them two? Because they are different networks, and this could be in the US and the user could be in Egypt. So that means we have to have routing, because the only way we learned that we can connect two different networks is through routers. So we have to have routing functionality in between, at least one in the internet. And we said that the internet is a gigantic number of routers or routers connected together with high-speed links, right? So what is the name of that address? What's the name of this address? And these are called IP addresses. And why are they called IP? Because it stands for Internet Protocol, which is a set of rules that are standardized globally that govern how data is sent and received over the internet or any other network. There used to be other protocols for other ways to build networks, but now IP is the predominant one. So think of the Internet Protocol as the postal system on the internet or any other network, whether it is in a data center, on a local area network, or a wireless LAN. So now the IP address, or the address of the client, is called the client IP address, and that of the server is called the server IP address. And the routing function is called IP routing as well, because now we are speaking a common global language on the internet called Internet Protocol, the IP language. So if we extend that and give an example, then the IP will define IP address blocks of which IP addresses they will get assigned to each device. And if you are on the internet like the phone system, it has to be a unique IP address to define you on the internet. It has to be. There is no budging on this. It can't be that my home wireless LAN and your home wireless LAN are using exactly the same internet IP address. There is no way this will happen. And we are going to get into how this is guaranteed. Okay, so we need the client IP address and we need the IP routing. So IP protocol as well will define how routing can happen and how routers function and how they understand messages and how they can forward them. So all of this is within the IP realm of protocols or functionalities. The messages sent from me to the server and from the server responses to me, they are called IP packets. Now let's look at the format of the IP addresses. How would an IP address look like? If we extend that into the client-server web application that we have looked at, then we need an IP address on the client side. Here's an example. This is how it looks like. A number dot a number dot a number dot a number. And we need the IP routing functionality here, and this could be the IP address on the server. Just examples. So the client, no matter what, must have an IP address, and the server you are trying to get to must have an IP address as well. How can we define or find the device IP address that we are using? How can I confirm that I have an IP address on my computer, for example? Then if you are using a Windows laptop or a Windows device, then you can open the command CMD, go in the search bar at the bottom, and then click CMD, type CMD and click. A black window will open, and then you can go and do ipconfig. That's it. So you will have a prompt like this, and then you just type ipconfig and hit enter. You will get the IP configuration on your machine, and you will get either the wired or the wireless will have an IP address for you. If this was on a Linux or a Mac OS device, you can use the IPA command. That is possible. Maybe it will work. If it's not installed, the IP utility on your laptop or on your Mac or on your Linux, you can use a different command like the ipconfig get interface address en0. And let me show you that on my Mac to prove that I have an IP address. So here's my terminal, and what I will do is I'm going to do ipconfig get if address, and that is en0, and you'll find that it has an IP address as you can see here. So 192.168.68.108. So that is a number dot a number dot a number dot a number, and that's how an IP address looks like. So use ipconfig, enter if you are on Windows after you open the CMD, the command, and you will see that. And if you are on Linux, try this and try this. One of them should work. So the IP address available versions are IPv4 and IPv6. The IPv4 is easy to understand when you look at it. It is 32 bits long. We're going to talk about what a bit means very soon in the next slides. And it is 4 fields separated by dot, as you can see here. So 120 dot, 130 dot, 233 dot, and then 12. It requires a subnet mask. We are going to talk about what that is. Can have public or private ranges. We are also going to cover that later on. The IPv6 is written or represented in hexadecimal notation. So you might see letters, A to F, and you might see numbers as well. It's 128 bits long, 8 fields, and an example is a number colon, number colon, number colon, and as I mentioned, you can see numbers and you can see A to F symbols as well. And it requires a subnet mask as well, and can have public or private ranges as well. So how can computers read IP addresses? How can the computer or my device or my phone be able to read this IP and to make sense of it, or read that IP and make sense of it. How is that possible? How can we allow computers and computing devices to read this IP address and recognize them and find out which networks they reside on and what are the host identity on that network? This is very important, and that's why we will a little bit get into some simple math to explain to you how is that represented inside the computer, because the computer does not have eyes to speak or read English and find out the decimal and the hexadecimal and other representation. Everything inside the computer is binary numbering system. So we need to understand it at a high level to be able to break down IP addresses and explain to you how that happens in a computer. All right, now let's introduce a little bit of simple math, and we are going to compare that to the decimal numbering system that we all know and deal with every day when we pay money, when we calculate the change and all that, because we need to understand how do computing devices understand IP addresses and how can they tell if an IP address belongs to their local network or needs to communicate with an external network or another network. So to do that, let's refresh our knowledge about the decimal numbering system. Several numbering systems exist. We are used to the decimal one, the one that has the symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And any number that we use today consists of a combination of these digits, we call them, or these symbols. And there are 10 symbols, and that's why we call them decimal, because it has 5 and then another 5. So from 0 to 9, including 0, are 10 symbols, not 9 symbols. Computing devices, they use the binary numbering system internally. And this has only 2 symbols. That's why it's called binary, the 0 and the 1. There also exists other numbering system. And as an example, the hexadecimal. Hexadecimal means 16. Hex is 16. And has 16 symbols. And they start from 0 all the way to 9. And then A, B, C, D, E, F. So from 0 to 9 is 10. And then 2, 4, 6. That's why it's 16. Example, if we have a number 521, that is decimal. Can we represent that in binary? Of course we can. And that will be the representation because we can only use 0 and 1 in binary. And in hex, it will look something like this. 0x, which means hexadecimal, and then 209. Don't worry about the conversion. If you would like to use your calculator to confirm this, that's fine. But we are going to explain the binary. We are not going to explain the hexadecimal in this course. Computing devices use binary numbering systems internally. Even your calculator, even if it is a handheld calculator, and you are typing numbers and doing mathematical equations, internally within the calculator, it's zeros and ones. It's converted into binary and represented as binary within the calculator. And that is true for your phone, for your laptop, for your iPad, for your computer, and so on. Decimal numbering system, when we have a number like this, how do we pronounce it? We don't say 345, we say 345. Why did we say about the 300? And why did we say about the 40? As if we are multiplying by 10, and here we are multiplying by 100, and this is only 5, 345. This is because depending on where the digit sits, where it is located in the combination of symbols, that has a weight. Each position has a weight. And this is something we all know. So let's say if I'm looking from the right-hand side on the first, second, third, and fourth positions, we know that the first one is called the units, and this is the tens, and this is the hundreds, and this is the thousands, and so on. And why do we call them like that? Because any number that exists in the first position, its weight is multiplied by 1, and that will be the weight of the position itself. Then we have the second position, which is tens, and that is 10 times 1. The hundreds is 10 times 10 or 100. That's the weight. And then the thousands is 10 times 10 times 10, which is 1,000. So if we have the number 345, the reason is this is in the hundreds position. So it is not 3, it is 300, 3 times the weight. Here it is 4 times the weight, that's why it's 40. And here it is 5 times 1, and that's why it's only 5. And if we have a number like this, we would call it, or we would spell it as 5,394, exactly because of the same reason. It's 5 times the weight of the fourth position, and 3 times the weight of the third position, 9 times the weight of the second position, and then 4 times the weight of the first position. And that's exactly how it looks. And the position weight is how it is written in this row. And if we multiply these, we can get each digit what it is exactly. And then if we combine these, we get the total number. So it's 5,394. So this is how it looks in decimal. How is it in binary? Let's consider that next. Right, let's now have a brief overview of the binary numbering system. And I promise you it is easy to understand, so don't freak out. The binary numbering system has only 2 symbols, the 0 and the 1. Each digit in binary number is called a binary digit or bit. Remember when we said that the IPv4 or the IP address is 32-bit long? So we call it in decimal digit only. Here we say it's binary digit abbreviated a bit. So when we say a digit, we are talking about decimal. When we say a bit, we are talking about binary. For example, this long number or long binary string is a representation of 521. Let's look at something called exponents. That's also in math, we use it. And this is a shortcut for repeated multiplication. We use it a lot in binary, and that's why we are bringing that in here. So for example, if we multiply 2 times 2, that's 4 times 2 is 8 times 2 is 16. Okay, so this is a 2 multiplied by itself 4 times, and that's the 16. Is there a way we can shortcut, or we can represent this in a shorter form? And the answer is absolutely, we can do this. And it is, the base is 2, and the number of times it's multiplied by itself is the exponent. So this is the base, and this is the exponent. All right, and it's pronounced 2 to the power 4. And it can also be written like this, 2 control 4, and that means 2 to the power 4. That means 2 times 2 times 2 times 2. If I say 3 to the power 2 means what? 3 times 3. 3 to the power 5, that means 3 times 3 times 3 times 3 times 3, 5 times. Any number to the power 0 is 1. So 2 to the power 0 is 1. 10 to the power 0 is 1. But we are going to focus on binary again. So what about the weight of the position when it comes to binary? So as in the decimal system, each bit position in binary has a weight. As we spoke about the tens and the units, tens, hundreds, and thousands, here it doesn't spell like tens or hundreds or anything because we don't have 10. We have only 0 and 1. So let's look at the first position, the first on the right hand side. So the first position's weight is 1. The second position is weight is 2 times 1, which is 2. And guess what will be the third one? It will be 2 times 2, because in decimal we did 1 and then 10 times 1 and then 10 times 10 and then 10 times 10 times 10 for the thousands and so on. Here it's exactly the same, but we replace the 10 by 2. So 1 times 1 is 1, that's the weight of this position. 2 times 1 is 2, that's the weight of this position. 2 times 2 is 4, and that's the weight of this position. Guess what will be the next one? Yes, 2 times 2 times 2, which is 8. And then 2 times 2 times 2 times 2, which is 16. And then 2 to the power 5, which is 5 times. That's 32, 64, 128, 256, 512, 1024, and so on. We are only going to focus on 8 bits long strings, because the IPv4 address or the IP address has 4 8-bit numbers. So let's go ahead and look at how we can convert decimal numbers into binary. And all of these strings are going to be 8 bits long. So we're not going to go to 7 or 9. We're going to stick to 8 all the time. because it is relevant to the IP address discussion that we are going to do next. So if I would like to represent the decimal number 0 in an 8-bit string, well, it's obvious. That will be all zeros because I can't take the weight in any one of the positions. If you put 1 in any one of these positions, you have to account for its weight in the result. And 0 has to be all zeros. How about 1? We start from the rightmost position, and then that will be a 1, and else is going to be zeros. Which means that is the weight is 1, 1 times 1 is 1, so it's exactly the same. 2, that will be 0 in the first position, and then I'm going to put a 1 in the second position. Why? Because the weight here is 2, and I want a 2. What if I want a 3? What if I want to convert 3? So I'm going to take the 2 and the 1 with me. What if I want to represent 4? This one cannot help me. This one cannot help me. The third one, the weight is 4, so that's why I'll take it. Remember that the weights are 1, 2, 4, 8, 16, and so on. 5, that means 4 plus 1. 6, that means 4 plus 2. 7, that means 4 plus 2 plus 1. The weight here is 4, the weight here is 2, the weight here is 1. If I add 1 plus 2 plus 4, that is 7. 8. That is 0, 0, 0, and then the weight in the fourth position is 8. So I'm going to put a 1 there. 9, it is going to be 8 plus 1. 10, it's going to be 8 plus 2. 11, that will be 8 plus 2 plus 1. 12, that will be 8 plus 4. And so on. So I think you get the point, and that is how it works. So 16, for example. 16 means I'm going to get the position that has 16 within that number, and then the rest is zeros on the left and on the right. Let's pick another number. Let's pick, for example, 31. 31 means 16 plus 8, that is 24, plus 4, that is 28, plus 2, that is 30, and plus 1, that is 31. If I need to shift to 32, the next number, that means I cannot have zeros in the very first 5 positions, and then I'm going to put a 1 in the position where its weight is 32. 33, that means 32 plus 1. And so on until we get to 63. 63 means 32 plus, this has a mistake here, so it should be 1. So it's 32 plus 16 plus 8 plus 4 plus 2 plus 1. So that's 48 plus 8, that is 56. 56 plus 4 is 60, and then 62, 63. Okay? And afterwards, if I would like to get to 64, then I have to zero all these ones because I'm going to take the position that has a weight of 64. What if I want 127? What do you think the equivalent numbers are going to be? Can I take the 8th position? And the answer is no, I cannot. Why? Because the weight is 128, and that's larger than the number I want. And then the next one, 64, I'm going to take it. Why? Because it's less than 127. 32, the next one, 32 plus 64 is 96, so that's less than 27. And what's the next one? That is going to be 16. 16 plus 96 is 112, so it's still less than 127. What about the next one? The next one is going to be 8. So 112 plus 8 is 120, so I'm going to take it with me. How about the next one? The next one is 4, so that's 124. What are we missing? We are missing the 2 and the 1. So 7 ones are going to give me the 127. What will be the 128? That will be 1 and then 0, 0, 0, 0, 0, 0, 0. How did I get to that? Because the weight here on the 8th position is 128. And that means I don't need anything else. We are going to practice a lot on this one, and we are going to be proficient as we get to it. So that's 127, 128. How about 192? 192 is, if you think about it, that is 128 plus 64. If you do the math, you'll find exactly these are what you need, and then you don't need anything else because you have already reached the decimal equivalent that you want. How about if we put all ones in an 8-bit string? What will be the equivalent? The equivalent is going to be 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. If you combine all of these, you will end up with 255. So the largest number you can have in an 8-bits string is 255. And the lowest number is all zeros, which will give you 0. So the range is from 0 to 255 when it comes to an 8-bits string. And these are 256 different numbers. One would tell me, no, hold on. This is 255 only. I would say, no, that's incorrect. Let's take a simpler example. If it is 0, 1, 2, 3, how many symbols do you have? How many numbers do you have? You have 4, although you are starting from 0. Similarly, if I start at 0 and end at 255, that means I have 256 different numbers that I can represent by an 8 bits string in binary. How about if it is only 2 bits, 2 positions? How many can you represent? Let's see. It's 0, 0, 0, 1, that's a different number. 1, 0 is a different combination, and then 1, 1. So that means in 2 bits, I can represent 4 different numbers. And these are 0, 1, 2, and 3 in decimal. We're going to practice a lot more on this, so we are going to be familiar with it. All right, so let's do binary to decimal practice. Let's do more examples, and these are going to be random, and I will show you the table of the weights, so it will be much easier to decide on this. All right, so what if I forget the numbers? I forgot the bit positions. How can I find it? The first one is 1. Remember that, and then any other one is 2 to the power 1. So here, 2 to the power, I'm sorry, n, not 1. And n is the bit position. So this is the second. So this is the second position. That means 2 times 1, it's 2. This is the third position. So you need to multiply 2 twice. So that is 2 to the power 2, which is 4. This will be 2 to the power 3. So 2 times 2 times 2, that's 8. And then 4, 16, 32, 64, 128. And we will always deal with 8 bits long symbols or strings. And that's what relates to the IP addresses that we are going to discuss. So for networking, for cybersecurity, for development, for cloud, for anything, all you need to know in binary is the 8-bit string conversion, and you will be good to go. So here is a practice. Find the equivalent in decimal for the following binary. So this is the rightmost. So this is position 1, and this is position 8. So the weight here is 128. And then 64, 32, 16, and so on. So let's put it in a table. It will be easier for us to remember it. So we need to map this binary into this weights and positions. So this one is going to map to the rightmost, and this one is going to map to the leftmost. So let's write it in a cleaner way. So it is 0, 0, 1, 1, 0, 0, 1, 1, and then all zeros. We need to look at the positions where the binary or the bit is equivalent to 1, and we take the corresponding weights, add them together, and that will be the result. So here I only have 2 ones in the 4 position and in the 8 position. So 8 plus 4 is 12. That's the equivalent to this number. Let's do another one. Here is another one, 0, 1, 1, 0, and 1, 1, 0, 0. So let's map that to our table. And that will be a 1 in the 3rd position, 4th position, and then 6th and 7th positions. So I have 1, 1, and 1, and 1. So what are the corresponding weights? 4, 8, 32, and 64. Why I will not take the 128? Because the corresponding bit is 0. 0 times anything is 0. Similarly, 0 times anything is 0. 0 times anything is 0. 0 times anything is 0. That's why I just ignore them. So I need to add 64 plus 32 plus 8 plus 4. So these are 96 and these are 12. 96 plus 12, that will be 108. Another example. What if I have this binary string 10011100? Again, this table should be implanted somehow, or it should be stored in your mind after you practice a little bit. So here is what we have. We have 1001 and then 1100. So what are the corresponding weights that we need to add? 8 and 4 and 16 and 128. So this does not count, this does not count, and this does not count, and this does not count. So 128 plus 16, that is 144. Plus 4, that is 148. Plus 8, that is 156. All right? You can use the calculator if you would like to make it easier for you. I like to do the mind math, but it's up to you. Here is another one, 10100011. So here's our table, and here's the mapping. So 1010. So this is with us, and this is with us as well. And then 11 at the end, and all the others are ignored. So we ignore these completely. 128 plus 32, so that is going to be 160. Plus 3, that's 163. Next one, 11001100. Although they look the same, but because of the bit positions, they will have different, like these 4 are going to weigh much heavier than these 4 because of their positions. So if we look at this and then we map our table, then we have this one is in, this one is in, and then we have this one is in, and this one is in. And you can see the weight of a 1 here is 4, and the weight of a 1 here is 64. The weight of the leftmost one here is 128, whereas this one is only 8. So that is 12, and then we have 192, that is 204. So hopefully that is easy to understand and do. Always write down this table if you are not sure about the weights, and the rule is very simple. Wherever you have 0, ignore the corresponding weight. Wherever you have 1, you need to add the weight or the corresponding weight to all the other weights that are accounted for, and that is how you get the decimal equivalent. Hopefully that is easy, and hopefully you are not bored. I promised you that it's going to be simple, and that's the hardest it will get, so don't worry about it. All right, so let's do binary to decimal practice. Let's do more examples, and these are going to be random, and I will show you the table of the weights, so it will be much easier to decide on this. All right, so what if I forget the numbers? I forgot the bit positions. How can I find it? The first one is 1. Remember that, and then any other one is 2 to the power 1. So here, 2 to the power, I'm sorry, n, not 1. And n is the bit position. So this is the second position. That means 2 times 1, it's 2. This is the third position. So you need to multiply 2 twice. So that is 2 to the power 2, which is 4. This will be 2 to the power 3. So 2 times 2 times 2, that's 8. And then 4, 16, 32, 64, 128. And we will always deal with 8 bits long symbols or strings, and that's what relates to the IP addresses that we are going to discuss. So for networking, for cybersecurity, for development, for cloud, for anything, all you need to know in binary is the 8-bit string conversion, and you will be good to go. So here is a practice. Find the equivalent in decimal for the following binary. So this is the rightmost. So this is position 1, and this is position 8. So the weight here is 128. And then 64, 32, 16, and so on. So let's put it in a table. It will be easier for us to remember it. So we need to map this binary into this weights and positions. So this one is going to map to the rightmost, and this one is going to map to the leftmost. So let's write it in a cleaner way. So it is 0011, 0011, and then all zeros. We need to look at the positions where the binary or the bit is equivalent to 1, and we take the corresponding weights, add them together, and that will be the result. So here I only have 2 ones in the 4 position and in the 8 position. So 8 plus 4 is 12. That's the equivalent to this number. Let's do another one. Here is another one, 0110 and 1100. So let's map that to our table. And that will be a 1 in the 3rd position, 4th position, and then 6th and 7th positions. So I have 1, 1, and 1, and 1. So what are the corresponding weights? 4, 8, 32, and 64. Why I will not take the 128? Because the corresponding bit is 0. 0 times anything is 0. Similarly, 0 times anything is 0. 0 times anything is 0. 0 times anything is 0. That's why I just ignore them. So I need to add 64 plus 32 plus 8 plus 4. So these are 96 and these are 12. 96 plus 12, that will be 108. Another example. What if I have this binary string 1001 1100? Again, this table should be implanted somehow, or it should be stored in your mind after you practice a little bit. So here is what we have. We have 1001 and then 1100. So what are the corresponding weights that we need to add? 8 and 4 and 16 and 128. So this does not count, this does not count, and this does not count, and this does not count. So 128 plus 16, that is 144. Plus 4, that is 148. Plus 8, that is 156. All right? You can use the calculator if you would like to make it easier for you. I like to do the mind math, but it's up to you. Here is another one, 10100011. So here's our table, and here's the mapping. So 1010. So this is with us, and this is with us as well, and then 11 at the end, and all the others are ignored. So we ignore these completely. 128 plus 32, so that is going to be 160, plus 3, that's 163. Next one, 1100 1100. Although they look the same, but because of the bit positions, they will have different, like these 4 are going to weigh much heavier than these 4 because of their positions. So if we look at this and then we map our table, then we have this one is in, this one is in, and then we have this one is in, and this one is in. And you can see the weight of a 1 here is 4, and the weight of a 1 here is 64. The weight of the leftmost one here is 128, whereas this one is only 8. So that is 12, and then we have 192, that is 204. So hopefully that is easy to understand and do. Always write down this table if you are not sure about the weights. And the rule is very simple. Wherever you have 0, ignore the corresponding weight. Wherever you have 1, you need to add the weight or the corresponding weight to all the other weights that are accounted for. And that is how you get the decimal equivalent. Hopefully that is easy. And hopefully you are not bored. I promised you that it's going to be simple, and that's the hardest it will get, so don't worry about it. All right, let's now do the other way around. What if I give you a decimal number and I ask you what is the corresponding binary? So let's do some practice and see if that is difficult or easy. So here's a question. What is the binary equivalent? And we need 8 bits string that will be corresponding to 191. Now, how would we do this? Let's go ahead with the bit positions again. Now we'll do the reverse one. Which of these weights I should write a corresponding 1 to, and which I should ignore? So let's find out. 191 is larger than 128, right? So I'm going to take the 128 with me. Do I take the 64? Well, if we put 1 here, that means it will be 64 plus 128. That is already 192. That means I cannot take the 64 with me. So it has to be a 0. Do we take the 32? It all depends. If you add this weight with the previous ones that you accounted for, is it going to be larger than 191? Then don't take it. If it's going to be less, then go ahead and take it. 128. We are going to ignore this one as if it does not exist because we put a 0 in here. 128 plus 32, that is 160. Is it less than 191? Yes, it is. Then take the 32 with you. Fine. Do we take the 16 or not? All depends. If you add 128 and 32 from before and 16, is it less than 191? And the answer is yes, because we said 128 plus 32 is 160. If we add to them 16, that will be 176. So nothing stops me from taking this one. That's why I'm going to mark it as 1 to take the corresponding weight. How about the 8? So we have 176. So we are, if we compare 176 to 191, we are 15 short. So we need to represent another 15 by ones, and we should be good to go. So do we take the 8? Of course, that is less than 15. I will take it. So now it is 176 plus 8, that is 184. Do we take the 4? If we take 4 with 184, that will be 188. I will take it. We are still 3 short, so I will take these 2 as well. The corresponding binary for that is going to be, let me just erase this. So what we decided is going to be 1 0 and then all ones, and we are going to compare it to what we have. So if we wipe these, you'll find that it's exactly what we have reached, which is 1 0 1 1, and then the rest is ones. Right? So that's the corresponding binary for 191. Find the binary equivalent of 238. Remember, if you are given anything that is less or equal to 255, you can represent by 8 bits. Otherwise, you'll have to go to 9 or 10 or more bits. And more than 8 bits is irrelevant to the IP address study that we need to make. So 238, do we take the 128? Yes. Do we take the 164? Yes, because if you add these two, it's 192. Do we take the 32? Yes, because if you add these 3, it's going to be 224, which is less than 238, so I will take it. Do we take the 16? No, I'm sorry, we cannot, because if we add 16 to 224, it will become 240, and that is larger than 238. All right, we still have 224, and we are 14 short to get to this number. Do we take the 8? I would say yes, because 224 plus 8 is 232, and that is less than 238. And we are only 6 short. So do we take the 4? Yes. 232 plus 4 is 236, and we are only 2 left, and then I don't take the 1. And if you look at the result, it's exactly the same. 1 1 1 0 1 1 1 0. So hopefully that was easy. Now I want you to write any numbers less or equal to 255, and you start the conversion. And how would you find if the answer is correct or not? You can go in ChatGPT. For example, let's check if 238 maps to 110 1110. All right, so let me go here and open ChatGPT. And you can stay logged out if you want. And I'm going to ask, what is the binary equivalent of 238 in decimal? As you can see, you're just typing exactly what you are looking for. There is no science to it. And hit enter. And not sure if you can see it clearly or not. So that gives you the math behind it, what's going on. And then it will tell you that the equivalent is 1110 1110, exactly like what we did. How about 191? What is the binary equivalent? 191. So it gives you the process as well, how you can do it. Equivalent is going to be 10 and then all ones, exactly like we did. So you can just put any numbers, and you can go into ChatGPT and find out if what you have answered is correct or not correct. I'm going to embed ChatGPT or AI in general. If you want to use Copilot or you need to use Gemini, that's up to you. But I'm going to embed that into the learning so you would know how you can yourself augment your learning using AI and find answers quickly without doubting or being uncertain about a specific answer. All right? Hopefully that's helpful, and we're going to use it a lot more as we proceed. All right, now looking at IPv4 addresses, and we're going to find out why it is v4. Let's look at the hosts and networks. Let's revisit what IP addresses are, or IPv4 is. The IPv4 is the decimal representation of IP addresses. And that's an IP address which is 32 bits long. So that means the length is 32 bits. And they are written as 4 bytes or octets. Every 8-bit string is called a byte or an octet. So it is 4 numbers, decimal numbers or fields separated by dots. And here is a valid IP address example. What do you mean by valid? Valid means 4 fields, and that's 1 field, 2 field, 3 field, 4 fields. Any one of them cannot be more than 255. Why? Because this is 8 bits long. There is no way I can represent a number in decimal that is more than 255 in 8 bits. And we said the IP address is 32 bits long and it's 4 fields. Each one of them is 8 bits or 1 octet. This is less than 255. 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 So if it is from 0 to 255, that's a valid field value. On the other hand, if any given IP address has more than 255 in 1 or more fields, that's an invalid IP address. It cannot exist, cannot be an IPv4 address. This is something else. So an IPv4 address in any one of the fields, the maximum value you would see is 255 and the minimum is 0. Okay, let's get now to find out what are the hosts and networks. Given an IP address, how can I find out what is the network, the main network, and what is the host on that network? For example, you have ABC Street, Willow Street, for example. So that is the street, that's the network. But then you have different building numbers, number 1, number 5, number 20, number 255. That maps in the analogy to a host on the network. So if the street is the network, the numbers in the street of the buildings are the hosts. So we need to identify that. So what is a host? It's any device with an IP address on a given network. That's what a host is. So it can be a router, it can be a switch, it can be a printer, it can be a laptop, it can be an iPhone, it can be anything. So exactly the analogy is street addresses. So each one of these houses will have a different street number, although they are all on the same street. So the hosts will have different IP addresses, although they are on the same network. So the main street is the network and the house number is the host. All right. So given a host IP address like this, is it a valid one? Let's see. 255, no, it's less. 255, it's less. 255 is less. So that's a valid IP address. We must be able to identify the network. So we need to know the street from the house number. So the network from the host part. Why do we need this? Because maybe we can be told, but when it is in a computing device, a server or a virtual machine or a switch or a router, they should be able themselves to find out what is the network and what is the host in order to be able to deliver it properly. Okay, so computing devices must be able to identify that too, identify the network part from the host part of an IP address. And this is achieved using what we call subnet masks. So we have to discuss what subnet masks are. So let's look at what a subnet mask is. And now we are focusing on IPv4. So IPv4 is the one that is 8 bits dot 8 bits dot 8 bits dot 8 bits. IPv6 is 16 bits colon 16 bits colon 16 bits, and it has 8 fields. So each one is double the size of the field, and they are separated by colons, not dots, and there are 8 fields, and that is what makes 16 times 8, which is 128 bits. But we are not going to discuss that here. So we are going to focus for the rest of this course on IPv4. At some point in your career, you would want to know about IPv6. And if you specialize in the network field, although I discourage that, you will need to know it sooner than the other fields. But for now, let's skip the IPv6 and the complexity. Let's focus on the easier one, which is IPv4, and that is what you will start learning. And that would be more than enough for you to learn almost all the technologies, and in cloud, and in DevOps and automation, and the other fields as well. So what's a subnet mask? That's what we need to know now. The subnet mask tells the computer which part of the IP address is the network and which part is the host or the device. All right, so the subnet mask is nothing more than a means or a tool through which computing devices can find out what is the network part and what's the host part of an IP address. It can separate the two, or using subnet mask, we can separate the two. Subnet mask can be represented in decimal or insider notation. Let's start with the decimal one first. If I have an IP address like this, 192.168.1.10, is this a valid IP address? Yes, it is. Why? Because all the 4 fields are separated by dots, and none of them is more than 255. So that's a valid IP address. We are given the subnet mask in decimal is 255.255.255.0. The science behind the subnet mask is whichever bits are in the network part, please put a corresponding 1 bit in the subnet mask. And where it is the host part, then put a 0 in that part. I didn't understand anything. Okay, to understand, let me show you this. The subnet mask, if we write this in binary, 255 means what? Means an 8-bit string that is all ones. Dot 255. So that's another 8-bit string that is all ones. And then I have a third one that is all ones in an 8-bit string. Dot 0, that is all zeros in an 8-bit string. All right. So what do I understand from that? What the computing device will understand is the complete first 24 bits, the first 8 and the second 8 and the third 8, they are all the network part. So this is completely the 8 bits field and the 8 bits field and the 8 bits field. This is completely the network part. And what is left is 32 bits for the entire number length minus 24, which is the first 3. These are 24. 8 and 8 and 8. These are all network part. And wherever there are zeros, that will be the host part. So that means we have occupied 24 bits for the network and only 8 bits for the hosts. All right, that's fine. So the subnet mask binary equivalent has ones in the network part and then zeros in the host part. And that is how computing devices can distinguish where is the network part and where is the host part. So now by looking into this, then anything that falls within the first 24 bits is the network itself. And that's why the network here is 192.168.1, and then you can put zeros for everything else. That becomes the network itself, the street name itself. And how about the host? That is the .10 left. Anything that will be in this 8 bits will be the host, and that is the .10. Anything on the left side is network. Now one might ask, can I have a subnet mask that will have zeros in between the ones? And the answer is absolutely not. It's always network part and then host part. It cannot be network part and a little bit of host in between and then a little bit of network and a little bit. So it's contiguous network part and then contiguous host part. It cannot be broken or interweaved. All right, so how did the subnet mask help me? It helped me by telling me which parts of this number are for the network and which parts are for the host. What if I wanted to do the same thing but insider? Remember what we learned from this subnet mask is that there are 24 bits for the network. The remaining 8, because the total is 32, there can't be more than 8 left. So the remaining is for the hosts. That means I can put different combinations here, and there will be the street numbers or the hosts on the network. And as long as this part did not change, the 192.168.1, it's the same network, and anything on the right of that is going to be a host on the network. So .1, .50, .100, .200, .254, .238, they are all hosts on the same network, as long as the network part is common. So now, if the computing device is given that 192.168.1.10 would like to communicate with 192.168.1.20, and both have the same subnet mask, that means These are two devices, probably on the same network, on the same switch, and they would like to communicate with one another. So even if I had a router connected to this switch, the router will not intervene because it's the same network. That's not my business. So let's look at the CIDR notation. Since the subnet mask gave us the number of bits for the network, then why don't we write it in an easier format? So it's a shorter way to write the subnet mask. Instead of writing 255.255.255.0, why don't I just write it like this? 192.168.1.10, and then we put a forward slash, and how many bits are there for the network? So obviously, the remaining of the 32 will be for the hosts. So the number after the slash tells how many bits are used for the network portion of the IP address. And the only reason for the subnet mask was to tell the device, or to tell me, or to tell you which portion of the IP address is the network and which portion is for the host. So 32 is the total number of bits in the IP address, minus 24 in our case, which is the network part. That leaves us with 8 bits for the host. Exactly the same that we have learned in the previous slide. This way or that way are the same. AWS chose to use the subnet mask this way, with the CIDR notation, not with the decimal notation. It's much easier to understand. So now if I give you an IP address and I tell you it's /16, what does that mean? That means the first two fields are for the network, and the next two fields are going to be for hosts. So I can allocate different hosts on the same network by changing the zeros and ones on the 16 bits on the right side. If I tell you it's a /8, what does that mean? That means the first field only is for the network, and then everything else is going to be for the host. So I can put different bits and bytes, different combinations here, and this will be different hosts on the same network. So hopefully you understand it now, and it's easier. So the meaning is the same. The first 24 bits are for the network, and then the rest will be for the hosts. And the result is the same. The network part is 192.168.1.0, whereas the host is the .10. And here is a table that it can be handy if you want to use it, or I can just, go to my friend, to go to ChatGPT, and I'm going to say, okay, fine. What is the binary equivalent if I'm confused of 255.255.0.0, for example? So now it will give me the binary equivalent for that. This is how it will look like. 255.255.0.0, which means this is the network part in any IP address that uses this subnet mask, and this will be the host part. What is the binary equivalent of 255.255.255.0? That's a /24. And it will give me the same. So the first 3 octets are going to be like this. And now, what is the binary equivalent of the CIDR /24? See, the first 24 bits are for the IP of the IP address for the network, and then 8 bits for the hosts. And if you compare this, all ones and then zeros, that's exactly the same, 255.255.255.0, which is exactly the same when I asked it what's the equivalent of this. So whether you write it this way or you write it as /24, it's exactly the same. All right, so this is handy if you would like to use it, or if you can do it on ChatGPT, that's also perfectly fine. And this starts from /8 all the way to /32. And it gives you all the numbers. So for example, a /9, what would it be? That will be all 8 that are going to be ones, and then only one more is going to be 1, and the rest will be for the host. So if you want to write that in decimal, it's going to be 255. And if we have 1 and all zeros, that is 128. If we have /10, so that will be 1 more bit taken into the network, and the equivalent of the second octet now is 11000000, which is 192. If you take 3 bits, that will be 224, and then 240, and so on, until you reach this one where you take the first 2 octets completely. So if you are at the boundaries, if you take 8 into the network only, or 16 or 24, that's easy because that will be 255.0.0.0/8, like here. Or it will be 255.255.0.0 if you do /16, or it's going to be 255.255.255.0 if you go for a /24. Hopefully that's easy, and I'm sure with practice, and if you use your best friend ChatGPT or Copilot or Gemini, it's very easy to train on this and to get it. And if you have any questions, definitely let me know. All right, so let's do some subnet mask practicing so we get whatever we have understood and grasped clear or clearer. And if there's anything missing or ambiguous, then hopefully that will make it more comprehensible. So example number 1, given the below IP and CIDR. So here is an IP address, and that's /24. So that's a CIDR notation, and that's a representation of how long the network part is. So this is your subnet mask in CIDR notation. And if it is 24, we mentioned that each one of these fields is 8 bits long. So that means I have 8 bits and then .8 bits long, and then .8 bits long field, and then .8 bits long field. So /24 means the first 3 octets or the first 3 bytes are for the network, and the remaining one is for the host. One might ask me now, this is .1. How come this is 8 bits? Remember that you can write the 1 as 0000 and then 0001. So the 1 is represented in binary in 8 bits long strings like this. Similarly for the 2, but it's going to be 0000, then 0010. All right, so this is what we have. What is the required now? We need to find the network ID. What's the network? What's the host? And what's the subnet mask in decimal? That's what we need to find out right now. All right, so let's find out. So let's write the binary equivalent of this IP address, and that would be 192. 192 is very easy. That is 128 plus 64, and then everything is 0. So 128 plus 164, and then 6 zeros. Remember, this is 8 bits long. It has to be 8 bits long. 168, that is 128 plus 32, that is 160, and then we have 8 with us. So we will take the 128, we will ignore the 64, so that will be 1 and then 0. We will take the 32 because these two together make 160, and then we'll ignore the 16 and we'll take the 8 with us. So that will be 168, and everything else is zeros. And then .1, 0000, and then 0001. .2, that is all zeros, and then 0010. We put the color of the network bits in purple and the rest is in blue to signify that we have 24 bits for the network and then only 8 for the host. Okay, what do we need? We need to find out the network ID. Very simple. 0 everything in the host part, and that becomes the network ID. So take this as is, copy it, and then .0000000. So that is 192.168.1.0. That becomes your network ID. Okay, so the host part is 8 and the /24 is the network part. Here is the network ID 192.168.1.0 by placing zeros in the host part, and .2 is the host, and then the decimal CIDR block is 24 all ones, so that is 255.255.255.0. All right, and of course I can go to my friend, which is ChatGPT, and I can ask ChatGPT, what is the network ID, what's the host, and what's the subnet mask in decimal for this range? Let's go ahead and try it. So what is the network ID, host, and the subnet mask in decimal for 192.168.1.2/24? So here's the subnet mask, as you can see, 255, 255, 255.0, and it explains /24 means the first 22 bits are for the subnet or the network. So the network ID becomes the 192.168.1.0, and then the host portion is going to be the .2, or here they write it as 0002, but preferably write it as .2. Here we go. The host is 2, and here's the subnet mask 255, 255, 255.0, and this is the network ID. So very easy to come up with any IP address, do it your own hands, write it down, and find out what is the network ID as you think, what's the host, what's the subnet mask in decimal, and come here to verify it or validate it. Okay, let's look at another example, and we're still going to do the same. Find the network ID, the host, and the subnet mask in decimal. We're going to repeat exactly the same. This is exactly the same like before, but here it's .12 and it's /26. So if you look at the binary equivalent, that's the binary equivalent. And then if you notice that we took 2 more bits from here, and these are in purple as well because of the 26. So that's 8 plus 8 plus 8 plus 2, that makes 26. And the blue ones are the host, and 8 plus 4 is 12. So where is the network part? All of this. Where is the host part? The remainder. And the network ID, you can calculate it by putting the host part as all zeros, as if these 2 ones don't exist. So this will become a full 0, and this will not change. 192.168 and then .1, 192.168.1.0, and the host part is going to be the 12, the blue one, the value 2.12. And the subnet mask, if you want to write the subnet mask for a /26, you guys are the best now. So it is 8 ones dot 8 ones, and then another 8 ones. This is 6, so 7, 8. And then another 8 ones. So that is 255.255.255. And for the first 2 bits, I have to put ones and then 0 everything else. So everything else is 0. So that's 255.255.255. This is a bit or an octet that has only 2 ones at the left, and then everything else is 0. So the first one is 128 and 64. If you add them, that's 192. That's how we got to the decimal representation of the subnet mask. Here's another example, exactly the same, but .80 and /26. If you look at it, same thing, the subnet mask is going to be exactly the same because it's /26. So 255, 255, 255.192. If you look at the host here is .80. 80 means 64 plus 16. So this is the host part, and this is the network part. Okay, so what's the host part in the subnet mask? The /26 or 26 bits, and this is the host part. Put zeros for the host part, and then you will be able to get the subnet or the network ID. So here, if you put all zeros and you leave this as is, that becomes 128 is not with us, and then 1 and all zeros afterwards, so that becomes 64. And that's why the network ID is 64, the host is .80, and the subnet mask is the same like before. The same thing, but .138/26. One might be bored by now and I say, okay, why is the same network? There is no change. You are not tricking us. You should give us other networks. There is a reason why I am using this network now, but we'll do more practice with different networks later on. So the equivalent, 138, that is 128 plus 10. So 128 plus 8 plus 2, that is 138. And these are the host part, and this is the network part. So what's the network ID? Put zeros in the host part, and you will end up with the network ID. So that's 192.168.1, and that will be 128. Okay, because we have all zeros. Forget as if this does not exist and this does not exist. That becomes the network ID. And the 138 is the host, and the subnet mask is the same like before. Last but not least, let's look at another one, but the range here is 217, same subnet mask. So 217, that is 128, plus 64, that is 192, plus 16, that is 208, plus 8, so that's 216, plus 1, that's 217. Network part, host part, so put all zeros in here, you end up with the network ID. So 192.168.1.192. And the host part is .17 and the subnet mask is the same. Now, why did I use the same network all the time? Now let's put them all side by side with the very original one that we have done. So the very original one that we have done is 192.168.1.2/24 and the network ID was .0. Then we looked at .12 and that was the network ID. Again, same network ID, but the subnet mask is different, so they are not the same. This is actually part of this. This covers the IP addresses until we get to the next subnet, which is 64. So this covers from 0 to 63, and this one starts at 64. We're going to explain that further later on. And this one ends before the 128, so at 127. This one starts at 128 and ends at 191, and this one starts at 192 and ends at 255. So as if what I'm trying to say here is, if we look at this IP address and the network ID, we find 192.168.1, and this is the .2, and this is the subnet mask. If we look at the next ones, we'll find that this was all the hosts, but now the host part has shrunk into 6 bits only. The network part has been expanded by 2 bits. And the subnet mask has also been extended by 2 bits. If you combine these 4 into one network, believe it or not, you will end up with this one. But this is just to let you know that as if we have divided this into 4 and we had to borrow 2 more bits from the host and make it a network in order to have one network divided into 4. This is called subnetting, but don't worry about it. Just keep it in your mind because we are going to use it later on. All right, let's now find out what IP address classes are. Actually, the IP addresses, whoever invented that, they divided them into classes. And they have class A, the class B, and class C. We have also class D and E, but we are not going to discuss that because it's beyond the fundamentals of networking. It has to do with multicast and other stuff. So IP address classes are created to help effectively assign IP addresses to big, medium, and small networks without wasting too many addresses. So when they thought about them, they thought about the best and efficient use of these networks. And they started with A, B, and C. So A, this is for big corporates. Okay, the CIDR block or the subnet mask, the default is /8. And it starts from 1.0.0.0 all the way, and inclusive of everything in between, to 126.255.255.255. This has 126 usable networks and 16 million hosts in each. So that's extremely large corporates. An example, 11.0.0.0/8. So notice that the leftmost byte starts at 1 and ends at 126. What about 127? This is reserved for local hosts and other stuff on the servers. We are going to learn about them as we learn more IT. What about class B? Class B is the default subnet mask inside their block is 16. So the first 2 octets are for the network. The second 2 are for the hosts. And it starts at 128 on the leftmost decimal value of the octet to 191. And that has 384 possible networks. In each one of them, we have more than 65,000 hosts to be allocated. An example, 148.12.0.0/16. Class C is for small networks. So B is for medium networks. This is for large networks. C is for small networks. The default subnet mask is /24. It starts from 192 and ends at 223. the leftmost byte. It has 2 million plus networks, a lot of networks, but each one of them has only 256 IP addresses, but usable are 254. We're going to discuss that later on. So consider that as 256 for now, or 254, that's fine. An example is 196.12.108.0/24. So IP address classes, by the look of the leftmost byte, you can tell whether that's a class A or a class B or a class C. So if it is from 1 to 126, that's a class A, definitely. 128 to 191, that's a B. And 192 to 223, that is a C for sure. So each class has a default subnet mask, as we mentioned, /8, /16, and then /24. And there are other specialized classes, but out of scope. All right, so let's now figure out how we can break an IP address block, an IP address range, into multiple subnets, we call it, or multiple segments, multiple chunks. Why do we do this? We do it because if I have, let's say I have a campus building and I have one big chunk of IP addresses, one block, and now I need to build separate LANs in each one of the buildings, and then I will connect them to the data center, for example. So how can I do this? I have only one range, and it's not recommended to use the same range across a lot of buildings because it has a lot of technical implications way over our heads now, and we shouldn't get into the details why we should avoid that. But it's recommended that you segment or distribute that into multiple subnets and then use one in each building. I'll give you another example. Let's say it's a corporate and it has one office in each one of the 50 states in the United States. And the headquarters is, let's say, in India, for example. And now they need to connect this. So they have to go across WAN. We said if it's not in a close vicinity, it has to be a wide area network. And we talked about that before. So in that case, if you want to break it down, the one big range, you must break it down, because otherwise you cannot use the WAN the right way without breaking that down and isolating a block of IP addresses for each one of these offices. They cannot be in one office. They can't live in one office, period. So they have to be different or separate IP address ranges, smaller ones, chunks, from the big block that you have. And that is called subnetting. So that is why we are going to discuss subnetting, but we will start doing it the easy way, without a lot of math, and without confusing you with a lot of binaries and all that stuff. If you have understood everything before this and you are good with that, then you can use the easy way and you are good to go. If you want to know more details, or if you are planning to be in the engineering side where you are going to do a lot of troubleshooting and you want to minimize your dependence on calculators and online tools, then you can learn the details which will follow this one. But now it's the easy way. So this is for the people who want the easy stuff, the easy way, the faster way to do things, but hopefully also they understand what they will see and what they will get. This is very important to know. All right, so let's see what subnetting is. Subnetting allows us to take one IP address block and then divide it into smaller blocks to be used on different networks. Think of subnetting an IP address range as slicing a pizza. Exactly when you have a pizza and you will have, let's say it's a small pizza and you would like to cut it into 4 slices. So that's exactly the subnetting. So this will be the block IP address range, the actual pizza, and then the slices, each one of them is going to be called a subnet. When we do subnetting, we don't have the liberty to decide how to cut it as we do with the pizza. For example, with the pizza, you may decide to cut it into 6 pieces or 3 pieces or 12 pieces. In subnetting, you can't do that. You either divide it into 2 or 4 or 8 or 16 or 32 or 64. Does this seem familiar to you? Yes, these are the weights of the binaries. So it's either 2 or 4 or 8 or 16 or 32 or 64. What if I need 5 only? Then you have to go for 8 and then you keep 3 as spare. What if I need 12? Then you have to go for 16 and you keep 4 as spare. What if you want 20? Then you go for 32. So you divide it by 32 and then you'll use 20, and then 12 are going to be spare. So this is very important to remember. You cannot divide an IP address block by 3 or by 5 or by 7 or by 11 or by 9. Given an IP address range to subnet, we need to know. What do we need to know? We need to know how many subnets are needed and how many hosts are needed per subnet. So if you are given an IP address block and you are given the scenario of the 50 offices in the 50 states in the USA, and you are told that we need to break it down, that big block, into enough subnets that we can use in each one of these offices, the very first question that you would want to ask is how many hosts do you need per subnet? So in each office, how many machines are going to connect to the network? If they are 50, then go for 64, or maybe go for 128. So you need to go for a higher number of IP addresses, not exactly 64 if they are 64, because what if a new employee is added tomorrow? So you always need to design for a little bit bigger than the requirements. Or maybe you can ask, okay, how many users are going to connect? How many devices are going to connect? How many hosts? If you are told 64, then you can have a subsequent question is, what is your anticipated growth rate per year or every couple of years? Is it going to be 10%, 20%, 30%? And that will help you decide what size you are going to make the subnet. So this is very important. The second question is how many subnets? So we have 50 offices in the United States, in each one of the states. Is there a chance you are going to open satellite offices from these offices? If the answer is yes, how many do you anticipate per year, per 2, per 5, per 10 years? If they know the answer, then you need also to design not 50 subnets. Now I will go for 128 subnets or maybe 256 subnets. So I'll have a room to scale, to grow. I don't need to design it and then start using it. And 1 year down the road, I would say, oops, okay, I didn't account for that. So now we have to redo everything and readdress everything, which will be a nightmare. Okay, so this is very important. The two questions, how many subnets and how many users per subnet? And the third question that will be, and will show that you understand what you are doing, is what is the growth rate for hosts and for subnets as well. So let's look at how we can have an IP address range and break it down, and we'll do it the easy way. The easy way, we mean we are going to do it using online calculators. So what we need to identify using the online calculators, the network ID of the IP address range that we have, the usable IP addresses in the range, and also the broadcast address of the subnet. The broadcast address, by the way, is the last IP address in any subnet. So when you put in the host bits all ones, that is your broadcast address in the subnet. So we have a range 192.168.1.0/24 insider format, and this means we have 24 bits for the network. 24 bits, so all 3 bytes. So this one included, this one included, this one included, and this is going to be for the host. So this is the network and this is the host. Okay, we need to divide the range into 4 equal sized subnets. So we're going to do a subnetting exercise using online calculators. And for each subnet, we need the subnet mask, the network ID, the broadcast IP address, and the number of usable IP addresses, and the first and last usable IP addresses. So that's what we need to know. And online calculators, we have 2 famous ones and easy ones that I would recommend. This one is very easy. And there is another one from SolarWind Subnet Calculator. I'm going to use this one. So when you practice, please use that one as well. So we are going to be in line. If you want to use the other one, if you want to try the other one, please feel free to do so. One online tool is more than enough for you to do that, and Calculate Quick is the recommended one, or the highest recommended one on the internet. And if you want other calculators, you can go to your friend ChatGPT and ask what are the popular IP subnet calculators or IP calculators. It will give you a list of available ones. All right. So what do we need to do now? I need to take this one, 192.168.1.0/24, and I'm going to click on this link, and we need to divide it into 4 equal sized subnets, and we're going to find this information for each one. Before we go and do anything, equal sized subnets. One small pizza, you need to cut it into 4 equal slices, 100% equal. If you think about it, how many IP addresses we have here? How many hosts in this network? So network ID, I can tell you that the major one, the main one, network ID is 192.168.1.0. That's the network ID. How many bits do I have for the host here? We have 24 for the networks. That means we have 8 left for the hosts. So if that's the case, we can have up to 2 to the power 8 different combinations in the 8 bits. So that's 256 host IP addresses that are available. A rule: the first one and the last one, you can't use them. They are not usable. So the 192.168.1.0, that's the network ID, so we cannot use it on a host. And the last one is going to be 192.168.1. Can you guess what would be the last number? Put all ones in the host field. So that will be 8 ones, which is 255. That's the maximum you can get from 8 bits. So this is the broadcast IP. This is for the original subnet. So what's the number of usable IP addresses? It will be the total number minus the network ID minus the broadcast. So minus 2, that will give me 254 actual usable IP that I can allocate on hosts on this network. What if this network grows more than 254? Unfortunately, you cannot use the same subnet. So what do? We have other hosts, they need to sit on the same subnet. You'll have to readdress your subnet and provide for a bigger one. That's what you have to do. That's why it is very important to ask the question, the size of the subnet, how many hosts, and the growth. All right, let's go ahead to the online calculator. I'm going to take this range and I need to divide it into 4 equal pieces, 4 equal pizza slices. So let me go ahead and click on this link. And this is how it looks like. IP subnet calculator. Here I'm going to write the range that we have, 168.1.0, and it is /24. And I would say calculate. If you scroll down, you'll find here, let me just make it a little bit bigger. So this is a class C, and the IP address, the network ID, and you can always copy the information. The broadcast address, as we calculated it, 192.168.1.255. The first usable IP, it will be the one after the network ID, which is .1. The last usable IP is the one right before the broadcast address, so that is 254. Here is the CIDR notation, and the total hosts is 256, but the usable ones are 254. And the mask bits are 24, and the subnet mask and all the details that you need to know about this. And here they give you the binary representation for the IP address, for the subnet mask, and the network ID and the broadcast address. Everything is included. So if you look at the network ID and the broadcast address, the only difference is here it will be zeros in the host field, and here it will be all ones in the host field. So they are exactly the same, but the network ID, all zeros. Oh, the broadcast IP is all ones. Okay, that's all cool. I need to subnet it. So we have a tool called Subnet Division tool. Here it will ask you, how many subnets do you need? So I need 4 subnets. You can here add, and so it allows you to add any number, but at the end, if you go for 5, if I go for 3, for example, calculate subnets, it will do 4 of them. It will do 4 of them. Yeah, but I asked only for 3 because you can't divide a block by 3. You can divide it by 2 or 4 or 8 or 16. So let's say if I tried to do 5, let's see, calculate subnets. You'll find that it has divided that by 8 because 4 is not enough. It goes to the next one. It's up to you to use 5 of them, and then 3 will be spare. So let's go back to our example, 4. Let's look at what is done here. So here you have the first subnet. It's going to be 192.168.1.0 and /26. Please note, that the subnet mask, when you divide a block by a number, so 2 or 4 or 8 and so on, if you divide by 2, you'll find that the subnet mask will be extended by 1 bit. If you divide by 2 to get 4 subnets, then it will be extended by 2 bits, and that's what we have here. So this is a /26, although the original one was a /24. So when you have a /24 and you divide it into 4 subnets, then the resulting subnet mask, or the new subnet mask, is going to be extended by 2. Why? Because 2 to the power 2 is 4. That's what gives you the 4 subnets. What if I want to divide by 8? What will happen? So look at this. This is by 4, 26. By 8, it will be 27. Why? Because 3 bits are needed to distinguish between the 8 subnets, and that is how it has been converted from /24 into a /27. So when you do subnetting, the subnet mask, or the network part, gets extended into the host. How many bits into the host? If you divide by 2, it will be only 1 bit. Let's prove it. So it's going to be 25. From 24 to 25, that gives you 2 subnets. From 24 to 26 gives you up to 4 subnets. From 24 to 27 gives you up to 8 subnets. From 24 to 28 gives you up to 16 subnets. Let's prove it. So let's say I want 16 subnets. You'll find that it has extended by 4 bits, the subnet mask. And it is very good that we are having more subnets, more networks you can use separately. But the downside is you are getting less hosts in each one of the networks. That's why it is important to ask how many hosts per subnet and how many subnets do I need. You divide it by 16 and you have a resulting /28. The /28 will only leave 32 minus 28, which is 4 bits only for the hosts. So that can give you a maximum of 16 hosts. And that doesn't help me because I need 64. So if you need 64, you have to divide maximum by 4. Why? Because this is /26. /26 for the subnet, that will leave me with 6 bits for the host, and 2 to the power 6, 2 times 2 times 2 times 2, 6 times is 64. So that's exactly the number of hosts that are available in a subnet. You put the subnet, it will give you the details about it, and it will give you the first, last, and on so on. And if you would like the binary, here it is. And if you would like to go ahead and look at the subnetting, then you can go into the subnetting tool and you can ask for how many subnets, and then you can do it. If you are not subnetting, it will tell you that the usable host addresses here are 192.168.1.1. You can take the network ID .0, and the last one will be 254, and the broadcast IP is here. So it's very easy to use. It doesn't need magic. It doesn't need a lot of knowledge, and you can play with it. And if you do only 2 exercises, you will be the master of using this tool. All right. So hopefully that was easy. And that is what we needed to do it when we subnet the easy way. Let's do one example on IP address breakdown, or IP address range breakdown. We are going to use the calculator, but I also will explain to you how you can do it. Given an IP address range and a subnet mask for a subnet, how can we identify the following? The network ID, or the network address, and the usable IP addresses in the range. How many are they? What's the first one and what's the last one? And what is the broadcast address of that subnet? So here's an example, 112.168.2.0/24. So let's go ahead and go to the IP calculator first. So 112.168.2.0 and /24. So if you click on analyze basically, or calculate, you'll find that the network address is 112.168.2.0. Here is the one. Let me just make it bigger. And the network address is the same, the network ID. Broadcast address, this is /24. So in the last octet, I'll put all the bits as 1. 8 ones. And where did I get the 8 from? Because it is /24. The first 24 bits are for the network, and the entire size is 32 bits. So 32 minus 24 leaves us with 8 for the hosts. So if you put 8 ones, that is 255. So this is your broadcast address. The first host IP address, the very first one you can use. You cannot use the broadcast and you cannot use the network ID, the very first IP address. So .1 will be the first one and .254 will be the last one because it is one before the broadcast. So this is everything we need to know about the subnet, and here is the binary equivalent. The subnet mask for 24, so 24 ones and then zeros for the hosts. Here's the network address. Put all zeros in the host field and put all ones to get the broadcast address. Very easy. To find the broadcast address of a given range, all you need to do is find out what's the length of the subnet mask, decide where the host field bits are, and fill them with ones. That will be your broadcast address. So in our example, here is the host field, fill it with ones, and translate that into decimal, and it becomes the broadcast address. So that is going to be 112.168.2.255. If you want the usable IP addresses, the very first one, which is the network ID, and the broadcast ID, they are not usable. They are reserved for special purposes. And that's why you can have all the hosts in that subnet -2, which is the network ID and the broadcast IP, and that would be the number of usable ones. So if I have this network, and we said that the network ID is .0, that is not usable, and the broadcast IP is .255, so that's not usable. So I have the ones that are usable. The number of IP addresses is 2 to the power and the number of host bits. So that means 2 times 2 times 2 times 2, 8 times, or that is 256. -2 for the network ID and the broadcast IP, that is 254. So these are the usable IP addresses, and the very first one to use is going to be .1, and the last one is going to be .254, as we have seen in the calculator IP. So what I'm trying to show you here is how you can do it yourself, or if you understand it well, then just go with the calculator. It will be much faster and much easier. And of course, you can go to our friend ChatGPT and you can get the same results. Let's go ahead and give it a try. And I'm going to ask, analyze the subnet 112.168. Let me just make this bigger so you can see what I'm typing. .2.0/24. I need to know the network ID, broadcast IP, first usable IP, last usable IP, and number of usable IP addresses. And of course, you can narrate that using voice. So you can click on voice, and instead of chatting, you can just say what you want to do. So here's the subnet, and that's the IP address. That's the CIDR notation, subnet mask, first address in the subnet or the network ID, then the broadcast address, and then the first usable IP, the last usable IP, and then how many IPs are usable, and it gives you the math on how that was reached. So in a /24, we have 8 host bits, 32 minus 24. And then here's a summary of what you need. So if you'd like to do it on the calculator, that's fine. If you'd like to do it in ChatGPT by narration, that's fine. If you would like to do it to your own hands and verify, that is also fine. All right. Now, let's do a cheat table for you to remember the number of hosts and also the usable IP addresses. If you have a subnet or a network with a /24, that will leave you with 8 host bits. Host IP address, the total number, including the network ID and the broadcast, is going to be 2 to the power n, where n is the number of host bits. It's 32 minus the subnet mask length. If the subnet mask is longer, then you get less hosts, and the net usable ones is -2, so that will be less as well. If you make it longer again, then you get less hosts and less net usable ones, and so on, until /30, where you'll have 4 IPs, of which 2 only are usable. So this is very small. Why would I use this? if you have two routers in a WAN and you would like to connect between them, you have to enable or to provide an IP address to this side of the link and this side of the link from a WAN, and they have to be in the same subnet. So you want only two IP addresses. So why waste more IP addresses? Allocate a /30 subnet that will have only two usable IP addresses. Allocate one on this side and allocate the other on the other side, and that's it. We're going to talk about that later on when we get to IP routing. All right. Now let's do another practice example for the IP breakdown, but this time we are going to do it ourselves. We're not going to do the calculator, just to make sure that you understood it right and you are capable of doing it before you standardize on using calculators or ChatGPT all the time. So here's another example, 112.168.209.33/20. So now we did not give you one that is 8 bits or 16 bits or 24 bits. No. Now we are giving you one that will end exactly at the half of this octet. The left half is going to be bits for the network, and the right half is going to be bits for the host. So you are more familiar with any subnet mask. It doesn't have to be /24 all the time. So for this one, if we translate that into a binary equivalent, that is going to be the first octet, second octet, and then 209. Can I take the 128? Yes, you can. That's why we're going to have a 1 in the 128. And now I'm talking about this one. I'm going to take the 128 with me. All right, can I take the 64? Let's see. 64 plus 128 is 192. Is that less than 209? Yes, it is. Then I can take that as well. So a 1 and a 1. That is 192. We are still 17 short of the 209. Can I take the 32? No, you cannot. So make it a 0. Can I take the 16? 192 plus 16, that is 208. Yes, I can take it. So that's why we place a 1. And then all zeros, we are still 1 short. 208 to 209 is only 1. That's why we put 1 here. So since it is /20, that is 8 plus 8, that's 16, and 4 is 20. So this is the network part, and then the host will be the remainder. So here we have 12 bits for the host. We have 4 here plus 8 here. So we have 12 bits for the host. All right. Okay, what do we need? We need to know the network ID. Easy. In the host part, put all zeros. So put this to 0 and put this to 0 and put this to 0 as well. All right. If I do this, what do I end up with? I end up only with the purple ones and then zeros, and here all zeros. So all zeros is easy, but the purple ones, and this is going to be a 0. So 192 plus 16, that is 208. So 208 plus 0, and the 168 will be the same, 168, and the 112 is going to be the same. So the network ID is 112.168.208.0. Easy. Right? Okay, what do we need? We need the broadcast IP. So to get the broadcast IP, you have to put all the host bits ones. So if this is all ones, easy, that is 255. So where is the tricky part? The tricky part is here. This is 208. Now if you put 4 ones here, the 4 ones are 8 plus 4 plus 2 plus 1. So 8 plus 7, that is 15. 15 added to the 208, that is 223. So 223 plus 255 is the broadcast IP. So let's look at that. So that's how it would look like, and that translates into 223.255. Now we know the network ID and we know the broadcast IP. How many usable IP addresses do I have here? Let's find out. We have the host bits 32, which is the total length of an IP address, minus 20, which is the network part in the subnet mask as they indicated here. That means I'm left with 12 bits for the host. So 2 to the power 12, 2 times 2 times 2 times 2, 12 times, that is 4096. Remove from that, now we're talking about the usable IPs. Remove from that the network ID and the broadcast IP. So remove 2, that leaves you with 4094. First usable IP, we put 1 and all zeros in the host part. That will be the first one. Last usable IP, broadcast IP minus 1. So if the broadcast IP was 223.255, the one before, .254, that is going to be the last usable IP address. And we have 4,094 IP addresses. So hopefully the concept is clear, and I want you to come up with IP addresses, any IP addresses, any subnet mask length, and then try to do it yourself, try to analyze it, and try to find out the host bits, the number of usable IP addresses, the first usable IP, the last usable IP, the broadcast IP, the network ID. I would like you to train, and you can validate on ChatGPT or on the calculator, and you will find if your answers are spot on or if you have missed something. If you missed something, go back and try to find out what did you do wrong, fix it, and that's how we cement the knowledge, and that's how we retain the understanding and the information we learn as well. All right, thank you. So let's now discuss the subnetting topic in details. So we are going to take ranges and we're going to break them down based on requirements. And during the process, you will understand how subnetting is done in real world. So why do we do subnetting? Subnetting will allow us to take an IP address block and then divide it into smaller chunks. And why do we do this? Because when we build an infrastructure, usually we have different offices, different networks, different LANs, wide area network, wireless LAN requirements. We have different requirements. Also, when we come to the data center, when we build it, we want to have databases separate from the application, separate from the monitoring, separate from the other tools, separate from the Active Directory domain where the users log into the Microsoft domain and the corporate network and be able to use the different applications, separate from accounting, separate from finance. So there are requirements to separate data in your data centers and to build different LANs and to build wide area network, and all of that requires IP addressing, and it cannot be one range. It has to be broken down into smaller networks that have boundaries and you don't intermix between the different networks. So that's why subnetting is a must. It's not a luxury and it's not an option when we have a sizable network infrastructure that we need to build. Also, the fact that when you build different networks, you can start to put security in between. You can do filtering. Subnetting is a critical component of any network infrastructure. That is given. Even if it is a small company that has 2-3 offices, they will need to have different networks in each one of these offices. So let's do a subnetting practice, and through the practice, I'm going to explain how that is done. So we have an IP range below, 112.168.240.0/24. So from what we know, that means the first 24 bits, because of these 24, is the network part, and the last 8 bits is the host part. How did we know that? Because it's 32 bits long, minus 24, I'm left with 8 only. So what do we need? We need 4 subnets. We need to divide that into 4 subnets. And each subnet must have 64 total hosts or total IP addresses. And if we do the analysis, it's easy, because how can I get to the network ID? Put zeros in the host part, and it's already done. It's already a 0 in the host part. So that's the network ID. The same thing is the network ID, and we don't write the subnet mask next to it. If I convert that into binary, it becomes 0111 and then 4 zeros dot 10101000 dot 11110000, and this is the host part. What is the broadcast IP? The process is easy. Put ones in all the host bits and convert that into decimal, and that becomes your broadcast IP, which is the last IP in the network. So put 11111111, and that becomes 255. Total number of IP addresses in the original network. We still did not do any subnetting. We are analyzing the original network. So how many host IP addresses do I have? Total, not the net, not the usable ones. So 2 to the power n, and n is the number of host bits. The number of host bits in our case is 8. So that's 256 IP addresses, including the network ID and the broadcast IP. So if you want the usable IP addresses, it is 256 minus 2, which is 254. And they start at .1 and they finish at .254. The one before the broadcast IP and the one after the network ID are the first and the last ones to be used. All right, so now let's go ahead and think about what we need to do. We need to divide this into 4 equal subnets. So if I have 256 total host IP addresses, now if I divide this by 4, how much do I get? That will be 64. You can use your calculator if you would like to check. Okay, so 64 in each one of the subnets. So each one of the subnets will have a total number of hosts of 64. Why? Because we need 4 equal in size subnets. All right, that's fine. So let's try to define the 4 chunks that we are talking about. So we'll start from 0 to 63. That will be the first one. What's my evidence? If I tell you that please divide 8 by 4, let's say you have 8 IP addresses. Divide 8 by 4 and you will start counting from 0. So that is 0, 1, 2, 3, 4, 5, 6, 7, right? So although the result is 2, the first one will be 0 and 1 because I start counting from 0. 0 and 1 are 2 numbers. That's it. So if you have a total of 64 and you would like to count from 0, so it will start, the first range will start from 0 and it will end at 63, not 64. If it ends at 64, that will be 65 in total. What's my evidence? Here, when we do the counting, the 8 numbers, they start from 0 and they end at 7. And total hosts that we have in the subnet, they start at 0, which is the network ID, and they end at .255, which is the broadcast IP, right? So these are 256. So exactly the same. The first one will be from 0 to 63. You can count them on your hand, or you can write them down if you want, or you can ask ChatGPT if you don't believe me. Okay, so if we are from 0 to 255, the first range, the first 64 is going to be starting from 0 and it ends at 63. The next one is going to start from 64 and it will end at 127. The third one is going to start at 128 and is going to end at 191. The fourth one is going to start from 192 and it will end at 255. If you would like to count, you'll find that these are 64, these are 64, these are 64, these are 64, and the starting is .0 and the end is .255, which is exactly what we have here. So that is the equal 4 chunks or 4 subnets that we need. Done. It's solved. Yeah, but how can we allow the computer to understand this? What is the subnet mask? And the subnet mask that we are going to come up with must start the first subnet at 0 and end it at 63. So the host bits, the iterations, the different combinations in the host bits must not exceed 63. Because when we exceed 63, we are going to transition to the next range, which is starting at 64. Same thing, this should end, the subnet mask should end at 127, because when I switch to 128, I'm going to get to the third subnet. So the new subnet mask can never be the same subnet mask. You cannot claim that you are going to cut a pizza into 4 equal slices and the result is going to be a full pizza and a full pizza and a full pizza and a full pizza. It's going to be a quarter and a quarter and a quarter and a quarter. So that means the subnet mask must change. That is not an option. It has to change. So let's think about the subnet masks now. If the number of IP addresses is 64, and we mentioned that the subnet mask must be able to reach the limit, the maximum, the broadcast IP, it will be the last one, will be the 64th host, and then it has to switch. How many bits do I need to get to 64 IP addresses? Think about it. 2 times 2 times 2 times 2, how many times? So 2 times 2 is 4, times 2 is 8, so that's 3. Times 2 is 16, times 2 is 32, times 2 is 64. So I need 6 bits for the host in order to switch subnets every 64 IP addresses or every 64 hosts. So that means I need 6 bits for the host, and that leaves me with 32 minus 6, which is 26, that is going to be for the new subnets or the new networks. So the new subnet mask is going to be a /26. How can I verify? So let's proceed and find out. So this is going to be the new subnet mask, a /26. /26 means 8 bits dot 8 bits dot 8 bits dot 2, and all of them are going to be ones. So 255 dot 255 dot 255, and the last one has only 2 bits that are 1, and that is 128 plus 64, so 192. That's how we came up with this one. So what are the resulting subnets? They are going to be .0/26, which will cover the first range, then .64/26, then 128/26, then 192/26. If you notice here, the difference is 64, the difference is 64, and the difference is 64. And why is that? Because each subnet has 64 IPs, right? So every 64, I'm going to switch subnet. And what will confirm this is the new subnet mask. Simply because in any one of these, it's going to be network 8 bits, network 8 bits, network 8 bits. Then I have network. So here I have 2 bits, 8, 8, and 8. And I have 6 left for host. What is the maximum number I can put in 6 bits? So let's try. 1, 2, 3, 4, 5, 6. Let's count them. So this is 1. This is 2, the weight. This is 4. And this is 8. So these are 15. And this is 16. And 15 is 31. 31 plus 32, that is 63. So you start from all zeros and you go to 63. If you add one more, you will switch to the next one. The next one is going to be 1, 0, 0, 0, 0, 0, 0, which is 64. So that means I have switched to another subnet, and that's exactly what happens here. In the first subnet, because of the subnet mask, 6 bits only for the host, I'm going to switch at 63 will be the max, the broadcast IP, and the next one is going to be a different subnet. So now we are satisfying that, and the new subnet mask seems to be working. Let's analyze the first subnet. So it is 240.0/26. Remember, the original one was 24. So that's the subnet ID. Okay, fine. Binary equivalent is the same 168.240, but then we take 2 bits for the subnet, and these 6 will be for the host. So what will be the first and last IP? This is the subnet mask in decimal. The first IP is 0, and the last one is 63. So 63 is the broadcast, and this is the network ID. So the usable IP addresses are not 64. They are 64 minus 2. They start at .1 and they end at .62. Right? So these are the usable IP addresses. And the broadcast IP is the last one. So that's easy, right? And what's the subnet mask? As we mentioned, it's going to be 255.255.255.192. Okay. So the first subnet, all of the numbers from .0 to .63, these 2 bits are going to be fixed at 0, 0. Let's analyze the second subnet. So that will be 112.168.240 and starts at 64, and the subnet mask is /26. So what's the subnet ID? Again, put zeros in the host and you will be good to go, 64. And here's a confirmation that if we put zeros here, then we're going to end up with 64. Now, notice that this is going to be fixed for all the IP addresses from 64 to 127. and it will switch at 128. So all the IP addresses or the hosts in this subnet are going to have 0, 1 here, and the range is from 64 to 127. And here's the subnet mask, and it starts at 64, ends at 127. And the usable IP addresses, they will start from 65 to 126. And the last, or the broadcast IP, is 127. If we go to the next one, 128, then similarly, we can do the same analysis, and you will figure out that the ID is 128. Please note that this has switched. So in the first subnet, the 2 bits were 0, 0. In the second subnet, they were 0, 1. In the third subnet, they are 1, 0. And then here, we start from 128 and we end at 191. Subnet mask is the same. The IP addresses or the range is 128 to 191. The usable ones are the next one, 129, and the one before the broadcast, 190, and the broadcast IP is 191. The fourth one is 192, and the ID is the same. And please note that this has switched to a different subnet. So that's how we distinguish the 4 subnets from one another. And the first IP is 192, the last is 255. The usable ones is 193, and the last is 254. And the broadcast IP is .255. So now it's very clear that in order to move from the original subnet to get to the entire subnets, so the original subnet mask was 255.255.255.0, I had 8 bits for the host. In order to divide that pizza into 4 equal slices, I ended up taking up 2 bits from the host. Why 2? Why not 3? Because we needed 4 subnets, right? The 2 bits can give me 0, 0, 0, 1, 1, 0, and 1, 1. So 4 different combinations. Each one of them will distinguish one subnet from the others. So that's more than enough for 4 subnets. If I needed 5 or 6 or 7 or 8 subnets, I will have to take 3 bits. And the second thing to note is the more subnets you create, the less host bits compared to the original you will end up with. So the more subnets, the less bits for the host. So that means less hosts per subnet. So that's one thing to keep in mind. The third subnet took the 0, 1, and that's the 64 subnet. And then the third subnet took 1, 0, and the fourth subnet took the 1, 1. So as if the rule is, if you would like to divide a subnet, a block, into 2 subnets, you will take 1 bit. If you want to divide it into 3 or 4, then you will take 2 bits. If you would like to divide it, or if you need 5 or 6 or 7 or 8 subnets, then you have to take 3 bits. Shift into the host side by 3 bits. If you want anything from 9 subnets to 16, you have to take 4 bits from the host field. And that's how it works. Okay, so at the end, the given IP range into 4 subnets, the resulting subnets will be /26, which is 2 bits longer than the original one. So we have borrowed 2 bits from the host field in order to create the 4 subnets. And each new subnet will only have 6 host bits, which means 64 IP addresses only, whereas the original one had 256. One golden rule, please stick that, engrave it in your brain, is once you subnet an IP address range, you can use these as you wish, but you cannot use this anymore. And here's a rule to summarize what we discussed. If you started from /24, and if you need 1 subnet, then don't do subnetting. If you need 2 subnets, then you have to borrow 1 bit. So the resulting subnet mask is going to be /25. That will give you 2 subnets, and it will leave you, instead of /24 gives you 8 bits for the host, this will leave you with 7 because you have already borrowed 1. And that will leave you with a total of 128 hosts in each resulting subnet, and the usable ones will be 126. So please notice, the original one, you had 256, and the usable were 254. Here you have 2 subnets, each one of them has 128. The usable in each one of them is 126. So you waste 2 in the first subnet and you waste another 2 in the second subnet. So the total usable hosts are not going to be 254. They are going to be 252. So subnetting wastes some hosts in the original subnet, but we have to do it because that is best practices for building infrastructures and networks and different LANs and different offices and different wide area network links and so on. If you want to subnet to 3 or 4 subnets, you have to borrow 2 bits. If you want to subnet 5, 6, 7, or 8, up to 8, then you have to borrow 3 bits. And the subnet mask is going to be longer in each one of them. And that means the remaining host bits are going to be lesser, and the total number of hosts and the usable ones are going to be lesser as well. So the more subnets you make, as you notice here, for example, I have more subnets and it's /30. It only has 2 usable IP addresses. So the more subnets, the lesser hosts per subnet. So you have to ask the questions: how many hosts per subnet? How many subnets do you need? And then you can assess and see if the block given to you is enough or not. All right? Hopefully that was clear. Now let's cover and identify the public IP addresses. We're going to talk about public IP addresses and then private IP addresses, and we're going to distinguish between them. Very important to understand. So what's a public IP address? A public IP address is an IP address that can be accessed over the internet. Are you saying that there are IP addresses that cannot be accessed over the internet? Yes, and these are the private IP addresses. In your home, internally inside your network, you will have private IP addresses. So the internet cannot get directly into your machines. They cannot. They have to go through a public IP address, and that will be how they get to you. And then this router needs to do some magic to send you the traffic. So if you go on your browser and then you type cnn.com, when you type cnn.com, you are using a private IP address. We're going to talk about this next. And the router is going to convert that into a public IP address before sending that out to the internet, as if it is masking a different identity, telling the internet, hey, internet, I am defined on the internet. I have an internet approved IP address, a public IP address. And if you want to come back to me with the response, please use this IP address. Any device or network that wants to communicate directly with the internet must use a public IP address. Even if it is your home router, yes, your home router does have a public IP address. And same thing, the router at your office or your company. And the same thing when you go to an airport and you connect to the wireless LAN at the airport, then the airport must have public IP address on the internet. If we reciprocate, that means if I need to get into Amazon.com on the internet, Amazon.com must have a public IP address. Yes, that's correct. If I want to get into CNN.com, into BritishTelecom.com, anything that is available on the internet, that entity must have a public IP address. So what's the public IP address? Think about the postal system. If you don't have an address registered on the postal system, that means nobody can get to you. If you are living in the middle of the jungle and there is no address and there are no streets and post doesn't deliver into your location, that means you are off the grid. Nobody knows about you. You must have an address in order to be able to send and receive mail. The analogy in the networking is if you would like to be on the internet and known and addressable on the internet, you can send and receive, you must have a public IP address. It doesn't have to be you, but the place where you are in must be connected to the internet. Where would you get that? At your home? The one company or service provider or telecom company that is providing you the internet connection will provide your router with a public IP address. So that's how it works, and there is no deviation from this. Public IP addresses, they are visible on the internet. So anyone online on the internet can reach it unless you put some security measures to block incoming traffic. There is no 2 persons or 2 homes or 2 entities globally on the internet that would be using the same IP address. So it is globally unique. So no 2 public IPs are the same anywhere in the globe. And it is used for communication, for websites, for servers, for emails. All your computer use on the internet or laptop or iPhone use on the internet needs public IP addresses. And it is routable. The internet, wherever you are, as long as you have a unique public IP address, they will be able to get to you and they will be able to send your traffic wherever you want to send it on the internet. the IP addresses. Now it's not random. What you are telling me is the service provider, the telco companies, the governments are the ones that have the blocks of IP addresses and they are in control. Otherwise, it's going to be a mess. So IP addresses must be assigned and managed globally by official organizations. And this is called the IP address hierarchy. And these are existing in the different continents and in different countries as well. So IP address must be unique. Otherwise, if two entities had the same IP, the internet wouldn't know where to send the data. And this is how the hierarchy looks like. So IANA, and then in Africa, in Europe, in Asia Pacific, in Latin America, and then we have resource allocation hierarchy, and then we have the service provider, and then the national IP registries in each country. So in each country, the continent responsible ones are going to deliver blocks to the countries, and then the countries are going to deliver the blocks to the ISPs, and each one has a record of what is used and what is not used. And that's exactly the analogy with plate numbers. When you go into a country and you get a plate number, the plate number may have the city name or the city code and then a number. The phone system, same thing. You have the country code, area code, and a unique number. The exact same thing happens on the internet. So IANA is the Internet Assigned Numbers Authority, the top level body, and that's in the US. And then you have the regional internet registries, which will manage the different parts of the world. And these are ARIN, North America, RIPE for Europe and Middle East, APNIC for Asia Pacific, LACNIC for Latin America, and AFRINIC in Africa. And then we have the national internet registries inside each country, and then the internet service provider. What do you get out of all of this lecture? The message is to be on the internet, either you yourself, if you're using your phone in the street, or the place where you are must be connected to the internet. To be connected to the internet, that means you have public IP addresses that are registered and they are assigned to you legally, and you are authorized to use them, and these are unique. They will not exist anywhere else on the globe. What are the private IP addresses if we have already discussed what are the public IP addresses? Private IP address ranges are IP addresses that you can use without having to go and ask for assignment or authorization from anyone. And these are called the RFC 1918, the request for comment. There are private IP address ranges, and these IP addresses are not routable on the internet. So you cannot have your wireless router at home be connected to the ISP using a private IP address. That's how it works. Or that's how the norm is. If you have your home router or your phone configured with a private IP address and you try to connect to the internet, it will not work. So they are not routable. The private IP ranges, they are not routable on the internet. They are not visible on the internet. So they have to be hidden behind public IPs. So they won't work directly on the internet. They have to be using a means that is connected to the public internet to be able to access the internet. They can be used freely within private networks. So the reason why they came up with the private IP address ranges is because they were afraid they will run out of the available IPv4 public IP address ranges. So because they were afraid of that, they said, okay, we cannot assign an IPv4 public IP for each device. At my home, for example, let's say I have 4 family members, and each of us has an IP phone, and each of us has a laptop. And my younger kids, maybe they have iPads, and then I have the smart TV, and maybe my fridge is a smart fridge IoT that also has an IP address. So I need in my home easily about maybe 12, 15 IP addresses. If each one of them would have been requiring a public IP, that means we would have been done with all the available IPv4 public addresses long time ago. They said, okay, fine. Let's now assign private IPs. Anyone can use it inside their homes, inside their offices, for printers, for fridges, for smart TV, for whatever. And that is for networking within the place. You don't need the internet. If you need the internet, then you have to put a gateway that will have a public IP, and that will be the bridge to the internet. So here's the example. In my home, I have these devices, and these are going to take private IP addresses. One would tell me, okay, can we prove it? Yes, I can prove it, but just hold on. And the Wi-Fi router coming from the telecom provider, it will have a public IP. And that's how it works on the internet. How does the conversion happen from private to public on the way out? And when the response comes back to the router, this will be addressed to the router public IP. How does that get converted back to the correct IP address, the private IP address? Who does the conversion? That will be your Wi-Fi router in this case. Private ranges 10.0.0.0/8, and that's a class A. 172.16.00/12, so 172.16 and 17 all the way, 18, 19, 20, all the way to 31, they are included in this range. This one will give me 16 million IP addresses. This one will give me 1 million IP addresses in each one of these networks. So I have 172.16.00/16 all the way to 172.31.00/16. This is for large, medium networks, and then this is for homes and small offices, 192.168.00/16. Here is the interface IP address that I have on my computer, on my Mac right now, 192.168.68.108. Let's compare that, contrast this to this, and you'll find that I have been assigned through Wi-Fi from my home router, the Wi-Fi router at home. I have been assigned this IP address, and that belongs to RFC 1918. And if you check with ipconfig or this command, if you have Mac or Linux, try this, or IPA if you're on Linux. And then in my case, this is the IP address. Check in your case. If you have Windows, go to CMD and type ipconfig and hit enter. Of course, here it's not complete because I have to do ipconfig get interface address, and that's how the IP address. So that proves my theory that I am getting a private IP address, but on the internet, I am seen as if I am the IP address on the router. And that's how I communicate with the internet. So what's the conversion process that happens on the router? This is called network address translation. And sometimes it's more specific. It's called port address translation. When we discuss the IP ports later on, we'll come back and revisit, and I will explain to you what PAT is. But for now, the IP address that is on my machine, which is a private IP address, when the message, which is going, let's say, to CNN.com, when this message reaches the router will say, okay, now I know it is coming from this IP address. Let's say that's the IP on my machine, 192.168.68.108. I'm going now to remove that as the source, basically, and I'm going to claim that I am the source. Why? Because your IP address cannot go to the internet, and the internet will never be able to deliver the response. But my public IP address is a registered one on the internet, and the internet knows how to take my traffic forward to CNN.com and knows how to get the response back all the way to here. And I promise you, when I get the response, I'm going to do the opposite, and I'm going to deliver the message to you. We're going to talk about this more later on. If a device with a private IP address inside the private networks needs to communicate to the internet, then the router will use network address translation and swaps the device private IP address for the public IP on the router. That's the only way this can work on the internet. Let's do a quick demo using a Windows client or a Windows PC in order to show you how to start the command prompt in Windows, and also to see the private IP address that we will have in that machine. So I'm using a Windows machine in AWS to simulate the client. So this is the public IP address, as you can see here, and this is the private IP address. So this is as if it is your laptop. First of all, how can I get to the command prompt? If I go here and I do a search, and then here in the search criteria, I just type CMD. So that's the command prompt window that we need to open. So when you open the command prompt, what you will see is this prompt, and we can do from here ipconfig. That will show what configuration we have. And as you can see here, this is the IP address, the private IP address, which exists right here. So that shows you that it is the same. Now it's time to talk about how do routers actually work. What we have not done yet is configuring, or at least understanding, how should the router be configured? How should the router be told how to use or find out the best path to a destination? That's what we are going to do in this module. So we'll know the AWS infrastructure. We'll know what is an AWS VPC, or virtual private cloud, or virtual data center. We'll know how to create subnets and route tables or configure routing inside a VPC. We'll also know how to connect a virtual private cloud or a virtual data center that you build in the cloud to the internet. And then you can launch applications or websites and it will be accessible from the internet. We will learn what is the difference between a public subnet and a private subnet from the AWS viewpoint. We learned before about public IPs and private IPs. Now we are going to learn about how to apply that into the AWS cloud inside your virtual data center. We will learn how the address translation happens. So we're going to discuss network address translation as well. We are going to learn more about the IP packet headers, and that would be a lot of topics that we are going to look at. The most beautiful thing is it's not going to be designing an IP scheme on a piece of paper. We are going to go on the AWS cloud and we are going to implement that, and you are going to build your own virtual data center in the AWS cloud by the end of this module. All right? So hopefully that makes you excited, and let's go ahead and get straight into it. Okay, so IP routing. How does IP routing work? Very important to understand. From what we have learned before, devices on a local area network, if they need to communicate among themselves, and as long as they are in the same VLAN, they don't need a router. But if any device would like to communicate externally with other sites that don't belong to the same IP network, they have to use a router for that. Only routers are capable of forwarding traffic between networks. Also, we learned that if we had two VLANs, red VLAN and a blue VLAN, for instance, and we would like to route between them, so in that case also I need to have a router that connects between them. It will have one leg in the red VLAN, one leg in the blue VLAN, and that router will route between them. If the switch has a router or a router functionality, if it is an intelligent switch, sometimes they call it a multi-layer switch. So the intelligent switch will have a built-in router, and it can do that internally. But anyways, going from one subnet to another subnet, if they are in the same LAN but on different networks, or if it is from a local network to a remote network through a wide area network, there has to be a router used. There is no way around this. All right? When one device tries to talk to a different network or subnet, it can't go there on its own. It needs a router. And the routing is done, or the routing is done by devices called routers. All right. Routing is the process of selecting paths inside a network to forward traffic between hosts. So, if this camera is trying to send a video footage to be saved somewhere in storage in the data center, for example, then it has to forward that traffic to the router, because now it's going outside the LAN. It will cross a subnet in the WAN and another subnet to get here until it makes it to the storage. So it will cross multiple subnets, so it needs a routing decision to be made here. What is the best path to forward this? When it gets to this router can send it in or can send it to the internet. How would it decide? Based on the routing, it will send it inside to the data center, because it knows that the storage IP address is towards the data center switch. The data center switch will know where to send it, and it will send it in. So I have a routing done here, and a routing done here. Each one of them will do a decision, or will make a decision based on its knowledge of where that destination could be and the best path to get to that destination. In order to do that decision, the routers will use what we call routing tables. Sometimes they are called forwarding tables, and algorithms in order to determine the most efficient path to forward traffic. So if the router has multiple ways to get to the data center on the other side, then which one to use? Then there has to be an algorithm that will enable the router to find the best path. When thinking about the routing tables or the forwarding database, the best analogy is think as if we are now configuring a GPS on the router to define directions to destinations. So the routing table is exactly like a map or a GPS on the router. Each router needs to build a routing table or a database of known destinations and how to reach them. When a router receives an IP packet, it will follow the process below. Based on the existing routing table or the forwarding database on the router, when the packet is received into one of the router ports, one of the router interface, let's say this one is connected to a switch. All right. And then we have a PC on the switch or a laptop that is trying to send something outside the network so it gets to the router. So that message is called a packet. That message from the laptop to the router, each one is called a packet. So packet is received. The router will receive the packet. It will check who is the sender and where is the destination. Now it would look at the destination and then check the GPS, check the routing table that it has. Do I know where that destination is? If the answer is yes, then where should I forward it? And then it will send it to the IP address or the interface. So here, for example, destination 10.0.0.0/24. If you want to get to it, send it to the IP address 100.2.1.1, which is a connected router or a connected network. If you don't know where it is, then by all means, drop it. Don't guess. The router will never guess. If it knows how to get to the destination, it will send it towards the destination. If it doesn't, it will just drop it. And that's it. And you will not get an error telling you that I have dropped it because of such and such. You will be waiting on your browser trying to get to that website that is hosted, and things are not working because you haven't configured your router properly. Routing tables, who is going to be building them? Who is responsible to populate that database or the GPS? Who is responsible to put the data inside it? So the routing table or the forwarding database can be configured manually, and this is called static routing. If your infrastructure is simple, small, you can do static routing, and that means you are configuring the routing manually and you are building the router database manually. That is an option when we are talking about a small scale infrastructure. And we're going to do manual configurations, by the way, in our demos in AWS. If it is larger than that, if I have two routers, all right, and let's say this router knows about other 3 routers, and this one knows about another 4 routers. And each one of these routers knows about multiple routers. I have so many networks now. I mean, this could be like a mini internet. It doesn't make sense to go ahead and build the information in each one of these routers to let it know the possible destinations and how to get to them. It doesn't make sense. You will not be able to maintain it. From an operational perspective, it will be a nightmare. And also it will be prone to mistakes. So what do we do then? There is something called routing protocols, dynamic routing protocols. For example, Border Gateway Protocol is the dynamic routing protocol used on the internet. Any routers on the internet, they communicate, especially the big ones, the backbone ones, they communicate using BGP because the internet table size could be in the multiple gigabytes, if not more than that. So what do? We enable BGP here, we enable BGP here, we enable BGP on the routers, and then the routers, each one of them will start to share the networks that it knows about with all the neighbors. So this will also share their information, and that's how they start to populate their GPS, their routing database, the routing table, their forwarding database dynamically. Either way, a router must have a forwarding database, an accurate one, either manual or dynamic, in order to be able to forward traffic properly. The router does not come pre-configured with a route table. The router comes from the manufacturer, and then you place it in your infrastructure, and you have to configure it and customize it according to your infrastructure needs. So this is something that you will need to do. So it requires dynamic routing protocols to be configured. Open shortest path first is an example, and border gateway protocol is another example. When you work with AWS, you will need to know about BGP if you would like to scale connectivity and configure wide area network and enable dynamic routing protocols and all that. But you can live with a static if that is sufficient. All right. So the routing table will be populated either dynamically or statically, manually, and then the flow chart or the decision-making process will work. Okay, there is a concept called default route or default route. What is that? In the previous examples, we looked at this forwarding table, and the decision was either I know where the destination is so I can forward it. That's the router decision based on its forwarding table or route table. And if it doesn't know, it will drop it. This is not practical. Let me tell you why. Let's say, for example, this router is the one connected to the big I, to the internet. And this is the LAN that will send the traffic, or maybe the wireless LAN in your office that is connected to the router. And then the router has this table. And based on that, it will forward to the internet. So when it receives your message, it will look at where it is supposed to go, and then we'll check if it has an entry for that destination, and then it will send it out. But this is not practical. On the internet, we have millions and millions and millions of networks and websites. Who is going to configure all of this here? I mean, it's my home office. I'm not going to run BGP as the dynamic routing protocol on my small router because it doesn't support it. It cannot process it. It cannot maintain the full internet table that requires gigs and gigs and gigs of storage on the router. So this mini router cannot store it, the wireless router. And at the same time, I'm not going to go on the router and start configuring the 10 million websites that I may reach out to or try to connect to throughout my life. Nobody does that. So what's the alternative? To avoid having to fill manually a large routing table, and even if you try, you will not be able to make it because there are millions and millions of networks. And if you want to run that dynamically, the router does not support the dynamic routing protocols. And even your ISP will not provide you any BGP information because you are just a home user. They would do that if they are connecting to a university, if they are connecting to a corporate like IBM or one of the big companies, they would give you the full internet table. But for you as a home user, of course not, and your router cannot support it. Way out of this is we use something called the default route. And we are going to stretch the flow chart a little bit. A default route is basically to tell the router, if you don't have a specific entry for this destination, please send it this way. So it defines a path to the router in case if it doesn't have an explicit entry in its route table for a specific destination, how to deal with it. Don't drop it. Please do this instead. So default route is a special route table entry that can be used as a last resort, a last choice to forward a packet only if there is no other specific entry in the route table to be used. So this is like your plan B. If you can't find a matching entry in the route table, please go for plan B and use this path. So how would that look like? So in a route table, there will be an entry like this, and sometimes it's written as /0. And that means to the router, here are the specific entries. If you get anything going to an IP address within this range, please use this entry. If you have anything headed into this range as a destination, then use this entry. If you get a destination IP address in a packet, so it is going to an IP address that does not belong here and does not belong here, do not drop it. Instead, forward it to this IP address. And the flowchart would be, a packet is now received. Is the destination known through a specific entry? If yes, go ahead and forward it according to the entry. If no, do not drop it. Is there a default route, a gateway of last resort in the table? If the answer is no, then go ahead and drop it. There is nothing you can do. But if yes, then please forward it according to the details in the entry. So this is very important, and it helps save effort and minimize the size of the root table immensely. In your home office, you have your own local network that doesn't need the router. But then if you would like to go to the internet, then the router should send it to the ISP through the link, and the ISP should deal with it, right? So you have only way out to any destination. So in that case, on that router, it's enough to have only the default route. 0.0.0.0, send it on this interface to the ISP and let them deal with it. Hopefully this is understood. We are going to look at an example of how we populate that, and we include the default routes as well in order to cement the knowledge and clarify any ambiguities. Let's have a look at an example, a practice on how routers should be configured, and we'll assume we are going to do that manually. How we can configure that, or what information we need to prepare in order to configure on the router when given access to that router. So we have this example. We have a local area network somewhere, and then we have a data center, remote, it's not nearby, and we have already installed router A and router B in the LAN side and in the data center side respectively. And we also work with the telco provider to have a wide area network connection between the two. So this router B, has now a WAN connection to router A and has an internet connection here. Also, we have here a subnet configured, routing subnet configured between the data center switch, the intelligent switch, and the router. And this is going to be the 10.0.255.0/30 subnet, has 4 usable IP addresses. .1 is on the switch and .2 is on the router. So this is the IP here and this is the IP here. All right. The CIDR block on this side is 10.0.0.0/16, out of which we are cutting subnets. So we're going to provide the application segment, the subnet 10.0.20/24, and the database is going to be 10.0.10/24. And you have this subnet as well. All right. For the WAN side, we have worked with the telco provider to use the subnet 172.18.00/30. .1 is on router A, so this is the IP address right here, and .2 is the IP address right here. On the LAN side, the CIDR block is completely different. So this is 172.18, this is 10.0, and this is 192.168. The 192.168, we are going to allocate .1 to the router and other IPs for the other devices. So what's needed now? We need to prepare the routing table. We need to include all the required details on router A and on router B. And that should include all local routing within the data center, from the data center to the LAN, from the LAN to the data center, within the LAN, and from the LAN to the internet, and from the data center to the internet. Oh my goodness. How can I prepare all of this information? Looks tricky. It's not. So let's look at the router A side first. What do we need to configure on router A? What does router A need to do? What are the possible destinations that it will have to forward traffic to? This is exactly what we need to configure in its routing table. So router A knows about the local area network, right? So this is number one. It also knows about the wide area network. And it should know how to get to the data center. Also, it is required that we need to know through the router how we can get to the big I, to the internet. So let me just write it as an I here. So here we have 4 entries or 4 decisions or 4 possible destinations from the local area network to the outside, or from the outside to the local area network. So how do we define that on the routing table? The routing table usually have at least 2 entries. One is to define which destination and how to deal with it, where to send it next. Next hop means what is my target to get to that destination, or what's my next hop? What's the next device or next IP address that I should send it to in order to get closer to the destination? So first of all, let's do number one. It knows about the local LAN. Through what? Through the LAN interface. So the interface which is configured here and it's on the switch. This interface, depending on the router type and model and all that, will have a name. It could be LAN 0, it could be Gigabit Ethernet 0, it could be Gigabit Ethernet 0/1/2, whatever the name is. This is irrelevant now. The LAN interface is how the router A can get to the LAN. Is that right? Yes. So 192.168.1.0/24, which is the LAN IP address range, and that is reachable through the local area interface on the router. All right, so that's number one. Number two, 172.18.0.0/30. How can the router A get to this subnet? This is through the local WAN interface, and this will also have a name. It could be also Gigabit Ethernet, it could be something else. Whatever the name is, you can get to it through this interface. All right, so these are the local networks that it's directly connected. How about getting to the data center, and how about getting to the internet? So getting to the data center, that has to go through the wide area network to router B, right? So my target, my enabler, my helper to get to 10.0 has to be router B. How can I talk about router B here? I know its IP address on a shared subnet. I have .1 and the router has .2. So to get to this network, I need to go through 178.18.02, which is router B interface. How about if I want to go to cnn.com or dolphinedacademy.com? How am I going to do that? How can I get to it? Again, through the WAN, through router B, because we don't have a direct connection to the internet from the LAN. So we have to hop through the wide area network to router B, and then we can go to the internet, right? So how can I write that? The internet has so many websites and so many IP addresses, and I'm not going to list all of them. Then we can take advantage of the default route, and I can tell the router, hey, if there is anything else other than the ones specified, any other destination other than the ones specified, please send it to same thing to router B. So now we have everything identified on router A side based on the requirements we have right now. All right, let's go ahead to the other side, to router B. So in router B, what do I need to define? I need to define this subnet, which is between the data center switch and the router. That's number one. I need to define the local area range in the data center, the 10.0.0.0/16, which is behind the data center switch. So I have to come through the data center switch in order to reach any one of these subnets. That's number two. So number two is the range, or let's just write it here. Number two. Number three, I can get to the internet, to the big I, through router B, through this interface. And let's assume that the opposite router interface in the ISP, so this is .1, let's assume that it is also 122.54.2 on the other side. What else? The WAN connection, the WAN interface. I know about this subnet, right? How? Through this. So this is number 4. So we have So this is number 4. And also, I need to respond to any requests coming from the local area network. So this is number 5. So I need to define all of these here. So we'll have 5 entries, not 4. Let's do it one by one. How can I get into the 10.0.0.0/16, which is this CIDR range? I can get to it through the data center switch IP address that shares with me a subnet. So I can get to it through 10.0.255.1. All right, how can I know about the 10.0.255.0 subnet /30, which includes .1 and .2? Well, that is directly connected through my LAN interface. How can I get to the 172.18.00/30? That's easy. That's through my WAN interface. How can I get to the other side, to the LAN? Oh, okay. In that case, if you would like to get to the LAN, then I have to go through my colleague router A. And by the way, I share with router A a subnet, and he is .1, or it is .1 on that subnet. How can I get to the internet? Oh, okay. Anything else not explicitly defined, then I can get to it through 122.54.2, which is the IP address we assumed that it is on the router at the ISP connecting to our router. So this needs to be configured manually on the 2 routers. And here manually is enough because it's a small network. Or maybe I will enable BGP configuration between the 2 routers and just enable that, or OSPF, or any dynamic routing protocol. Either way, this is the minimum that I need to see on router A, and this is the minimum that I need to see on router B. All right? Hopefully this is clear and it clarifies how do routers take decisions. So in this case, if there is anything unknown destination on router A, when the traffic comes from the LAN, it will be sent to router B. Router B, please deal with it. If it gets to router B, and if it is not part of these entries, then it will say, okay, this is the right entry to use the default route, and I'm going to send it to the internet and let the ISP deal with it. So we have 2 default routes, 1 in each routing table, and the use is clear. Let's talk about what an IP packet is. Let's get deeper into an IP packet and understand what information does it carry with it. In order to understand that, the message in IP networks, or networks that use TCP/IP, is called a packet. So let's take a step back and do an analogy first. If John Smith, who lives in 32 University Street in Boston, Massachusetts, in this zip code in the US, would like to send a mail through an envelope and a stamp, like a legacy mail, to Sarah, who lives in this address in Egypt. What would John do? John would write on the envelope, of course, after a stamp is used, John will say from my name, my address as John, and it's going to, and the details for Sarah. And that's how it gets correctly to the right address through United States Postal Service and then through the Egyptian Post. The response will be the other way around. It will be from Sarah going to John Smith, and this will allow it to be delivered properly. So this is in postal systems. Now, what about in networks? So the IP packet is like a sealed envelope as well, carrying the digital mail or the digital message from one end to another, one computer to another. So if I have a user connecting to the internet, the user's IP address or the user's home router public IP address is 100.2.55.3. It is not 10 dot, and it is not 172.16 to 31, and it's not 192.168. So this is a public IP address, and this is not a private IP address. So whether it is on the home wireless router or on the user's phone, and the user is connected to data, to the internet, the user would like to get to a website, and the website IP address or the server IP address is 205.111.37.86. Again, this is a public IP address. Of course, I'm not allowed to use these IP addresses because they must have been assigned somewhere on the internet. But I'm just showing you an example of what might be a public IP address just for the use case. All right, so I have no right to use these IP addresses in any network that I build, because these are public IP addresses and they have to be allocated according to the registry, to the hierarchy of the public IP address control system organization across the globe. What am I trying to get to? Comparing from the postal office example, what if we need to send a digital message from this IP to this IP? What happens? Then an IP packet has to be created, and the IP address of the source must be included as a from field, and then the destination or to field will carry the destination IP address. So it will look something like this. I'm just trying to show it as an envelope. It's not an envelope. So it has to show the source, where it came from, which is this IP address. And it has to show the to, or the destination address, which is the other side's address. And since both are public, that means the internet will be able, router by router, to carry that message until it gets to the server. Great. What about the response? The response, like in the postal and mail system, it's going to be reversed. So now it's going to be a message from this as the source to this as the destination. And that's why it will be shifted the other way around. So the from is now the server going back to the user. So it's exactly the same. This is source IP and the destination IP. This is not the message. The message is inside the envelope, and we call it the payload, or the data within the message. So what is this then? These are like the stamp and the envelope. At the end, when I receive the message, I'm going to discard the envelope. I don't need it. It's not anything that I need except for John's address or the other party's address. And as soon as I write the new envelope, I can discard the old one. So these are called headers. The IP packet includes the actual message data being sent, and which is called the payload inside the envelope. And the IP packet also includes the IP addresses and other details, and these are called the headers. So the message sent is not only the data you want to send, but also other required information in order for the message to be delivered properly. These are called headers. So when you hear the term headers, please know that we are talking now about IP addresses and other details necessary in order to deliver the message from node A or host A to host B on an IP network. All right? Since we are going to apply all our hands-on in the AWS cloud, let's find out what is the AWS global infrastructure and what does it consist of. The AWS cloud globally consists of a number of what they call geographic regions. A region is an AWS presence, a group of data centers that are in one country. And some countries, they have more than one region, like the US, for example, it has 4 regions. And a lot of other countries, they have only a single region. When the AWS business grows in one country, they may consider building other regions. At the moment, they have 38 plus geographic regions. How can you find out the details about this? You have this link, awsamazon.com, about AWS Global Infrastructure Regions and Availability Zones. And if we go to that link, as you can see here, this one lists the up-to-date information about the AWS regions. So this is 38 at the moment and 120 availability zones. And you can go continent by continent, and then you will be presented with this globe view that will show you the regions in the area or the country or the continent that you have chosen. All right, so you can acquaint yourself with this, play with it a little bit to find out more information. That is not important to memorize because it only shows that AWS globally has multiple regions. As we mentioned, 38 plus geographic regions, and each region has 3 or more availability zones. The availability zone is 1 or more data centers clustered together and interconnected with very high speed links. The region may have 3 availability zones, and some regions has 6 regions like the one in North Virginia. We have 120 availability zones at the moment and increasing. And as I mentioned, the availability zones in one region are interconnected via high-speed links. So region 1, for example, availability zone 1, 2, 3, and they have high-speed links among them. Same for region 2, same for region N. And now we need to understand what is the availability zone. So an availability zone consists of one or more interconnected data centers, like this. So if we look at one of the availability zones and zoom in into it, you will find that one or more data centers, now we're talking about the data center that we know, and they are interconnected with very high speed links. And these data centers, they could be, I don't know, 10 kilometers, 20 kilometers, 50 kilometers away from each other. And the point about having more than one data center in an availability zone and then more than one availability zone in a region, the whole point is high availability. So now if I create 3 virtual machines in the same availability zone, chances are they're going to be created in different data centers. So if one of them gets busted, the other 2 will be alive. And that's why it's always recommended when you create workloads, applications, databases in AWS, it is recommended by AWS to establish it in multiple availability zones, not in a single availability zone. If you do this, if you have your workload or application or virtual machines distributed across more than one availability zone, then in the eyes of AWS, you are highly available. Your workload is highly available. All right, so that's enough about the AWS global infrastructure. Next, we're going to introduce what is an AWS VPC, the virtual private cloud in an AWS region. So let's now go ahead and discuss what is an AWS VPC, a virtual private cloud. That is your virtual data center that you can create in a minute in cloud computing or in a AWS cloud, to be more specific. So a virtual private cloud, building your own isolated virtual data center in the cloud. So the VPC is a virtual data center in the cloud which is isolated from other VPCs by default. The VPC client or the customer who owns the VPC, who created the VPC, has full control over the VPC or the VPCs. You can create more than one if you want. And a VPC is confined to a single AWS region. You will never see a VPC stretching between 2 regions. It's either in region A or B or C, but it's not going to be half in here and the other half in another region. A default VPC is created automatically in each AWS region when an AWS account is created. And the VPC spans all the availability zones in a region. What does that mean? What does it mean when I say that a VPC stretches across availability zone? That means in that VPC or virtual data center, you can have virtual machines and workloads. We call the applications and the data that you add and all that a workload or an application or a database, whatever that is. You can host it in any of the availability zones in that region. As if we are saying that you can control where in the region to place your workload inside the VPC. It's up to you. You can have a virtual machine for application A in availability zone A, and in availability zone 2 or B, and in availability zone C. You can have databases in availability zone A only. That's up to you. You can have some security virtual machines also available in availability zone 2 and 3 only, but not in 1. It's up to you. Creating a VPC means you have the permission to create a workload, a virtual machine, anywhere in the region, in any of the availability zones. Why is that an advantage? Because it allows you to have more availability of your applications. I can now have them or have my e-commerce website in 2 availability zones in the region. If one gets busted for whatever reason, I have the other one. And remember, we mentioned that the availability zones are far away from each other, and each availability zone is a cluster of 1 or more data centers interconnected with very high speed. The availability zones themselves are also interconnected with very high speed. So hosting your application or data or website in more than one availability zone gives you an advantage of being more available, and the uptime will be higher and your customers are going to be happier. So what are the components of a VPC? When I build a virtual data center that takes me a minute or less, as you will see, what are the components that I can create in a VPC? First of all, you can't have a VPC without a CIDR block. There has to be an IP address block of which you can divide subnets for the VPC. And there is a router configured automatically, and it connects to all the subnets that you create within a VPC, and it guarantees that they can all talk to each other. Then you have the route tables, which will tell the implied router for each subnet what to do with the traffic coming into the subnet or going out of the subnet. We're going to discuss that in detail. If the VPC needs to connect to the internet, that only happens through the Internet Gateway, or abbreviated the IGW. Now, for security, we are going to discuss that in subsequent modules. We have security groups and network access control lists, which are virtual firewalls, but we'll discuss them when we get to them. So let's start with the CIDR block. You cannot have a VPC without a CIDR block. It's all IP communication inside the VPC, so there has to be an IP address range. And the VPC subnets are created from that CIDR block. So that's the extra large pizza out of which you can break down slices, which are going to be your subnets. And the CIDR block size can be anywhere from as small as /28 to as big as /16. So this one gives you a total hosts of 65,000 plus, and this one gives you only 16 hosts. Of course, this is not something that you would want to do unless if you are testing something for 5 minutes, 10 minutes, half an hour, and then you will switch it off. Default size for CIDR blocks in AWS are /16. Can I have /15, /14? No, that's not allowed. All right, so the VPC stretches across all availability zones in one region, and the VPC is confined within one region, cannot stretch beyond the region. And I can have one or more CIDR blocks actually, but at least one. And the subnets are chunks out of that CIDR block, and they can be in different availability zones. Let's now discuss subnets and route tables as far as a VPC goes. So let's start with subnets. We can configure multiple subnets per VPC. As big as your original size block of IP addresses, the CIDR block, you can create as many subnets as you want. So I can have one subnet in availability zone 1, one subnet in availability zone 2, and I can have more than one subnet per availability zone if I want. As we mentioned that the VPC is confined within a region, cannot stretch beyond a region boundary. Similarly, a subnet cannot stretch outside of an availability zone. So the subnet and all its hosts must be within the same availability zone. So the VPC is confined to a region, the subnet is confined to an availability zone. So can I configure a virtual machine here and assign an IP address from subnet 1 in availability zone 2? The answer is no. If subnet 1 is in availability zone 1, all the hosts in that subnet must be in availability zone 1 as well. Can I have more than one subnet per availability zone? By all means, yes. So now we have the subnets, but we need the implied router. You don't need to configure it. It will be created automatically, and it will connect to every single subnet that you created or will create in the future in your VPC. So nothing needs to be done on that implied router except for, if you want, create route tables. The implied router will forward traffic among the subnets in a VPC, but it also will have the traffic, or will help the traffic forward the traffic that is going outside the VPC, or traffic coming from the outside to one of the subnets in the VPC. So basically, this is where traffic can roam around within the VPC, go out, or traffic can be received through the implied router. Routing between subnets within a VPC is enabled by default, and you cannot disable it. We're going to look at that. The implied router by default will have one routing table, and the routing table would say all the subnets within the CIDR block are local. I know how to get to them all. So all the routing among the subnets is enabled by default, and you don't need to do anything about it. This router is fully managed by AWS. You cannot access it, you cannot log into the router, and you cannot change configuration in the router. All you can do is you can play with the root tables that are available to you. Root tables, as I mentioned, each VPC has a default root table. It's called the main root table. That root table can be used by more than one subnet at the same time. So if I decide to keep only one root table in the VPC, all the subnets in the VPC are going to use it. The router can hold a separate root table if required for each subnet. So I can have RT1, RT2, RT3. Or you can have one root table and all the subnets are going to use it, so the router will use the same root table for all the subnets. Is that in your control? 100%. You can create custom root tables as required, and you can assign them to the subnets that you want, and we are going to do this. The subnet can attach to only one root table at a time. So you can switch the association of a root table from one subnet to another. So let's say this subnet, now I have it with the green root table. I can decide to switch it to the gray root table or to the blue root table. But at any given moment, it will have only one root table. That means when traffic is going into the router from the subnet, the router will consult the root table for that subnet and find out how to forward it. And we're going to do that in the demo as well. All right. So how can we provide internet access to the VPC? Through what we call an internet gateway. So the internet gateway is how a VPC can communicate with the internet. So I have a VPC with subnet and implied router. I have to add the internet gateway, otherwise the subnet cannot get out to the internet. And I can have only one internet gateway per VPC. So it is fully managed service. You cannot access it and log on to it. And there is only one that you can create and attach to the VPC at a time. I can remove it and attach another one, but this is a fully managed, scalable, highly available service from AWS. You don't need to worry about that. In order for a subnet to use the internet gateway, its routing table must have an entry pointing to the internet gateway, like this, for example. Any IP address not specifically listed in the root table, please send it to the IGW. So now it's a good time for us to have a look at all these components in the AWS console. So now it's a good time to stop and start to show you the different things that we have discussed in a VPC. The VPC, the subnets, how it stretches across availability zones, the root tables, the internet gateway. And the best way to do this is to go ahead and create a custom VPC and create subnets and create the internet gateway, attach it to the VPC, and look at how we can do all of the stuff that we have talked about, how we can create different root tables and so on. So first, we're going to do a walkthrough. I'm going to show you an AWS VPC that is created by default by AWS. And this is true for anyone, anywhere in the world. When you create an account in AWS, they will voluntarily create a VPC for you with the same specs in all the enabled regions in your account. Usually there are 16 or more regions. So here is what we need to create. So this is going to be a custom AWS VPC. A custom one means that is a VPC that we are going to decide how it will look like. So what do we need to do? We need to create the VPC, and the name of the VPC is going to be custom_VPC. As we mentioned before, a VPC must be confined to a region. So here they are requesting that we create it in Ohio, in US East 2. This is the code name or the nickname of that region. We need to create 4 subnets in the designated availability zones as shown below. So we're going to create subnet 1 in US East 2A. US East 2 is the name of the region, and A is availability zone A. The CIDR block provided for the VPC is 172.31.0.0/16. So we're going to use that as well. Subnet 1 that we are going to create in availability zone A in US East 2 is going to have the block range or the IP address range 172.31.00/20. Please note that this is 20 and this is 16, which means this is a subnet from this block. Then we are going to create subnet 2 in availability zone B in the same region, and the IP address range for that is going to be 172.31.16.0/20. Subnet 3 and 4 are going to be .32.0 and .48.0, and both of them are /20 as well. Then we are going to create and associate the root tables as shown. So we have root table 1, the green colored one, and then the gray colored one is going to be root table 2, and then root table 3, 4, which is the blue one. Root table 1 will be associated with subnet 1. So subnet 1 must be associated with root table 1. Subnet 2 will be associated with root table 2. Subnet 3 and 4, both of them at the same time, will be associated with table 3, 4. Remember, we mentioned that at any given time, a subnet can be associated with only one root table. But nothing stops me from associating two subnets with the same root table at the same time. We are going to reference this again, but let's go ahead and do the walkthrough in the AWS console for the VPC. We are going to look at a default created one, and then we are going to move on and create our own. The AWS management console, and I'm in the VPC dashboard. So if I go to console home, this is the page that you will see when you log in to the AWS account that you have. Then I'm going to type VPC and click on this. So this is going to take me to the VPC dashboard. Let me maximize that a little bit. And as you can see here, you can select the region that you are going to be in. So if you would like to travel from North Virginia in the US to Mumbai in India in 1 second, all you need to do is to click here. So you are now traveling faster than the speed of light to India from the US. Now, if you are done with what you are doing here and you would like to go to Germany, why not? There are no airfare tickets, and there is no time delays, and there are no airports involved. And this is the beauty of the cloud, that you have a management console, you have a portal, you have an orchestration and management account that can allow you to control your infrastructure and deploy your infrastructure across the globe from one central location, from your office, maybe with your pajamas, and you can monitor all that centrally as well. All right, so Europe, Frankfurt. Let me use one region that I think I have never used before. So let's try Ireland, for example. This is a relatively new account, so I'm sure many of the regions I have not used before. So this is the navigation pane for all the VPC feature and configurations and all that. And here you can see that we have VPCs, subnets, root tables, internet gateways, and so on. And here you have a summary of what you currently have configured. So VPCs, I have one. I have never touched this region before. So where did this come from? This is the automatic VPC that is created on your behalf when you create the account. And you get one in every region. Subnets. I have 3 subnets. And again, because Ireland has 3 availability zones, and that's why it is showing 3 subnets. If you click here on this side, zones, here you'll find the availability zones in each one of the regions. So for example, I am in Ireland, this one, and it shows me that I have 3 availability zones. If I click on this, it will tell me this is what I have. So I have EU West 1 AZ1, EU West 1 AZ3, EU West 1 AZ2. And opt-in not required. So you are already into that region. You don't need to opt in to use the region. It's already enabled. Okay, the one that has the most availability zones is the North Virginia one, and as you can see, it has 6. Some have 4, and this one, United States, California, has 2. This is the least, I think, among all. Yeah, it's the least. The rest, as you can see, they have. So now I understand why I have 3 subnets. This is because I have 3 availability zones, and what AWS does is it creates the VPC by default automatically, and then it will create for you 1 subnet in each of the availability zones. So let's go ahead and look at this VPC. So what's the name of the VPC? There is no given name. I can click here and I can add a name if I want. So for example, I'm going to call this default. I didn't create it. This is the VPC ID, and this is a unique ID allocated for each VPC when it is created, and this is allocated by AWS. You don't need to worry about it. The VPC is available, and if we switch here, you will find that this is the CIDR block 172.31.00/16, and if you click to the right, we have a main routing table created by default. I have network ACL, and here it shows you that this is a default VPC, and this is the account that I have. So resource map, if you click on this, it will show you that. Let me just drag this a little bit to the top. I have the VPC, and I have 3 subnets, and all 3 subnets are attached to the same root table, and they are connected to the internet gateway. So these subnets are accessible from the internet, and the internet can access them. But right now, I don't have any virtual machines or anything, and that's why I cannot access the internet, and nothing can access me as well, because there is nothing to connect to. There is nothing to respond to queries or connections coming from the internet. All right, so this is the VPC. How about the subnets? I can click on the subnets. Let me also make that a little bit bigger. So I have 3 subnets, as you can see here, and they all belong to the same VPC. How do I know? VPC ID is the same, and the name that we assigned. And here are the subnets that have been provided: 172.31.00/20, 16, 32, and so on. And these are the usable IP addresses in each subnet. You will find that there is a discrepancy. A /20 should give me 4,096 IP addresses. The first one is the network ID we cannot use. The last one is the broadcast ID we cannot use. So that should have left me with 4,094. The other 3 are reserved by AWS. So the first IP address, not the network ID, the one after that, the first usable IP address, and the second and third are reserved by AWS. You cannot use them. So you can start from the 4th if you want. And here it's showing that this is in 1A, 1B, and 1C. And here it shows that all of them are allocated to the same root table. And I think this is the important information about the root tables. All right, what about the VPC itself? What's the CIDR block of the VPC? The CIDR block, as we mentioned, is here, and the subnets we have seen are carved from the same CIDR block. What if I move to, let me see, Sydney, Australia? So as you can see here, if you click Sydney, this is AP Southeast 2. This is the code for it, and this is the name of the region. I have a different VPC ID, a different one, but the same range. And if we scroll to the right, there you have a main route table. It's a different route table ID, and it's the default, and it's in the same account. And if I do a resource map to find out what resources we have in this VPC, let me drag this a little bit up. You'll have the VPC, the new one, and then I have 3 subnets connected to 1 route table and internet gateway. So as if AWS is creating the same VPC configuration for you everywhere in all the regions, 1 per region. But if you are not happy with it, go ahead and create whatever you like. So if you're not happy with this, you can decide, no, I don't like it. I'm going to use something else. I'm going to create something else. And that's why there is an ability to create a VPC, a custom VPC basically. All right. So now let's check the root table. What root tables do we have? So we have only one root table available. And if I select it, I will know the configuration in that root table. So here I have two roots. One is saying that the destination, here as you can see, the destination 172.31.00/16 local. Local means what? That means the implied router who holds this root table knows about anything within this range. Now, what if I need to get to the internet? Internet is anything else. As we mentioned before, there is no way anyone would set and write the millions and millions of internet IP ranges in a root table. This is the default route, which is saying anything else not belonging to any of the entries that are explicitly configured, please forward it to the IGW, to the Internet Gateway. And if we click here on the Internet Gateway, you will see that we have one Internet Gateway and it is attached to our VPC. So it is attached to this VPC. If we go back to the root tables, that is fine. Here is the root table. These are the roots in the root table. Which subnets is this root table applied to? So we look at the subnet associations and we find out we have subnets without explicit association. So basically these are using the route table right now. If you want to change association, you can edit and you can take one subnet and assign it to another root table if you would like to. So that's how we switch. We're going to see all of that. So for now, this is the walkthrough for the automatic VPCs that have been created. Let's switch back to US East 2 in Ohio. And this is where we are going to create our stuff. So if I switch to Ohio, I will find that we have the same VPC, but a different ID. And if I click on that and I do root resource map, you are going to find the same thing. I have three subnets. Let me move this one a little bit up. Three subnets in 2A, 2B, and 2C. And then they are associated with a root table, and the root table is associated with an IGW. So it's exactly the same. But the task we have at hand is to create a new one. All right, so let's now create the VPC that we have discussed before, the one with the 4 subnets and the details and the root tables given and so on. So let's go ahead and create that now. And it will be a custom VPC in US East 2, and these are the subnets. Subnet 1, 31.0.0, subnet 2, 16.0, and then I have 3, 32.0, and 4, 48.0. And we're going to create root table 1, root table 2, and root table 3, 4. And these labels, we're going to use them, and this is going to be in availability zone A, availability zone B, and availability zone C. All right, let's go ahead and create the VPC, allocate the CIDR block, and then move on to creating the subnets and the root tables and do the association. All right, so let's go ahead and do this. Here we are in the console, and I have switched the region to United States, Ohio. And if you look here, you will find out that this is US East 2. What do we need to do? I need to create a new VPC. And I can do VPC only, or I can have AWS help me create subnets and create root tables and network connections and so on. That is if you need help from AWS. In my case, I want to show you how you can do it from scratch. So I'm going to choose VPC only. And the name was custom_VPC. The CIDR block given was 172.31.0.0/16. And believe it or not, by clicking Create VPC, you have now successfully created a virtual data center in AWS. And it's isolated by default from anything else. And let's see what else was created. So when you look, these are the details of your VPC. So there is a main routing table that ends, the ID of which ends with 833. This is created by default for you. There is a network ACL. We're going to talk about this later on when we get to security. And we don't have any subnets. And we have only one root table. If I look at the CIDRs, I have only one CIDR and it's associated. And that's it. So if we want to know the details of the route table, let's go and figure it out by clicking on this link. Or I can go here and from root tables, Let me just refresh this page to show the new one. This is the new one. So I'm going to here give it a tag or a name, custom VPC def for default. All right. So what do we have inside this root table? I can scroll up, click on roots, and then we have the range that we have allocated. And if I want to edit the roots, I can always click on edit roots and I can add, but this one, the default one, I cannot remove it. So if I click for add a root, for example, and I add a root 0.0.0.0, send it to, let's say, local for now. It's meaningless. Don't worry about what I'm trying to do. But here, as you can see, you can remove the customized ones, but you cannot remove this. So what does this one mean? It means any subnet within the CIDR block of the VPC, current subnet or future subnet, I know how to get to it locally through the implied router. That is what it means, and you cannot edit that. So let me go back. I don't need to do any changes now. So these are the routes available. What subnets are associated? I don't have any subnets in the VPC yet. That's why there is no association. So this route table is not applied to anything, but it has been created. What do we need to do now? We need to start creating the subnets. So let's go ahead. Here's the subnets that I have. These are the default ones. And how would I know? They all belong to the same VPC that ends with DE2. But if I check my VPC, DE2 is the default, and I can always highlight it as the default, so it becomes easier when I see it in the different screens. And I have the custom VPC, which is mine. So let's go ahead and create the subnets now. So I have 3, and they're all in the default VPC. These are the automatically created ones. I'm going to click on create subnet. And which VPC? I'm going to create it in the custom VPC. If by mistake you go and create it here, now you are creating a subnet in a completely different data center, which is not the right one. So you have to be very careful when you have multiple VPCs, which one are you choosing? So I'm going to choose the custom VPC. And what is the subnet setting? What's the name? So this is going to be subnet. We can do _1. You can do it _-1, _space1, whatever you like. Which availability zone? If you remember, the assignment was subnet 1 in availability zone A, subnet 2 in availability zone B, and subnet 3 and 4 in availability zone C. And the ranges are 3100 for subnet 1, 3116.0 for subnet 2, and then 48 and 32.0/20 for 3 and 4. So I'm going to create this one in US East 2A. And the range, the CIDR block for the subnet, and I'm going to have 172.31.0.0/20 as the subnet, as given. I don't need to change anything. And I can create a new subnet, another one, subnet 2. So this is going to be subnet _2. The availability zone is going to be 2B, and the CIDR block is going to be 172.31.16.0/20. And we have already put the name. And then we have 3 and 4. So this is going to be subnet _3. Availability zone is going to be C. And the range is going to be 172.31.32.0/20. And last but not least, I need to have the last one, which is subnet 4. So subnet _4. And this is going to be in C as well. And the range is 172.31.48.0/20. Let's say you make a mistake. So for example, let me here go back and say 30 only, for example. And I try to create, what will happen? CIDR is not within the CIDR address from VPC. So they are telling you, now you are trying to create a subnet that does not belong to the pizza. You cannot have a pepperoni pizza and you try to get a slice that has seafood. It won't happen. So here they are telling you, we are watching you. Now you are trying to configure a subnet in a range that does not belong to you and to this VPC, so please fix it. When I fix it and create subnets, now as you can see, it is creating subnet 1, subnet 2, subnet 3, subnet 4. This is the beauty of the cloud. From the dashboard, did some clicks, and if you are familiar with this, it wouldn't even take 1/10 of the time that is taking me. And if you know infrastructure as code tools like Terraform, you can have a script ready and it will do it, everything that we have done in 1 minute. So the point I'm trying to make is the orchestration and management is now doing stuff in different data centers, in the AWS different availability zones, in an AWS region, in Ohio, and I'm sitting in Dubai right now. And this is all happening without me knowing which devices, which equipment that this will be configured on. Is it software or is it hardware? What is the switch? What's the router? I have no clue. So this is the management and orchestration that sits on top of the physical infrastructure of the data center, and that is what makes a cloud called a cloud. So let's check the subnets and see if we have what we needed. So now let me just minimize this so we have more working space. Okay, so I have subnet 1, all right, and subnet 1 is assigned the range 00/20. Then 16 is subnet 2, and each one has an ID that was allocated by AWS. I did not intervene in the selection of the ID. And for the availability zone, the first one is in 2A, which is subnet 1. Subnet 2 is in 2B, as you can see here. Then I have two other subnets in 2C. So it looks like I've done it the right way, 3 and 4. And as you can see here, they are all attached to a route table, but I haven't created any. Remember that there was a default route table. So this is the custom VPC default. This is the route table that has been assigned to all of them. What do we need to do now? I need to create 3 route tables. RT_1 will be assigned to subnet 1. RT_2 will be assigned to subnet 2. And then RT_3 and 4 assigned to subnet 3 and 4. So let's have a look. RT_1 for subnet 1, RT_2 for subnet 2, and RT_3, 4 for 3 and 4. So let's go ahead and do this. See, this is going to teach us how we can create different route tables and how we can associate or change association for a subnet that I can have a new route table as opposed to the old one. For now, all of them associate with the same route table, which we need to change now. But we need to create the route tables first. So let's click on route tables. And we have the default one. This is the default for the custom VPC. So if we look at the subnets again, subnet 2, 3, and 4, they are attached to the route table. So as you can see here, they are all attached to the route table for the custom VPC default, which is this one. So what is this route table? This is the one for the default VPC. How can I confirm? So this is the default VPC. If I select it, you'll find that it has a route table that ends with 037. And if I go to these route tables, you'll have that it ends with 037. To avoid confusion, I can say that this is default VPC. So what do I need to do now? I need to create 3 more route tables as instructed. So create route table, and this will be RT_1. In which VPC, it's very important to pay attention when you are allocating VPCs. You could create a resource in a completely different VPC, then you go and check in your VPC and you don't find it. This is because you allocated it to a different VPC. So I need to work with the custom VPC, and this is the route table. Okay, create route table. Oh, hold on. We didn't configure any routes. Let's check what happened. So any route table created by default will have this entry. Anything in this VPC, I know how to get to, and this is local to the router. I don't need the help of anyone. So this is RT1. This is the route table that we just created, RT_1. Let me associate it with the right subnet. So I'm going to click on Edit Subnet Associations, and I'm going to take subnet 1, and I will shift it from the main route table, and it will go to the RT_1. Save association. Now, if I look at subnet associations again, let's see what we're going to find. This RT1 has an explicit subnet association now to subnet 1, whereas 2 and 3 and 4 are still having fun with the other route table, which is the default route table. So there are available subnets without explicit associations. I don't want to associate any other one with RT1. So now we have 3 route tables, and subnet association is adjusted. Now we need another one, RT_2. Again, it's going to be in the custom VPC, and I'm going to create it. Believe it or not, same entry has been created automatically and you cannot delete it. Subnet association, this one needs to go with subnet 2. So now I have save associations. If I look at subnet associations again, you will see that subnet 2 is associated with the route table that in question right now, which is RT2. And then I have only 2 that are not associated explicit and available if you want to change association. All right, I need a third route table, and this will be called RT_34. And it's going to be in the custom VPC again. Don't make any mistakes. Create the table. As you can see here, the same entry again, subnet associations. I'm going to edit, and I'm going to select subnet 3 and subnet 4 to be connected to this table. And when you click it again to verify, you'll find that 3 and 4 are associated explicitly, and there are no available subnets without explicit association. Basically, it's telling me all subnets have been associated with custom route tables and none is with the main route table. So let's check again, route table. Let me look at the default in the main. Click on subnet associations, and you'll find that 0 is associated with this route table. We have taken them with a different route table. So this confirms that you can switch route tables association to a subnet, but at any given time, a subnet can only be associated with one route table. All right, so by doing this, we have created everything that we needed. Let's do one extra step that was not required. Let's create an internet gateway and attach it to the VPC. So internet gateways, I have one here, but as you can see, this has been attached to the default VPC. I need one for my custom VPC. So I'm going to call it custom VPC _IGW internet gateway. And believe it or not, now you are assigning a router to a VPC by these 2 clicks. VPC router is available now. The internet gateway is available now. And I can attach it to a VPC, or I can click on here and select attach to a VPC. Which VPC? I need to attach it to the custom VPC. And I'm going to do attach internet gateway. So what you have done now is you have created a virtual data center. You have created 4 subnets, 3 route tables, associated the route tables with the right subnets, and you have also created an internet router, and you attached that, connected that into the VPC. So you have built a full virtual data center right now in AWS. And by the way, this is not chargeable resources. The VPC, the subnets, the route table, the internet gateway, they are all free. Doesn't mean that all the resources in a VPC are free, but these ones are free. So even if now you are going to go have lunch or have a break and complete later on the work, you are not being charged anything. That is not the case for every single resource. As we go, I'm going to tell you what is chargeable and what is not chargeable. When you finish work with a chargeable resource, either you stop it or you terminate it, and you can always recreate it again when you come back and you'd like to work more. So please keep that in mind if you want to avoid surprise charges while working on AWS. All right. Remember that we can switch the region from here. Now, all what I have created is a virtual data center with all its requirements so far given to me in Ohio, in the US, while I'm completely in a different country. In AWS, let's see how we can apply the concept of public and private subnets in AWS VPCs. Remember, we mentioned that a public IP address is something routable, or an IP address routable from the internet, reachable from the internet directly without mediators. And private IP addresses are the ones like that we use at our homes, and the internet cannot see us from the outside, cannot reach us from the outside. One might ask, okay, so how come I can connect from my home, from my private IP address through Wi-Fi, can get to the internet, and internet can get back to me? Remember, there was something called network address translation that is done on the Wi-Fi router, and we're going to discuss that shortly. So let's go ahead and see how in AWS we can do public subnets reachable from the internet and private subnets that are not directly reachable from the internet. So a subnet in AWS is considered a public subnet if it satisfies two conditions. Condition number one, the subnet is created in a VPC that has an internet gateway attached. So for example, if we have a subnet 172.31.0.0/20, there is nothing when we are creating the subnet drop-down menu to select whether it's public or private. How you configure it makes it public or private. So now we have this public subnet, and implied router is there by default in this VPC with this CIDR block. The first condition, the VPC must have an internet gateway attached, and we have seen in the last demo that the internet gateway in a custom VPC is an option. It's not something that is there by default. So that's one condition. What else? The subnet is attached with a root table. That root table must have a default root entry pointing at the IGW. Basically, the root table of the subnet must have this entry. If you have noticed when we did the demo that all the root tables were created with the CIDR block of the VPC only. None of them had the 0.0.0/0 pointing at the IGW. Let's prove it. Here are the root tables that we created. Let me select any one of them. Let's say root table 2. If I click on the root table and look at the roots available, it's only one root pointing at the subnets within the CIDR block. If I choose any other one of the root tables, let's say RT1. RT1, look at the roots, same root. So none of them has any reference to the internet gateway, although we have created and attached internet gateway into the VPC. So having an internet gateway is one thing, but telling your router to use it is a different thing. How can you enforce that the router for a specific subnet is going to send traffic to the internet through the default route? So through this entry that we have seen, 0.0.0.0 pointing at the IGW. All right, so can I make subnet 1 in the VPC that we created a public subnet? Now it satisfies the first one. The VPC has an IGW. Can I make it a public subnet by satisfying the second condition? And the answer is absolutely. If I go here, subnet 1 is associated with root table 1, as we know. So let me click on this and look at the root table for this subnet. You will see that it's attached to RT_1. So what I'm going to do is I'm going to go under RT_1, and I'm going to click on roots and then edit roots. And I'm going to add a root. And in this root, what I will do is I'm going to say anything else not in the route table, please send it to the IGW. So internet gateway. It will ask me which internet gateway, and here is the custom VPC internet gateway. So this integration and AWS knowing the orchestration and management layer, knowing what resources are in my VPC, and it's a pull down menu and I can select them, and that's how easy it is to configure routers to point at internet gateways and attach the internet gateway to the VPC and create subnets and create root tables. So that's the beauty of the cloud. That's why you need to learn the cloud. This is the modern IT. If you are planning for the future, plan it from now. Don't take transitional careers and in 3 to 5 years you realize that I wish I have done like my friends did and I got into cloud and automation and machine learning and AI and all that stuff. So you need to see the difference. You need to appreciate how easy this is becoming compared to traditional IT. All right, so let me choose the internet gateway and save changes. So now let's look at the roots, and now we have two roots, 0000 default root pointing at the IGW, and the entry, the first one. So now we have managed to make subnet 1 a public subnet. So let me go back here, and what I will do just to make my life easier is I'm going to put here an underscore, and I can say public. It becomes much easier for me when I'm creating to identify my subnets, as opposed to if I don't have any tags. These are called tags, name tags, location tags, building tags, production, development, testing, and so on. So now I have managed to create subnet 1 as a public subnet. All right, so this is clear on the public subnet. How about the private subnet? A private subnet is the one that does not satisfy the two conditions, or at least one of them. So this subnet, for example, 172.31.16.0/20, it has a routing table like this. Let's say this is RT_2, or even RT_34 that we created, because all of them, they only have this entry. So these are all 2, 3, and 4 are all now private subnets. Why? Because they don't have this entry. So they satisfy the first condition. They are in a VPC that has an IGW. Okay, fair enough. However, there is no instruction to the implied router to take that traffic from here that needs to get to the internet and deliver it to the internet gateway so it can make it out to the internet. So if you lose one of the two conditions, that subnet is immediately private. Now, if you would like to have your website virtual machine, then you have to launch it in a public subnet, because that's the only way the internet will know about it, and it will reach the internet directly. Whereas if you have some sensitive data, like for example a database, some credit card information, some order information, payment information, patient health records, and so on, this is sensitive, should not be exposed to the internet, and then hackers are going to try to break into it and steal that critical information. So in that case, you need a private subnet, and you can hide it in a private subnet. And as we move on and we learn more about the cloud, you will know that how applications are deployed, and we'll talk about that later in the course. All right, hopefully this one is clear, and you do now understand the difference between public IP addresses and public subnets in the cloud, and also private subnets in the cloud that are hidden from the internet. All right, now let's go ahead and talk about network address translation a little bit more. Understand how it works. We have mentioned that earlier, but now it's time to expose it and understand it. So the network address translation is a feature, or an IP feature, happening on some devices like wireless routers at home or in the offices, to mask or hide the fact that the communicating part, the sender, is with a private IP address, and hide it behind a public IP address. So that's the whole thing. So let's understand this. We have a router performing network address translation. The router connects this local area network, the mini local area network we have on the drawing, and connects that to the internet. The local area network has this range, 172.31.1.0/24. .1 is configured on the router LAN interface, and the router is connected to the switch. And we have a laptop that has an IP address, 172.31.1.118. Both belong to the same network, and everything looks good, and they are both configured on ports that belong to the default VLAN, so they can communicate with one another. And this laptop is configured to send anything that is going outside the network, to send it through to the default gateway, or .1.1. This is all easy. Now the user of the laptop would like to get to CNN.com. And CNN.com happens to have the IP address on the internet, 205.111.37.86. And both are connected to the internet. Connections are live, and life is good. The router got an IP address from the service provider, a public IP address on the WAN side, on the internet side, which is 100.2.55.33. the browser needs to formulate a packet that will go to CNN.com. So the packet, assuming, just for analogy, that it is an envelope, so the message is, or the payload is put inside an envelope, and now the browser is going to write, I am the sender, 172.31.1.118, which is a private IP, and this should go to CNN.com, which is 205.111.37.86. And it will send it to the router because this is going outside the network, so this will need to be sent to the router. The router will receive it, will look at the source IP address, and finds out that this is going on the internet, and the router understands this cannot happen. So what do? NAT will kick in, network address translation, and what the router will do is it will remove the private IP address from the message, and it will replace it with its own public IP address. And the destination does not change. Now the message can be sent through the internet and it will arrive safely at CNN.com. CNN.com will receive the message, read what is required. So that user wanted to go into the financial news page. The response is going to be formulated, put in an envelope, and the sender in this case is going to be the server itself, and the receiver or the recipient is going to be the public IP address of the router. How and why? Because when it received the message, this is what appeared to be the source. So now it gets to the router. The router has a table of mapping of what has been done. And part of that was that I have taken the 172.31.1.118 and I have swapped it with my 100.2.55.33. So now when this comes back, it's going to do the reverse process, but it will not remove the source. It will remove the destination, the one that has been before placed as the source, and swap it with the private IP address, and that is how it gets it to the laptop. So this is how it works, and exactly the same happens at home in our wireless routers. So if we use the same example, and assuming the router received this IP address from the service provider, of course it could be a completely different one, but it's a public IP address. We have this range for the network within your home, which is being broadcast by the router on the wireless LAN. The router has the .1.254 on the WLAN on the wireless LAN side, and this has the .1.120. The exact same thing repeats. The private IP address is the source when a message is being sent from the laptop to the server, gets to the wireless router will stop it, will change this IP address with this IP address, and then send it to the recipient on the internet. And the response is the reverse process. In AWS, when you have a virtual machine that has a public IP address, the public IP address is not configured on the instance. It will be configured on the IGW, on the internet gateway. And mapping will happen between the private IP address of the instance and its assigned public IP address. And we are going to see how that happens in the hands-on lab. All right? So network address translation is extremely crucial to conserve the public IP address space by masking private IP addresses and allowing the use of private IP addresses internally within wireless LANs or local area networks, and converting that into public IP addresses when a communication is required with the internet. And it does the reverse process on the response traffic. Hopefully it is clear. It's very easy, and it happens, and you are using it at home all the time without you knowing. So this is how you are seen on the internet, as a public IP address. And that is how on the internet, when someone attacks a website or a critical system or something, they look at the logs and they find out who was the source IP address. And then wherever that is, they can find quickly the country, which service provider, and from the service provider logs, they can find out who was using that IP address at the time of the attack. And that's how they can track you down to your home. and find you when you have done something wrong on the internet. All right, so be careful when you use the internet. Use it as a good citizen and don't use it as a bad citizen. So let's now do a hands-on lab in the AWS cloud, where we are going to create a virtual machine in a subnet. We want this subnet to become a public subnet. So we are going to edit the IP route table of that subnet in order to point to the internet gateway. It is already in a VPC that includes an internet gateway, as we have seen, the custom VPC that we created. And we will log in to that instance or virtual machine, and we are going to access the internet and access it from the internet to prove that a public subnet means something. So let's go ahead and do this in the AWS console. So what we are going to do is we are going to adjust subnet 1 to become a public subnet. And after that, we need to create a virtual machine in the public subnet. And the virtual machine must have a public IP address assigned. We need to adjust the security group to allow all traffic. Every virtual machine that is created in AWS is protected by a security group. Think of this right now as a protection around the instance. We are going to explain it later on what a security group is. But for this one, in order to void the security group, we are going to force it to allow all traffic. So to do no filtering whatsoever, because we need to test the public IP and we need to focus on that. Once we connect to the machine, we are going to try from the machine to access something on the internet to find out if this is working or not working. And then we are going to ping from the internet to the instance. So from my laptop, I'm going to send messages requesting a response from the virtual machine, and I'm going to direct that request to the public IP address of the virtual machine, and we'll see what happens. Of course, after doing this, we can do some additional step where we are going to remove the part that allows subnet 1 to communicate with the internet from the root table, and we'll try the same tests again, and at that time the communication should stop, which indicates that the public subnet was key to be able to access and communicate with the virtual machine. So let's go ahead to the console and do this. It's very simple. We're going to take the very first subnet, subnet 1. We're going to convert it into a public subnet by adding this entry into RT_1, which is the root table for subnet 1. And we're going to continue our testing as mentioned. So let's go ahead and do this. So here I am in the VPC in Ohio, the same one that we created before. So it's the custom VPC. I'm in the VPC dashboard. I'm going to go into subnets. I'm going to pick subnet 1. Let's look at the root table of subnet 1. It has only the entry that states I can route anywhere within the VPC to any subnet without the aid or help of anyone. So this is the root table. We're going to go to the root table, and we're going to edit routes. And we're going to create a new route that would state anything else other than the subnets in the VPC. Please send it to the internet gateway. And which internet gateway? The one in the custom VPC. Save changes. So now we have forced subnet 1 to be a public subnet. If I go back, let me now label it as such. So I'm going to label this as public. Save. And just to check one last time, here is the entry that made it a public subnet. So what else do I need to do? I need to have a security group that is going to have all traffic allowed in from anywhere. So we can do it separately right now. So under security, I'm still in the VPC dashboard, scrolling down to security groups, and I'm going to create a security group. For now, please don't bother what is a security group. We're going to explain that carefully. So this is the outbound rules, and it shows that all the traffic is allowed to anywhere outbound. I'm going to call it testing _ security group, and description testing VM public subnet. So just a reminder, if I look at it later on, I'll find out what this is all about. And we have to make sure it is in the proper VPC. Inbound rules, I'm going to add a rule that would allow all traffic. We said make sure that it's not going to filter anything. So all traffic from anywhere, and in the outbound, all traffic to anywhere, and create security group. So the security group for me is called testing SG. This is the one we are going to use. So what do we need to do now? So we adjusted the public subnet. We adjusted the security group. Now we need to create a virtual machine in the public subnet. So I'm going to click here and then write EC2. EC2 is the service for the virtual machines in AWS. And I'm going to right click here and open it in a new tab. So I will have the VPC tab and the EC2 is going to be next to it. So instead of jumping on the same page between dashboards, I will have the required dashboards open in separate tabs in front of me. So now we are going to go here, click on instances, launch instance. I'm going to call this testing _ public subnets. Of course, you can call it just testing, call it anything. The name is irrelevant. And I'm going to have it as Amazon Linux 2023. And I'm going to leave it to the size T2 micro. For the key pair login, I'm going to proceed in this case without a key pair, doesn't matter. Network settings are important. I want to make sure that it's going to be in the custom VPC. And I want to make sure it's going to be in the public subnet. This is very important, assigning a public IP address to the instance. Make sure that this is enabled. And I'm going to select an existing security group. As I mentioned, you cannot create an instance without a security group. So here we're going to choose the testing one that we created. Okay, and that's it. Quick review. It's Linux, T2 micro, and without a key pair, that's fine. Custom VPC, and subnet 1 public, and has a security group testing that allows everything. Launch the instance. So the instance has been successfully launched. And I can click on connect when it is a blue color. And I'm going to choose EC2 instance connect. Scroll down, click on connect. I'm now trying to log into the instance to open a connection into the instance so I can use it to verify whether it has access to the internet or not. As you can see, we are in the instance right now. The instance has a public IP address and has a private IP address. So let me do sudo su. And from here, I can try to ping an IP address on the internet. Ping is a testing tool that is used for troubleshooting to find out if another host that I know the IP address of is alive or not. So one that we know on the internet is the Google DNS 8.8.8.8. This is connected to the internet and it does accept ping packets or messages and responds to them. So let's click on ping. And here, as you can see, the response is successful. How do I know? If I do Control-C, stop it, you'll find that 7 were transmitted, 7 were received, 0 packet loss, and the time. That means the virtual machine on a public subnet can access the internet. All right. Can I access it from the internet? So let's take the public IP address. And I'm going to go into my terminal on my MacBook, on my laptop. In your case, you are going to open Windows command prompt and you will do exactly the same. Okay, so here we go. I'm going to do ping and then Control-V to paste the public IP address. So the 3.146.178.137 is the public IP address I grabbed from here, from the instance. And if I do ping, as you can see also, it is successful and I'm getting responses. How can I know? Control-C. 6 packets were sent, 6 packets received, 0 packet loss. This indicates that by having the instance on a public subnet with a security group that allows communication out and in, we were able to communicate from the virtual machine outbound to the internet and from the internet inbound to the virtual machine, which confirms that a public subnet is key into this. Now, how else can we confirm? Okay, let's go ahead into the VPC again. And let me go into the root tables. And on root table 1, here are the roots. I'm going to remove this one again. So edit, and I'm going to remove this. And I'm going to save it. Now let's go ahead and try from my laptop if I can get to the instance. So here I am. I'm going to repeat the same command. And now, as you can see, there is timeout, timeout, timeout. Why? It's the same virtual machine. It has a public IP address. And I was able a second ago to ping it from my laptop. What happened now? What happened is the placement of the virtual machine or the instance right now is on a private subnet, not a public subnet. So despite the fact that it has a public IP address and the public IP address still exists on the instance or the virtual machine, it is unable to get this traffic, and even if it gets it, it will not be able to respond. Because the root table for the subnet, subnet 1, is no longer able to communicate with the IGW. It's not instructed to communicate with the IGW. The way it stands right now is this way. All right, let's do one thing. Let's add the entry again. And I'm going to say anything, please send it to the IGW. And before I click on Save Changes, see, we're still timing out. Let's go ahead and do the Save Changes and see what happens now. See, it immediately started working. So this confirms that if you want workload that is accessible from the internet in AWS, it has to be a workload, a virtual machine, an instance that has a public IP address and it sits on a public subnet, and the security group allows the communication in and out that you need to have with the virtual machine. All right, hopefully this is clear. It confirms our point and everything looks fine right now. So let's do one thing extra. Let's see what IP address do we have on the instance. Do we have the public IP address on the instance or not? So let me go back to the virtual machine. And I'm going to do the command IP address or IPA. Let's see what IP addresses exist on the instance. Let me just make it a little bigger. So this is 172.0.0.0.1. This is a loopback interface, troubleshooting, testing on the instance. That is not the communication IP address. Then I have number 2, which is ENX0. And if you look here, you will see that we have the INET, the IP address on that interface, 172.31.4.177, which is exactly this one. So the private IP address exists on the VNIC, on the virtual network interface card of the instance, and it has a broadcast IP 172.31.15.255. All right, and the mask is /20. All looks good. But where is the public IP address? Where is this IP address? Why don't I see it here? The reason why you don't see it is because it is configured on the IGW, and there is network address translation happening on the IGW whenever this instance needs to get to the internet. That will take care or will swap the private IP address with the public IP address. How can we prove this? How can I prove that this is existing? Let's ask the internet. So on the internet, what we can do, so we did the IP address and we saw that we only see, or we only have the private IP address of the virtual machine configured on its VNIC. You could have used this one as well as a command. If you are on Windows, all you need to do is ipconfig only without get interface address and all that. So open the command prompt and do ipconfig. If I do curl interfaceconfig.me This command, if I use it now on the virtual machine, it will tell me how does the internet see me from an IP address perspective. So let's do curl ifconfig.me. So let's do curl ifconfig.me. So I'm asking the internet, I'm going to send you a packet now. Can you tell me what is the source IP address that you see in that packet? If I hit enter, you'll see here the response 3.146.178.137. So the internet sees me as 3.146.178.137, which is the public IP on the instance. And that confirms that there is a device somewhere that is converting the source IP in the packet, which is 172.31.4.177, on the way out. When the packet is going out, it's converting that into this IP address. And that's how the internet sees me. And the proof is this. So which device is that? That's the internet gateway. This is documented in AWS. And we just proved it, that we don't have the public IP address anywhere on the instance. So the IP address command basically lists all the IP addresses that are on the virtual machine and proves that there is no public IP address configured on that virtual machine. And we have found that the internet still sees us, or sees the virtual machine with a public IP address. So hopefully this is clear. Now we confirm that this is happening. You could use the ifconfig or the curl ifconfig me as well on your Windows laptop if you have one, direct from your laptop to the internet and see what will be your public IP address. But in your case, that will be the one from your office router or from your home wireless router. How that is changing or doing network address translation to your IP address when you communicate with the internet. All right, hopefully this was clear. Now, since we are done, I'm going to go ahead and terminate the instance. If you wanted to do some more testing, that's fine. At the end, please make it a habit that you terminate the instance or the virtual machine when you don't need it. Don't worry about the root table and VPC and all that. These are free resources, but the virtual machine is not. Hopefully this was easy to understand. Thank you very much. Okay, so let's do a demo. And the demo, you will do it from your own PC, whether you have Linux, Mac, or Windows at home. And it will show you that the wireless router does actually do NATing between the IP address that you have and how you are seen on the internet, and it will be a public IP on the internet. So you are seen as if you are the IP address of the router. So what we'll do is, in your case, you will be connected to a laptop, and the laptop is connected to the internet. So you will have a private IP from your wireless router. You are connected through the wireless router, not directly to the internet. So the private IP that you have is most probably is going to be a 192.168 IP address. Most of the routers or the wireless routers do that. And then it has a public IP here, and the internet will see you through the public IP on the router. That's what happens. So to simulate this, and since I don't have a Windows machine or Windows PC, then I will launch a Windows PC on AWS, and I will connect to it, and I'm going to use it as if it is my PC at home, and I will check and see if there is NATing happening or not. You follow the same steps on your PC, and you should see the public IP of your router. So let's go ahead and do this, and I'm going to show you how it happens, how it works. We are going to use the Windows command prompt. I'm going to show you ipconfig first, because that will show you the private IP address that is on the machine itself from AWS. And then we are going to use the curl ifconfig.me, and that should also show us how the internet will see us from the outside. So let's go ahead and do this. So I am on a Windows machine. What I will do here is I will write cmd, and this is the command prompt I'm talking about. All right, and I'm going to make it a little bigger, so hopefully you will be able to see better than when it is very small. And I'm going to start with ipconfig. ipconfig will show you the IP address that is on the machine. So let's see. So as you can see, I have an IP address. This is forget about DNS for now. This is the IP address that I have, IPv4 address, as you can see, and it is 172.31.80.56. And the subnet mask is 255.255.240.0. Can you tell me in a CIDR fashion what is this size? Is it a /24, /16, /20, or all of the above? So this is 8, 8, 240 is 4 ones plus 16, so that will become 20. So this is a /20 subnet. All right, so this is my private IP. What if I do curl and then if config.me? As you can see here, it's saying that you are seen from the internet as 52.87.238.95. All right, so if I may just move this to the right a little bit and minimize the view, minimize it again, you will see here that the 52.87 IP address, and this is the private IP address. So that's the IP address that we have, and it shows you that there is NAT happening. Of course, this is on the IGW and AWS, but in your case, it's going to be in your wireless router. In case if your operating system does not have the curl, if it tells you curl is not recognized, that means you have to install curl. Or if you are satisfied with what you have done in the cloud on the Linux machine, and you have seen the curl and you have seen how the NAT happens on the gateway, so that's good to go. Or of course, you can go to your best friend, ChatGPT, and tell how can I install curl on a Windows 10 or Windows 11 that you have, and it will tell you exactly the steps. Once you have the curl command, you can do curl if config.me, and it will get you the public IP address. Now it's time to talk about the network reference models and protocols. If we have multi-vendors, we have, let's say, an access point from HP, network from Cisco, and we have cables from a Chinese company, and maybe we have data center switches, let's say, from Taiwan. When they manufacture these, what are the electrical signals or the optical signals on the cables that is acceptable by all parties? What is the shape of the connection that needs to plug into the switch, and the size, and how many connectors, and whether it is copper or it is something else? How should the packet look like exactly in order for that to be understood that this is coming from this place to that place? Where should the IP address for the source be placed? Where should the destination IP address be placed? So all of these are standards for people who are working on cabling, on switches, on routers, on software, on browsers, on website engines, to find out how they should build it in order to be interoperable with the other vendors. And now any startup, given these standards, can start and work on cables. Maybe they have a better quality cable, or maybe they can compete on the price. And also for other companies to work on switches and compete with Cisco, HP, Juniper, and the like. And also for routers, and also for software, and also for security, and also for applications and browsers, and so on. So the standardization, or this standardization, requires a reference model. And that is what we need to discuss now. So first of all, we'll start with proving to you that we require more headers in an IP packet than just the source IP address and the destination IP address. We'll also talk about the Open System Interconnection, or Open System Interconnect, the OSI reference model, which is the standard model for the networking. That will take us to talk about TCP and UDP protocols, and what is a protocol, and other known protocols in the networking field. We're going to pick some of the common ones that they will come in handy, and you will come across them frequently, no matter what career choice you are going to go after when you finish this course. Again, if you would like to get more knowledge and more depth into this course, you want to get more design assignments, more practice, more hands-on labs, and also the IT tools primer that will give you a 50,000 feet view of what is Linux, what is Git, what is GitHub, what's Docker, what's Kubernetes, what's Bash scripting, and Terraform, what's Docker and Kubernetes. This is going to be available on our website, and you will also support us in creating more free content like this one at this quality for you to enjoy and for you to grow as well. This course the supplemental material can be found at www.dolphinet.com/courses/ITF-course.